hear everyone. And do use the chat boxes for questions, as Ola pointed out. And also, since this is quite informal, if you have others, I would say that during the talk, we probably encourage questions while the talk is on, even. If there is somebody who has a very urgent question, maybe the moderator can allow that. And Ula, are you going to be moderating, just so I know? Are you going to be the person handling the sort of the transitions and so on?
Well, I will unshare, but it's actually set up so people, only one person can share at a time, but I'm not going to, heavy-handedly turn people on and off or anything like that. So we'll just let people do that on their own and help out, of course, if something is needed, help it.
Terrific, terrific. Thanks. That's all I have to say.
Right.
Yeah, I would just add that I will try and keep an eye on the chats for anyone that wants to post a question there, but I really like the idea of this being informal and stimulating lots of good discussion. I think short questions during the talk should be encouraged, and then anything that turns into a lengthy back and forth we should perhaps hold for the Q&A after each talk, or even the discussions at the end of the day. In terms of the material, I think I'll just echo what Ollie said, is that what resonated with me is this connection between real and momentum space, and that's something that has always fascinated me about condensed matter, and I think it's here in spades in this material with the topological aspect. So yeah, I'm excited about today. So take it away.
Thanks. And finally, the CATS, the Center, our EFRC CATS is led by Rob McQueenie, who's on also. I don't know if you want to say a few words, Rob, before we kick off.
No, I won't say much, but obviously you can tell by the name of the center that we're really interested in topological semimetals, and I think the Mn3X compounds are some of the most heavily studied in that class of materials, and so there's a lot of people in the center who are currently working on it or interested in expanding their research. So, as a center, we use these kind of forums to allow us to know what is the latest in a class of materials, what is the most exciting research going on. And then, when this workshop is over, we go back and we strategize about where we think the most promising directions for us to go are. So I appreciate, everybody coming in and telling us, what the most exciting things are in these materials. And so I'll be listening intently all day.
All right, thank you. So with that, I'm going to stop sharing and turn this over to Binghai Yan, our first speaker. We'll talk about band structure topology-induced anomalous transport phenomena and manganese-D, germanium, and manganese-D tin. Take it away. You are muted, so there. Now you're unmuted.
Okay, now I'm okay?
Yep.
Yeah, okay. First, thank our organizers for the kind introduction and also for this wonderful idea to organize this workshop. My talk will be about the band structure perspective related with the Barry curvature topology and in these interesting materials. And before going to details, I first thank my group, also including my former students, John, Hao, and Jacob in Dresden, and also my current postdoc, Huixia and Ku. And this theory work I will talk and is closely inspired and collaborated with Claudia, Stuart, also Cameron. Cameron will be the second speaker today. This is my outline. I will start talk generally, the general idea about the anomalous Hall effect and these AFM materials. Then I extend to the anomalous thermal Hall effect and this thermoelectric interaction. And if I have enough time, I will talk about the most recent results about the spin Hall effect. Okay, let's start the anomalous Hall effect. We are very familiar with this formula. And can you read my mouse? Yeah, good, thanks. Then here we know that for the anomalous Hall, here this is the trivial Lorentz force contribution linear to magnetic field. There's another contribution related with the magnetization. And this is an anomalous term. This is a historically very well-known term. And for this anomalous Hall effect, there's an intrinsic contribution. Intrinsic means it's determined by the material property by itself. And we know this is the barrier curvature. And then barrier curvature is a property related to the band structure and the block wave function. And a very important consequence of the barrier curvature is the anomalous velocity. And here we know if we have a non-trivial barrier curvature, we will get a velocity perpendicular to the electric field to drive the electron moving. Therefore, this is a transverse Hall effect. Then we get the Hall conductivity from the barrier curvature by integrating all the occupied electrons. And this is a well-known textbook established now. And go to the band structure, this barrier curvature is closely related with these features. Like this is a band anti-crossing. We get a huge barrier curvature. Also related with the band crossing. Here is the wire points. The wire point play as a monopole point. And we have positive monopole, negative monopole. In between, we have a net flux. This flux, in other words, is the integration in the momentum space. And we get the Hall conductivity. And we also know in some systems, actually, only these two terms are not enough to fit the Hall resistivity. And we have a third contribution here. This is called, sometimes called topological Hall effect. Its feature is like, let's see, this red curve is the faking with these first two terms. And we possibly have anomalous Hall here, but there's an additional hump. This hump is related with a special spin structure and a finite magnetic field. This spin structure determines here is called spin chirality. Actually, it's written this way. This means these three spins form this chirality. It has a non-zero solid angle. And later these days, this idea is was introduced to understand the real space. Like for example, this is skirming lattice. One skirming give you in real space a non-trivial barrier curvature. And this is a topological Hall effect. It requires here, it has this non-collinear spin structure, but it should be non-coplanar. Okay, this is a general feature.
I apologize for interjecting, but I forgot, I would like to record this. If you do not like your talk to be recorded, let me know and I will not do it.
Yeah, I'm fine with it. Yeah.
All right, thank you. Go ahead.
Yeah. Okay, now we have this formula, like we have the ordinary Hall, we have anomalous Hall. This usually we call the momentum space. This is the real space, the spin texture Hall effect. And then somehow we think we can understand most of this anomalous Hall system. And clearly, here we know for AFM system, for example, this is the ordinary AFM, the anomalous Hall is 0. And with this old knowledge, we know the magnetization is 0. And the spin texture, this spin chirality also 0. But more important actually is for ordinary AFM, there's a symmetry, is time reversal combined with the space spatial symmetry is like a time reversal together with a half lattice shift. And this is the symmetry of the ordinary AFM. Then here, because of time reversal symmetry, it kills the anomalous Hall, making it exactly 0. But here we still miss some part. Some very interesting part is there's a special AFM. Oh, sorry. This is a collinear, non-collinear AFM. All the spin, they stay in the plane. In this case, magnetization are 0. The spin chirality also 0. But the question is, here the anomalous Hall 0 or not? The different, this non-collinear AFM, different from the ordinary one is here. This combined symmetry with the time reversal is broken. And actually, this broken allow a new anomalous Hall out. This new anomalous Hall clearly is different from these two terms, right? Because we don't have magnetization, we don't have spin chirality. And here today, we start here, this is related to this interesting material. The idea, I think, is started with the seminar theory work by Chen, Yu, and McDonald. And they pointed out in this cubic non-collinear AFM material. And although the total magnetization is 0, and then there's an anomalous Hall effect along this 111 axis. Like that means in the 111 plane, they expect you can mirror anomalous Hall. Unfortunately, this cubic material is very hard to detect this anomalous Hall, maybe because of the magnetic domain. But only recently, there's a spin Hall effect that was mirrored here. But fortunately, we have other materials. This is Mn3Ge and germanium. And slight difference, this is a hexagonal material. Similarities, they all share the same magnetic plane. This is kind of Kagome type plane. The bigger atom are manganese. And this blue are another layer of manganese. The small atom is tin or germanium here. And their spin structure is this non-collinear in the plane they formed here. And then quickly, 2 experiments, one from Tokyo, another from the Max Planck, observed in these 2 materials the strong anomalous Hall effect. Okay, now let's go to the details of this material. First, like this is the crystal structure I said, it's layer by layer. Although I plot in a layered way, but actually the atomic distance is really short. They are kind of well-defined 3D material. But the spin, as far as we know, their spin structure, they all like to stay in the plane. This is a co-plane AFM. And they have a different possibility, and from earlier theory and recent neutron scattering, I think the third speaker will talk about the spin structure. And these 2 spin structure is the most favored one. And then actually, there's an in-plane magnetic field. If you apply an in-plane magnetic field, you can all rotate this spin spontaneously. You can convert from one to another and get intermediate states. There are many possibilities. By the way, in the literature, as far as we know, actually, there's many materials in these 2 families. One is this cubic one, another is a hexagonal one. And so today I will talk about germanium and tin because they are reporting the experiment. Actually, they are also more interesting. Their magnetic order temperature are far above room temperature. Therefore, they are if there's something interesting related with this spin structure, and they appear at room temperature. And then let's go to the anomalous Hall. There are first 2 experiments. This is a tin germanium. This is the room temperature result. I only show one. This is a standard anomalous Hall result. And you see there's a finite magnetization, but it's tiny, it's a really small one. And you can see this one with a larger magnetic field. And here, this is an anomalous Hall. And this anomalous Hall effect, first, there are 2 effects. First, we see the strong anomalous Hall. Second, I pointed out, this is the pure Hall signal. And here, this I0, this Lorentz part is really small. This slope is tiny. The one reason is because these materials, they are metal, they are well-defined metal. This is a band structure. There are a huge number of dense states at the Fermi energy. Therefore, this Lorentz part, this slope becomes very small. And okay, this give us an advantage. Let's see, as long as we observe something, this anomalous Hall give us a super strong signal. And let's go to the detail of this material. Let's start from the symmetry. And this help us to understand this anomalous Hall. I started with the 1 spin structure. And actually, this blue and red, they represent 2 different layers. And they share this spin order actually force the system to have a symmetry. Is My means the mirror plane, Y plane, and mirror from up to down. Then have a half lattice shift along the Z-axis. Then we exchange the blue and the red spins. This symmetry actually help us a lot to understand the barrier curvature and anomalous Hall. And let's see, we know barrier curvature is kind of a pseudo vector. The pseudo vector actually and mirror reflection, it behaves very different from ordinary vector. A pseudo vector, if it's perpendicular to the mirror, in the mirror reflection, it remains the same. It does not change direction. This is the same for spin and barrier curvature. They are pseudo vectors. But if they are parallel to a mirror, and they will reverse the sign. As I said, we want to get the anomalous Hall effect. The anomalous Hall, we just integrate the barrier curvature in all the momentum space. Suppose we integrate the barrier curvature in this box. We have plus, minus, then we get exactly 0 because they cancel each other in both sides of the mirror plane. But only this term will survive. And actually, this is the numerical result about the barrier curvature. This is the XZ term. This is like perpendicular to the mirror plane. This is the mirror plane. And they all have the same sign up and down. Therefore, when they sum it over, we get the sigma xz is not 0. And in compare, and sigma yz will be 0. And the same for the sigma xy. Sigma xz means if we apply a current along z-axis, we will mirror the Hall voltage along x. And if we apply the current along x, we mirror the voltage along y, we get 0. Okay, for another spin structure, here it has a different symmetry. It has a very simple one, it's the Mx. Follow the same argument. Mx will make the new term, this omega yz term, does not change on both sides. But the other two, they change the sign. Therefore, only the yz, sigma yz survive. And also, as I said, we can rotate the spin, right? Now, here there's a beautiful experiment by Cameron. He passed the current across the sample along the z-axis and mirror the Hall voltage in the xy plane. There's this 3 Hall voltage. And then actually, when rotate the magnetic field along this 5 degree, they all give you this cosine theta and sine theta dependence. And here, the sigma 0 is this is the real value of the anomalous Hall. Actually, this is the experiment value, experiment sigma. And actually, tin is slightly slower than germanium one. And they're very close to the theory value. And also interesting here, when ferromagnetic material, usually we get experience. We enhance the spin of the coupling. We enhance the anomalous Hall effect. But here in this case, actually the heavier material, the tin one, has lower SOC, has a lower anomalous Hall. But we will go to the band structure later about this detail. And okay, it has interesting anomalous Hall. And actually at that time where I studied the band structure of this material, I also think that time I looked for other wire sand metal material. And for wire sand metal, there's a very simple estimation about the anomalous Hall because these two wire points are monopoles. The anomalous Hall's amplitude is proportional to the separation between these two wire points. And simply this integration becomes a very simple, like a proportional to the distance of the wire points K0, and the 2 pi is the size of the Brillouin zone. And but that time we think, well, a wire sand metal is a beautiful demonstration of the anomalous Hall effect. However, for quite a time, we didn't have a magnetic wire sand metal material. That time we have tantalum arsenide, we have molybdenum ditelluride, but we didn't have a magnetic material. Then this anomalous Hall gave me a motivation to think oppositely, saying, okay, now I have an anomalous Hall effect. Maybe this anomalous Hall material is already wire sand metal. Then I go back to the material, look at the band structure again. And then this is a metallic band structure. And usually we look at the band structure, we plot it only along the high symmetric line. Actually, in the momentum space, this is the hexagonal Brillouin zone. And there are many band crossing. And this crossing, they are wire points. The wire points also means like, if I zoom to this point, I look at the barrier curvature, I will see a monopole distribution. And a very important consequence of wire point on the surface is the Fermi arc. Like if we project the wire points to the surface, there will be Fermi arc connecting these two wire points. And this Fermi arc becomes an experiment hallmark to identify this wire sand metal. Actually, after our theory, this Fermi arc was quickly observed by the Tokyo group. And okay, now let's look at the band structure detail more. Like since I said anomalous Hall motivate us to think about the wire point, then we ask a question whether this anomalous Hall is dominantly contributed by wire points or not. And what I plot is here. This is the barrier curvature contribution from the momentum space. Let's see, the dominant one is from this red line, these hot pots. Here, actually this region, they are come from the band anti-crossing point. It's not wire point, not necessarily wire point. As I said, band anti-crossing, this feature also generates a huge barrier curvature. Then this contributes a larger value in the anomalous Hall. And for tin, unfortunately, tin don't have this, this huge peak. And because this anti-crossing, actually for tin, it happens here, it's a little far from Fermi energy. And this is, as I said, although tin has a stronger SOC, however, its total anomalous Hall is weaker. This is just related with the band structure detail because the Fermi energy don't cross this high barrier curvature density region. Okay, let's see. Like since we know the anomalous the charge transport, and we also know if the charge transport is strongly correlated with the thermal. For example, if we like the Mott relation told us, if we have a charge conductivity and its gradients with the chemical potential will be the Nernst effect. That means that if we have a longitudinal charge, and we will get a transverse temperature gradients. Also, there's a we know the Wiedemann-Franz law. The Wiedemann-Franz law, we know here, the charge conductivity is related with the thermal conductivity by a constant times temperature. And here, all these holds in the longitudinal transport. It also holds for the transverse one. Yeah, this is actually the beautiful data by Cameron. And here mirror these three different transverse thermoelectric phenomena. Here now we ask an interesting question, for example, about this Wiedemann-Franz law. We know from the textbook, actually, the thermal conductivity divided by the temperature and the charge conductivity at zero temperature will be a constant. This constant only determines by this, this physical constant. This is called Lorentz number. And at zero temperature, it's usually valid for most materials, especially 3D materials. But we also know when temperature is high, at that time we will have an inelastic scattering, and this Wiedemann-Franz law simply get violated. Or in other words, the conductivity, the thermal charge, they are closely related with the scattering. Yeah, we have a tau in the Joule term there. Now, interesting is why this transverse Lorentz ratio can be interesting is because we always claim this sigma and kappa, this transverse part, they are intrinsic property. They are robust against the scattering. Therefore, we call it a topology. And since they are robust against this scattering, then we are curious whether this Lorentz number will be always a constant at all temperature. And if it's not, what could be a mechanism? Maybe it's not related with the scattering, right? Are there something we didn't have a chance to observe? And then this is the experimental Cameron. And I told you first, let's see the simple part. This is the charge resistivity with respect to the temperature. As increase in the temperature, this is a standard increase of the resistivity of a metal. And here, this is represent kind of phonon contribution. There's both tin and germanium materials. Okay, this is a standard metal behavior. But let's look at this Lorentz ratio. What we observe for the tin material, actually the Lorentz number is almost a constant from 0 to room temperature to even higher. However, the germanium one, it's okay, it's L0, it's lower temperature, about around 100 Kelvin. It's just, there's a quick drop. And actually before, for me, when I studied the band structure for these two materials, I never feel they are like, they're intrinsically different. And just the band structure, we have some detail. But why, like in thermoelectric, they behave so different? Then since we argue, like here at 100 Kelvin, you see the resistivity. There's not strange thing happen with, especially with the germanium one. Actually, germanium behaves smoother. And what happens at 100 Kelvin? And okay, before we go to the detail, let's go back to the formula. Here, I put the sigma xy tilde as the 0 temperature anomalous Hall. That means this is the exact sum of the barrier curvature below the Fermi surface. And then this is the temperature dependence. The temperature dependence comes from the Fermi distribution. We know this is the Dart function. This only gives us like the smearing, like this is the smearing function. And but for the thermal, we have another part. We have an energy square here, because here we have an energy flow, and we also have temperature. And we know actually exactly when temperature go to 0, this is exactly recover the Wiedemann-Franz law. But at the final temperature, let's see, at the final temperature, this function is a double peak. In other words, that means the charge anomalous Hall is related with the exact Fermi energy, the 0, 0 Fermi energy barrier curvature. However, the thermal Hall is related with the barrier curvature at both sides, related with the two sides of the Fermi surface. If the temperature is too high, like this double peak is separate too much, and this may make a difference for these two integral. In other words, that's related to the shape of the intrinsic anomalous Hall, the barrier curvature. If it's distribution with the Fermi energy, it's linear or constant. And these two integration are equivalent. But if it's nonlinear or it's highly nonlinear, get higher order term. And if these two start to get different, we get a violation of the Wiedemann-Franz law. Now, the key point is let's look at how this term are different for two materials. Actually, they independent, indeed different. And this is the tin compound. Actually, you see near the Fermi energy is relatively flat, is almost constant. For the germanium one, actually, it becomes highly nonlinear. If this window related with the temperature, and now we feel the difference quickly. And this is the reason why tin is almost flat up to room temperature for the Lorentz number. And but for germanium one, actually, from 100 Kelvin is quickly go away from the Lorentz ratio. And okay, this is about the thermal Hall effect. And my last part, I will like to talk about the spin Hall effect. The spin Hall is like its measurement is like if we drive a charge current along X, and as we will get an opposite spin accumulation here, this is the spin current, the transverse spin current with the spin polarization along Z axis. This is the Euro spin Hall effect we are familiar. And the spin Hall conductivity also related with the barrier curvature. Actually, this term called spin barrier curvature has a slightly different form with the barrier curvature. But fine, this is the way usually we calculate. And spin Hall effect is generally studied for this heavy metal, platinum, tantalum, tungsten, also topological insulators, while Semimetals. And in other words, they are all non-magnetic materials. And for this AFM, non-collinear AFM material, I'm asking a question. And not only like we use the old formula to calculate, we get some value, maybe big, maybe small. I ask maybe a more basic question like, can this non-collinear AFM bring us some new understanding about spin Hall? And for this, let's go back to the symmetry analysis again. For the charge conductivity sigma xy, and we know there usually we can write it in two terms. One is the odd is the time reversal odd, or reverse the magnetic field, we reverse the sign. This is the anomalous Hall effect we are familiar with, or the Hall effect. And we also have an even term. The even term is usually related with the geometry of the sample or the misalignment of the contact. This is the trivial term, is a trivial part, we know. But this is the conductivity, we can usually separate them into two. For spin conductivity, we can also do the same. And for the spin conductivity, this is the time also even one and the time also odd one. Time also even one, actually, this is the conventional spin Hall I talked related with the spin barrier curvature. Actually, there's an odd one. It's related, but it's allowed by symmetry. I only say allowed by symmetry. We will see the mechanism later. And then that means, let's see, like, if we have time reversal symmetry, that means if it's odd and time reversal, and then this odd term will disappear. Odd term will become zero. We only have the even term. Then in other words, for charge is trivial. That means if we have time reversal, we don't have Hall effect. But we have spin Hall effect. We have the even term. This is the conventional spin Hall we talked about. And if time reversal is breaking, we know the odd term come out. This is the Hall and anomalous Hall effect. Then it's the same for the spin Hall. We will have a new term come out. This term actually we are not very familiar. Then in other words, that means like usually spin Hall we usually talk about is the even term. Then what happens for the odd term? The odd term is generally come out as long as the material is magnetic. And for either ferromagnetic or antiferromagnetic. And here, let's see, like this sigma odd term, for example, like if we have a ferromagnetic material and we pass a current, actually the longitudinal current is spin polarized. This is a trivial conclusion, right? A magnetic material give you polarized current. This is one example of the this odd term. But for this AFM material, we don't have net mechanization. And can we get such kind of spin current? Actually, we can start, this is with a Fermi surface of this AFM material, just a simplified one. The circle is the Fermi surface. Here, the blue arrow is the velocity. We know the velocity everywhere point out. And this is the spin. The spin has a special structure. We have three orientations. At k minus k, we have the same spin because the system has inversion symmetry. And at the equilibrium, we know the charge current is zero because all the velocity cancel. The spin current, this is the approximate definition of spin current, V times S. Spin current also zero because here, spin SV parallel, SV antiparallel, they cancel each other exactly. At the equilibrium, there's no current. If we apply an electric field, we know the Fermi surface will have a slight shift. And therefore, we have a charge current start to flow. At the same time, we have a spin current. Because we enhance this parallel, Sx and Vx, this term, we suppress this antiparallel part. In addition, we also have another part, like actually the perpendicular component, this antiparallel component, we enhance this part. In other words, that means we apply an electric field in an AFM material, we get a spin current, spin polarized current along X. We also get a spin polarized current along Y. And this is a kind of special spin Hall effect. And actually this spin Hall effect, with a not surprise, I said is by definition is time reversal odd. When we reverse time reversal, like we reverse the spin by rotate by a magnetic field. This spin Hall connectivity will reverse the sign. Actually, after our theory, recently this magnetic spin Hall is measured in Mn3Ge. And this is the transverse part. Actually, the longitudinal part is also interesting. Like this longitudinal part, you see, as I said, we apply a current through AFM, it becomes spin polarized. For FM material, this is the trivial. But FM material, like we usually use 2FM, build this magnetic ternary junction. And then actually for this FM, like if we make a magnetic domain, actually cross the domain, if two sides are same, let's find the spin current flow. If the two sides are different, the spin current is suppressed. And this is a kind of way, like it's a new type of AFM, internally junction. And okay, in the very last, maybe I don't have enough time. I think if you have a question, you can ask. Here, in addition, I pointed out actually, we recognize this spin Hall effect. Actually, you don't require any spin orbiter coupling in this coplanar structure is here. Like although anomalous Hall requires spin orbiter coupling, here it does not. It's give either for time reversal or even time reversal odd, just because for spin Hall, the only symmetry you need to break is the spin rotation symmetry. As long as we make the electron start to rotate, flip, when it travel, the spin Hall is allowed. That means if the system don't have magnetism, we need spin orbiter coupling to make it flip. But if the lattice already give you a fixed spin structure, especially non-collinear, when electron moving, it has to flip because of the exchange coupling. And therefore here, we don't always need spin orbiter coupling. And yeah, in addition, this is the numerical calculation for the spin Hall. The red one is without SOC, the blue one is with. Actually, they're almost same. That also means actually the spin orbiter coupling don't have much contribution for these two systems in the spin transport. And this is my short summary. I think with that, I thank you for your attention.
Thank you so much, Ming-Hai. It's open for discussion. So if you have a question, just unmute yourself and ask a question.
So can I ask a question?
Yeah.
You're going very quickly as you were showing your cartoon picture of the circular Fermi surface and the spin directions and the VF. Maybe you could just show that slide again, so that I get my head around what you were saying. So I got how this gave you a longitudinal spin current. How did this cartoon give you a transverse? I didn't get that as you were going quickly.
Okay, let's look at this pair.
Yeah.
They are anti-pair level. Along z-axis, let's only look at the z projection, the y direction projection.
Sure.
And they are still anti-pair level like this. Oh, sorry. They're still anti-pair level, right?
Yep.
And this side also anti-pair level.
Yep.
Yeah. And this side is pair level. Somehow, yeah, if we compare this pair and this pair is enhanced. This pair is suppressed.
Yes.
Therefore,
isn't the top right and bottom left, don't they cancel?
Yeah. At the equilibrium, they cancel.
Okay. So doesn't that lead to a net lack of transverse spin Hall, or am I missing something?
Yes.
So I get how there's an imbalance top right, bottom left, but top right, bottom right.
Here, these two, they give you the same contribution. Because S times V are opposite, are negative. Yeah. Yeah, they give you the same contribution. They are enhanced. These two, they are suppressed. Yeah.
Okay, thank you.
Other questions? Please feel free.
Could I ask a question?
Of course.
Sorry, this is Andrew Boothroyd from Oxford. Thanks for the nice talk. I just wonder whether you had any comments about the third compound that you mentioned at the very beginning, which is manganese-3 gallium. Would you expect that to exhibit the same anomalous transport properties as you have described for the tin germanium, or bigger or smaller, or what difference would you expect?
Yeah, good. Yeah, actually, I always have a question I want to ask experimentalist. Like, actually, in theory, we calculate, actually, anomalous Hall for the gallium one is stronger. In theory, stronger. Also, spin Hall are stronger. Like, because it has one electron more than germanium and tin, it's tuned the Fermi surface to a different area.
So you expect the properties to be even more enhanced?
Yeah.
Has the magnetic structure for that 470 KTN been confirmed?
Good question. I think this magnetic space group I think there are early literature
Okay.
about this one. Yeah.
They're all the same. Okay.
Yeah.
All right. Any other questions, comments? That's a very subdued audience. Maybe the time difference is we're literally from Greenwich +3 to Greenwich minus what 7 or something like that. So it's quite a wide span. Well, thank you so much.
Okay, you're welcome.
And yeah, you unshare, and if you also turn off your video, then I will ask Kamran Benia to, yep, there you are, and you should be ready to share.
You hear me?
Yep, very good.
Thank you very much. Thank you for the introduction and for the invitation. So I'm going to also talk about the two types of Berry curvatures, momentum space and real space Berry curvatures in Mn3X, but I'm going to mention a number of other topological magnets during my talk. So what I'm going to present actually have been done in part, I would say even mostly in China, in Zhonghui Zhu's group, and the students you are seeing here, Lin Xiao Ding, Lin Shai Xu, and Xiao Kong Li, made half of their stay in Paris, where they did experiments in my lab, and half of their stay in Wuhan. So my group, Benoit Fouquet and Clément Collignon, were participating in the measurement together with Alaska Subedi. So Binghai has been the driving force in understanding, bond structure of these systems. I'm going to repeat some of the stuff that he talked about from an experimentalist point of view. On domain walls, we had a nice collaboration with Leon Balens, who was the first to put his finger on domain wall topology. The boundary between two domains. And we have also some very positive interaction with Satoru Nakatsuji, one of the leaders of this field. Okay, so the first part of my talk is somehow repeating part of what Binghai said in an experimentalist language. So
let me also repeat, you're okay with being recorded?
No problem.
All right, thank you.
Okay. All what I'm going to talk about are published materials, actually. So, I'm going to talk mostly about transport, not thermodynamics. And when you measure transport, you can either put an electric current, look at the electric field, which is basically electric conductivity. You can look at thermal current and the thermal gradient it produces. Then you have thermal conductivity, and then you have crossed responses when the thermal and electrical effects mix together. Now, just to begin with, you don't probe the same kind of electrons with these three experiments. When you look at electric conductivity, you have this expression, and this is the expression for thermoelectric conductivity, and finally, this is the expression for thermal conductivity. Basically, in each case, you are looking at different population of electrons in respect to the Fermi surface, Fermi level, which is shown by this vertical red line. Basically, each of these formula, you have a material dependent parameter. All of them squeeze this in this function C. This is a combination of density of states and scattering time. Then you have quanta of conductance, the three of them, different between electric, thermoelectric, and thermal. And finally, for the, which is very interesting for what I'm going to talk about, you have a pondering function, which is reflecting actually this population of electrons. And we are going to see that even in the context of topological materials, this distinction remains and is interesting. Now, the two fundamental links, Binghai mentioned it. One is the Mott formula, which relates thermoelectric to electric response. The second is the Widman-Franz law, which relates thermal to electric. Basically, we are going to see that these two formulas are going to survive and be a source of information about topological electrons. Okay, this talk I'm going to talk about three subjects. First, I'm going to talk about anomalous thermal Hall effect and the Widman-Franz law. It's very similar to what Binghai mentioned in his talk. I hope I would just give another way of saying the same thing. Basically, the second part of my talk, I'm going to talk about anomalous nurse effect and the Mott formula. And there are two main messages. The first is that one should make a distinction between two different experimentally accessible numbers. The first is what I would call anomalous nurse effect, SIG, really the electric field divided by thermal gradient. And the second is alpha Ig. And we are going to see that these two things are distinct. There is a scaling between anomalous Hall effect and anomalous alpha, anomalous transverse thermoelectric conductance, if you wish. And finally, the third part of my talk would be about real space-Berry curvature, the chirality of domain walls, which generate not only anomalous Hall effect, but topological and cralar Hall effects. So I hope that I will have time to look at all these three subjects. Okay, let's look at the first part. I'm not going to repeat it. I would say that this is actually a spectacular experimental discovery, which was first in case of Mn3Sn in Tokyo, and then in Hall by Stuart Parkin and his collaborators on Mn3Ge. So basically, this is the signal. I'm grateful to Binghai, who talked mostly about this particular texture, which is very important from what I'm going to talk about. So you have a pseudo Kagome lattice. So it is not perfectly a Kagome lattice because these two numbers are not the same, but it very much looks like a Kagome lattice. And action is happening in these planes. And as you can see, you see a clear step at room temperature. Nothing almost happens on resistivity. Now, when you see this curve, from an experimentalist point of view, it's a piece of cake to measure the nurse effect or the thermal Hall effect. And this is the data I'm showing at room temperature. Basically, this is a large signal. You don't have a lot of difficulty to measure it. And basically, all experimental groups who have looked at this find very similar data. So this is one of the cases where we have actually beautiful physics accessible to rather simple, experimental techniques. And the samples are also not very hard to grow, at least single crystals. So the first thing you want to look at is, yes, well, does the anomalous transverse version of the Widman-Franz law holds? You can measure easily your thermal Hall effect. You can easily measure your Hall effect. Then if you look at the ratio and you compare with this number, you can just ask a very straightforward question. Are these numbers equal? The first experiment we did was on Mn3Sn, and we found that basically we had large error bars because the contacts were rather large, but basically the first answer was yes, it is very similar, and basically we could not detect any violation of the Widman-Franz law within our experimental resolution. And that was published in 2017. Sorry. Sorry, I have a problem with, I should, I have a problem with my setup. I hope to.
So what is the problem?
I cannot change the pages. I go back and I am going to do it again. I'm going to share again the screen. Okay, I think it will work. Sorry about this.
No problem.
Okay. So the story continues when we looked at Mn3Ge. In the case of Mn3 germanium, in contrast to Mn3 tin, this is a detail, but this is important. You can go to 0 temperature and the triangular magnetic order survives. This is something which is not the case of Mn3Sn. In the case of Mn3T, there is another magnetic order which competes with this non-linear, non-collinear antiferromagnetic order, which sets in either at 50K or 200K. So there is no low temperature data. So what I'm showing here is basically the evolution of the anomalous Hall effect between sub-Kelvin temperatures, almost 0.3K, up to room temperature. So these are different sets of data. So the dilution results were done in Paris. The high temperature data were obtained in Wuhan. We looked at 3 different samples, and you see that you have a nice continuity. Up to 100K, basically, the anomalous Hall conductivity is constant. The anomalous thermal Hall conductivity divided by temperature is almost constant. And then you have the Widman-Franz law obeyed within experimental uncertainty, but then you have a downward deviation. Don't understand why. Yes. So here I'm showing what Big High showed. We have a deviation between the Widman a difference between Mn3Sn and Mn3Ge, which is surprising given that from resistivity point of view, the inelastic scattering, it is small in both cases. Now, what does this tell us? It tells us that if we look at the summations of the Berry curvature with these 2 different pondering functions, electrical and thermal, the result is the same for Mn3Sn, but not the same for Mn3Ge. The only way to explain this is to invoke that in the case of Mn3 germanium, we have a change, significant change in the Berry curvature near the Bingham potential of the order of 100K, 10 milli-electron volt or less. Because of that, you are going, as you rise the temperature, you are going to scan a wider window of, your thermal window becomes wider and wider, and then you are going to end up by having this difference between these 2 summations. So just again, to put this picture in a more detailed way, when we are looking at the anomalous transverse response, we have a Berry source and a Berry sink, which have a size in the K space. They have a distance to the Fermi level. Of course, you have a disorder which creates some finite pixel in K space, and then you have thermal broadening. So if you go to higher temperature, you are going to scan in a wider temperature scale and in a different manner for the 2 terms, the electrical Hall effect and the thermal Hall effect. And because of this, you may have a difference between the 2 systems. And actually, this is exactly what ab initio calculations find, that there is a difference between the 2 systems, and the one in which you can expect to have a large deviation from the Widman-Franz law at 100K is Mn3 germanium. So this is again one other argument to take first principle calculations seriously, because the agreement between theory and experiment is not only rather very good about the amplitude of the Hall effect in the 2 systems, but also about the difference between the 2 systems. Okay,
Cameron, can I interrupt there a second? So yeah. I like this argument for the Lorentz number, for the ratio of the conductivity and the thermal conductivity. Does it say something about the magnitude of each? Because around 100, both are changing rapidly. So does it capture that as well as the ratio?
Well, okay. As far as I understand, the theory doesn't give doesn't expect a temperature-dependent anomalous Hall effect. On the other hand, you see, all theory calculates the bond structure. The calculations Bingham showed. It all depends on the position of the Fermi energy. So you expect also to have a difference according to stoichiometry. Now, the fact that we are seeing something around 100K means that there is an energy scale of 10 millielectron volt in the barium spectrum. This is what I can say, actually. So I would say the deviation is something you expect according to theory, but the finest details of this evolution is not something that theory can quantitatively reproduce.
Okay. So you don't get something just from looking at the first derivative of the Fermi function tells you that energy landscape on the 10 MeV scale.
Yes, yes. But you can do, you can basically, it's very much like, because it's not the mod formula, it's a bit more than just the derivative, but basically, yes, you're right.
But it still is interesting that, these deviations turn on so sharply at 100 Kelvin, right? I mean, normally if you think you have some thermal smoothing and you have your sort of E squared minus mu, E minus mu squared, you wouldn't expect that to suddenly kick in so suddenly at 100 Kelvin, right? But you naively would expect it to be sort of have a smoother onset as you start to probe Barry curvature, Barry spectrum farther away from the Fermi level. So that is still sort of very, a little bit mysterious to me.
Well, as I said, the details cannot be reproduced. If I come back to theory, you see, the three curves you are seeing here in the middle panel here are different stoichiometries. And actually, one of the things about these samples are that they are not stoichiometric. So the only thing it is saying, if you look now here, is that in the case of Mn3Ge, you expect to have this kind of variation because of what Big High said, because you have not only hot spots and you have these while nodes. So the overall contribution of all these guys, it seems to be much more sensitive to any change in the stoichiometry. Right. So my understanding is that actually now we should be very careful, because what we are saying for this difference, so maybe come back to experimental result, is that if you look, this is Mn3Sn. Actually, this is our data. This is the data obtained in Tokyo. They match. So at least in Mn3Sn, you cannot detect any deviation up to 300K. But if you go to higher temperature or you go to different stoichiometries, you may also detect such deviation.
Okay.
Okay. So it's basically the beginning of actually this exploration. We are just going to see that, okay, we are on the right track, but not the details. Okay.
Kamran, sorry, Anand here, I had another question. So we know that manganese 3 has this sort of frustrated structure at low temperatures, right? So when you guys are measuring these things, I mean, what is the rationale for thinking that nothing's going to happen below 56 Kelvin, let's say?
Of course, there are a lot of things happen, but this order disappears. Actually, the anomalous Hall effect exists there, but for another field direction.
I see.
So you see, so if I want to do the same experiment, I cannot do it below 40K, 50K, just because then actually spins are out of play.
I see. Okay, I see. So
it's not interesting. The physics is different. That's all. Okay.
So the Lorentz ratio there too, it does not change what you're saying, right? The Lorentz number does not, the ratio does not change as you go below.
Well, we don't have data for that. You see, these data were obtained for magnetic field along X or Y, not along Z. So you see, this is sigma A ZX, K kappa A ZX. You see?
Oh, okay.
Okay. So if you go to 50K, you should look for XY, because spins are along z-axis.
I see.
Okay, so, of course, this is an important detail. I didn't mention it that much, but yeah. Okay, so let me now go to anomalous Nernst effect. I want to be very fast. We have been working on Nernst effect for a long time. This is ordinary Nernst effect. And one thing we know in that if you go and measure Nernst effect in different systems, actually, it is the magnitude of the diffusive Nernst coefficient at low temperature is set by the ratio of mobility to Fermi energy. The cleaner the system, the larger the Nernst signal. And let me here make some important distinction between what I call Nernst effect is this quantity. It is in volt per Kelvin. This is what experimentalists measure. Nernst coefficient is the same, just divided by magnetic field. And alpha xy, which is what theorists can calculate, which is somehow more fundamental if you wish, is in the first approximation, just the Nernst effect, Sxy, divided by longitudinal resistivity. Its units are ampere per Kelvin meter. Okay, now we have a basic understanding of semi-classical Nernst effect. This is very simple. You know, in the same way that the Hall effect is quantum of conductance times the ratio of these two length scales, and the Seebeck coefficient is also a ratio of two fundamental constants and these two length scales. Alpha xy is basically set by the fundamental constants and the ratio of these four quantities, if you wish. I am going to come back to this because Berry curvature is going to mix up with these guys. Now, I'm going to switch, before talking about Mn3X systems in which we measure the Nernst effect, I want to go to talk about another system. Well, it is also a very, it's a ferromagnet discovered by Claudia Felser and collaborators. It has also a large anomalous Hall effect. Its magnitude is unambiguous. It's ferromagnetic below 180 K. It has also a Kagome lattice, but the spins are out of plane. The reason I'm going to talk about this system is that it is semi-metallic. It has a large mobility. So you are going to see in a moment why I'm going to talk about this. So this is also work done with Zhongwei and Binghai. We looked at 5 different samples with different mobilities. Our samples were slightly cleaner than samples previously grown. Now, what is important is that we could change the mobility of these samples a lot without changing the carrier density. So you can see that carrier density N and P are almost the same in 5 samples, but the mobility measured by either the Hall effect or magnetoresistance or just simple residual resistivity basically changes by factor 4 or 5. Now, I just showed you the raw data of anomalous Hall effect and anomalous Nernst effect. In both cases, you see this hysteresis loop. But what is interesting is that if you compare 2 different samples with different mobilities, the dirtier sample, B5, has a larger anomalous Hall effect, but a lower ordinary Hall effect. Now, in Mn3X systems, we cannot see the ordinary Nernst effect because the mobility is so low. This system is a semi-metal, low Fermi energy, high mobility. You can also see both ordinary Nernst effect and anomalous Nernst effect. And now, if you compare them, it's very interesting. You can see that actually, if you look at the ordinary Nernst effect, it is correlating with mobility. The cleaner the sample, the larger the ordinary Nernst effect. On the same samples, when we have measured the anomalous Nernst effect, it is the opposite trend. The cleaner sample has the lowest anomalous Nernst effect. So ordinary Nernst effect correlates with mobility, but anomalous Nernst effect anti-correlates with mobility. So you can put the data on this universal graph. It is where you expect them to be. On the other hand, the anti-correlation with mobility shown here is something which we need to understand. Actually, I'm going to argue that this is actually a signature that this anomalous Nernst effect is intrinsic. Okay, for this, I beg you just to look at this simple expression for the Hall effect in 2D. As you can see, you can write it in this way with all these length scales. I'm just writing the conventional transport phenomena. And so if we go to low field, basically we have this expression. And if we go to high field, we have this expression, which is the expression for Hall conductivity in the quantum Hall effect. In presence of a Fichte's field, what you do is just you replace, the magnetic legs by this Berry curvature, which just means that what we call the anomalous Hall effect is the quantum of conductance times the average Berry curvature divided by a quantity which can be assimilated to the Fermi wavelengths. This is, if you wish, a simple-minded picture of the magnitude of anomalous Hall effect. Now, you use the Mott formula, you do the same thing for alpha. Alpha is the energy derivative of sigma. You end up by having this quantity at low field. This is why the ordinary Nernst effect is going to scale with mean free path. Now, in the case of anomalous Hall conductivity, if you do the same game, you end up by having an average of the Berry curvature over a distance which is set by the thermal wavelengths. And now you have an anomalous Nernst effect which inversely proportional to L. So you see here L is in nominator, here L is in denominator. So this is exactly what we are seeing. And this basically explains this kind of graph. I just want to add that this picture means that alpha xy is intrinsic. So the reason Sxy is variating in opposite way as a function of mobility is just because alpha xy remains the same. Now, we measured another ferromagnetic system, cobalt-2 Mn gallium, which was provided by us by Nakatsuji-san and his group. And we looked at alpha xy and sigma xy. And we can now establish this, that there is a simple rule. If you look at the ratio of these two quantities in this picture, if you go to high enough temperatures, when the temperature begins to approach the Fermi temperature, these two length scales begin to be of the same order of magnitude. So this ratio should become as simple as this. It should become Kb over E. And as far as we know, this is the case of all topological magnets studied up to now. These topological magnets are Mn3Sn and Mn3Ge. So these are based on anomalous Nernst identity systems. We have this cobalt-3 Sn2 system. This cobalt-2 Mn3Ge system has a huge anomalous Hall effect, higher or comparable to BCC iron, slightly larger Nernst effect. But basically, the whole idea that all these data over 3 orders of magnitude, okay, more than 2 orders of magnitude, actually are telling us that this order of magnitude correlation between these two quantities is respected. I just want to mention this is a room temperature value. Of course, alpha xy is going to go to 0 at low temperature. Okay, I'm going to talk now about real space Berry curvature. So momentum space Berry curvature is about Bloch waves, their projection, and the fact that you have a fixed magnetic field in K space. In real space, actually, inhomogeneous magnetization can give rise to an emergent field in real space if this quantity, which is basically a measure of the skermionic number, is finite. You can have an emergent magnetic field in real space. And now, what I'm going to argue is that in Mn3X system, actually, you also meet this real space Berry curvature. Okay, so I'm not going to talk only about anomalous Hall effect. So maybe this data set is important to show. So because of this triangular magnetic texture, you see basically an anomalous Hall effect when your magnetic field is along X or along Y. The order of magnitude of the two signals are the same, and you don't see any anomalous Hall effect when the field is along Z axis. If you look at the magnetization, basically you do see a jump in magnetization. So this is not a system in which magnetization is absent, even if the spins are supposed to be in plane, most probably because there is this weak ferromagnetism comes from canting or the possibility of octuple physics. this is something which is still under investigation. But if you look at the number, you are talking about something which is 5 milli or 10 milli Bohr magneton per manganese atom. Now, something is very interesting about this system is that you have a very well-defined domain nucleation threshold field. And we could not detect any dynamics. Changing the sweeping rate of the field doesn't change. All these curves are on top of each other. So we go from a single domain regime to a single domain regime with opposite polarities of the domains. And there is just a region 2 where you have 2 types of domains with opposite polarity. Now, this nucleation field times the jump in magnetization gives you a way to quantify the energy cost of nucleation, which in the case of Mn3Sn we have quantified. This is a small number, but it seems that the system refuses between 0 field and this field of the order of 20 millitesla at room temperature. Even if you are sweeping a field with opposite polarity to the single domain system, the system stays in that situation, and only at a given thermodynamically well-defined field, it begins to introduce domains of opposite polarity. And this multi-domain regime is what I'm going to talk about, is where Skyrmion physics is emerging. So what is our evidence? Of course, in our group, we don't have any microscopic evidence. What we can do is what people have done in other contexts, in MNSI to begin with, but in other systems in which people suspect to see skyrmions. You look at your anomalous Hall effect, which is here. You look at your magnetization, which is here, and you look at the difference. And you see that exactly in this regime 2, where you have domains of opposite polarities, you have a topological Hall effect. This, you know, on its face value, it's not a direct evidence, it's a kind of indirect evidence for the fact that in presence of domain walls, you have a finite skyrmionic number. The second port of invitation is the emergence of a planar Hall effect. So this planar Hall effect refers to a Hall effect which is not perpendicular to the magnetic field, but parallel to the magnetic field. So we did an experiment in which we looked both at the Hall effect and at the Nernst effect. In both cases, we put 4 different electrodes to look at the electric field perpendicular and parallel to the magnetic field. So in addition to the anomalous Hall effect, in region 2, you have this signal which emerges. It has almost the same order of magnitude that the topological Hall effect. So these are the 3 signals. And basically, we have an explanation for that. This comes from the chirality of these thick domain walls. So here I'm showing a sketch of spin configuration in regime 2. Imagine that you have a domain nucleated at the center. Of course, this is just a way of thinking about it. In the middle of this huge majority domain. Now, if I zoom here, you have a pi domain, pi because of the orientation of spins. At the center, you have a 0 domain at periphery, and in between, you have a domain wall, which is pi over 2. Now, if we look at this, you have 2 ways of having such domains. You know, you can have a pi over 2 domain wall with 0 at the center and 1 pi at the periphery, or the inverse. In that case, you have a clockwise rotation of spins. In the other case, you have an anti-clockwise rotation of spins. You can have the opposite case. Then you still have an anti-clockwise or clockwise rotation of spins. Now, if you are going to do this, the way you are going to have a planar Hall effect, its sign would depend on the orientation of spins. You can either have first a field sweep, which gives you this signal, and when you come back, you will have the signal in the same orientation with the same sign, but at opposite fields, or you can have exactly the same thing, but with opposite signs. So what we found is that actually this depends on the history of the sample. You can train the system to give either a planar Hall effect in this way or in this way. And it all depends on the way actually that magnetic field has been applied prior to this hysteresis cycle. All these experiments have been done at room temperature. And I think that I have ended my time. It was short, but I would like just to summarize. First of all, there is a finite temperature of violation of the anomalous Wiedemann-Franz, which gives you a window to the Berry curvature not accessible by electric measurements alone. I think we have a rather good understanding of the amplitude of the anomalous Nernst effect in this system and its correlation with anomalous Hall effect. And domain walls in Mn3X, which are chiral, actually are really an interesting playground. There are a lot of things about them that we don't really understand. And what is fascinating is that this is a physics which actually is already accessible at room temperature. So thank you for your attention.
Well, thank you so very much for a very interesting talk, and open for questions and comments, so fire away.
Maybe I can start. Cameron, for the domain walls you're mentioning at the end, it strikes me there's the possibility of doing not just simple hysteresis loops where you sweep the field up and then down, you know, through zero, but you can sweep up, rotate the magnetic field, and then sweep down to zero in a different direction. Have you done anything like that to look at the domain wall?
No, but it is a very good idea. Yeah, it's just starting. Yes, you're right.
Yeah, so you could really try and explore that. Yeah, that's quite interesting. I need to think about that some more, but that's kind of cool.
Yes, thank you.
So I have a question. You said you see the skyrmions, and also maybe the same questions for the domain walls. Do you know or have a feeling what is the density? Like how many skyrmions do you have, or how many? What is the domain wall density? Yeah.
Okay, actually, it's a very good question. First of all, let me be clear. I don't claim that we have seen the skyrmions. We have not. You know, it's see people who have the direct evidence for skyrmions in different systems either comes from Lorentz microscopy or from neutron scattering, you know, in K space or real space. The only thing I'm saying is that since there is a difference between magnetization and the anomalous Hall effect, you expect the only way of, you know, the one way of available about this is to have a finite skyrmionic number. Now, the magnitude of the anomalous Hall effect we are seeing is large, which says that, which implies that the skyrmionic density is rather large. Now, one way of understanding it is that actually in this system, the texture is so complicated that in one orientation, actually the change in magnetization is rather large. You see, we have three different orientations. So we need it. And one other thing is that to have a skyrmionic number being finite, we need some out of plane rotation of spins, as far as I understand. I may be wrong. But as I said, we still don't understand where does this weak ferromagnetism come from. So at the moment, our information, so I look forward to listen to Colin Broholm. What are the latest news about these you know, things? But you know, I think the question is still open, how you can have skyrmions in this system.
And what about domain walls? Do you have a better idea there? What's the density of domain walls?
Well, what I can say is that domain walls are thick. You see, because you know, it's a there is a calculation by Leon Balens which talks about several hundreds of angstrom. It means that if you go from one domain for another, it is much larger that just the atomic distance. This is also most probably why we see such a big contribution. So when you go from one domain to another, there is a big region of no man's land where, you know, spins are rotating smoothly, going from one domain to the other. So no, what is their density? I have no idea.
So I just wonder, there's a simple way to relate, and this is usually done in topological Hall effect in skyrmions. You can sort of get an effective field that is related to sort of the skyrmion density. So have you tried to sort of estimate what the corresponding effective field would be for this, and therefore some sort of idea of the skyrmion density?
Yes, it's large. You see, just to give you numbers, the total anomalous Hall effect in this system is equivalent to the Fictius field of 100 Tesla.
Oh, yeah.
And our topological Hall effect is, let's say, 1/4 of this.
Yeah.
So this is a large field.
Right. Right.
Hi, Kamran, this is Anand again. I had a question regarding the field at which you begin to see these domains forming, this you called it a thermodynamic field. And I'm thinking, you know, do we understand how this reversal even happens, and, you know, what sets the field scale? Because I always thought that all of the fact that the lattice follows along with the applied field has to do with this small excess moment that is there in the system that nobody seems to really know why it's there, or at least I don't know why it's there. So you call it a thermodynamic field. So I'm trying to understand where that idea comes from, that you have some intrinsic field at which, in these, let's say, bulk single crystals, there's a small field at which it begins to reverse.
Okay, so what I say is, well, I should be careful with my words, because thermodynamic may not be the best way of putting it. It's a very well-defined field. So, you know, if you take, let's say, iron or all these, you know, common ferromagnets, you have this hysteresis cycle, and actually it's complicated, but basically the system, this is, you know, this is in Kittel, the system has all reason to stay multi-domain. It, you know, being multi-domain will lower the energy of the system. Domain walls are good. In this system, actually, the system refuses to be multi-domain up to a threshold field. And you have domain nucleation at that field. So there are other magnetic systems in which this happens. But here, I'm not sure it is actually understood. This is some specific case of not only this system, a number of other, these topological magnets are like that. Cobalt 3 SN2S2 is one of them. But I'm not sure why. You see, I discussed with a friend of mine who's in magnetism, and when I talked about coercive field, he told me that Nel, you know, the French physicist who, you know, the Nel temperature, said that actually coercivity is one of the most difficult problems in magnetism. It is not as easy as that to understand it, even in the case of ordinary magnets.
So I had maybe a small follow-up, which is that, so I'm presuming you measured multiple samples and with different levels of, let's say, manganese concentration or defect density, and you always find this threshold field, which is well-defined, you're saying, with, or is it that for that given sample, it's always the one field, or?
Yes, but
I mean, is there something intrinsic? I'm just trying to ask if there is something intrinsic about, say, a given material, that at that particular field, that one field, sort of independent, if you will, of some density of defects, you begin to see this nucleation. That would be very curious if that were to happen.
Well, we have not done any study as a function of manganese content. So this is something to be done. But in all samples with the same manganese content, yes, this field is very.
You see the same thing. I see. Gotcha.
Right.
Cameron, along those lines, you mentioned sweep rate dependence. Over what range of sweep rates you went past that quite quickly? I didn't notice.
Okay.
You said there was no sweep rate dependence. Yeah.
So we did it. What is possible in PPMS? So over 4 orders of magnitude. So if there is in dynamics, there should be some dynamics. It is something which is not within seconds to hours. It may be much faster.
But you didn't do anything faster. Okay.
No.
Sorry, I interrupted someone there.
Yeah, I just wanted to comment that for the, so Jonathan from Johns Hopkins, I just wanted to comment that on the relative small field scale that it requires to select one domain in these materials is related to the energy scale of the crystal field interaction. So I don't know if people are used to kind of the exchange plus De Moivre plus crystal field model to explain the magnetism of the system. And here there is some preferred domain in zero field, and this comes from the crystal field interaction. And this is a very small field scale as compared to exchange, energy scale compared to exchange. So then the field that is required to pin down one domain is basically to go against this crystal field interaction.
Yes, but let me precise something. You see, if we go above the nail temperature and come back, then we erase every memory. You see, so the system, but when it is below the nail temperature, which is the case of all experiments I showed, we can train the sample to be single domain. Now, when the sample is single domain, then it refuses to become multi-domain up to some small, 20 millitesla is a small field, which is related to this domain nucleation physics. But I agree with you that the magnitude of this, threshold field should be related to, crystal field.
But that single domain can be pointed in any direction.
In plane, yes.
Yeah, that's what I mean, in plane. So that, when I first started measuring this, surprised me a lot that it didn't discretely lock into the
So
threefold, sixfold of the plane.
Yes, Bing-Kai showed our experiment on triangular shaped samples. Basically, this magnetic field can slide these spins with almost no, effect of, if the effect of lattice on spins is very small.
Right, well, thank you so much. Good discussion. So if there are no more questions, then if I could ask you to unshare your presentation.
Sorry, okay. Sorry.
Thank you. And then we have next speaker up, Andrew Boothroyd. Can you hear me?
Yes, thank you. Can you hear me?
Yes, very well, thank you.
And am I sharing my screen?
Yes, you are.
Fantastic. So thank you ever so much for inviting me to be part of your very nice meeting. Here it's been, in Oxford, it's been raining the whole day, so it's nice to get a little bit of intellectual stimulation and to meet all you guys. I want to talk about the magnetic structure of manganese germanium in particular, and this is work which has been done by my group here in Oxford, especially Jean-Louis So, who's a PhD student, and it formed part of his PhD work, in collaboration with Fernando de Joan, who was a theoretician who was visiting Oxford for a while and is based in the Basque Country in Spain, and Navid Qureshi, who is an instrument scientist at the Institut Langevin Neutron Scattering Center in Grenoble, and he was really very, very central to the analysis of the data. And Wang and Guo from Shanghai Tech, who made the important samples which we used for these measurements. And the work is published in this paper a few months ago at the bottom here. So I want to describe our experiment to determine uniquely the magnetic structure of manganese-3 germanium. And at one level, this is rather trivial because the result of our experiment is shown in the bottom right-hand side there. That is the magnetic structure. You've already seen it a few times in the previous two talks. So if that was all there was to it, then I guess we could just go for an early lunch. But actually determining these magnetic structures is non-trivial, especially when they're collinear, non-collinear like this one is. And the technique that we used to do the determination and to find a unique structure is also not particularly well known. It's called spherical neutron polarimetry. So I really want to describe some of the details of how we were able to get a unique solution for this magnetic structure, and what problems that one has to encounter and overcome to do that. And I want to also say something about this magnetic structure and what its significance is with regard to the understanding of the anomalous transport properties of this family of materials. So I don't think I really need to introduce to this audience the motivation for studying the material. As you've already seen, back in 2016, these two papers at the bottom here, these two groups simultaneously showed that there was an anomalous Hall effect at room temperature, and that if the magnetic field is in plane, then the anomalous Hall effect is extremely large. And moreover, it's switchable in these very, very small fields. So it's a very interesting material, both from an intellectual point of view and also potentially from an applications technological point of view. And this is my view of the crystal structure. You've already seen some other visualizations. Key things are that it contains these trimers of manganese, which form layers together with germanium, which fits in the space between these layers. And if one looks down the structure, down the c-axis, then you can see that you have these Kagome or Kagome-ish layers made out of either blue manganese spins, which are up here at 3/4 in the unit cell, or the red ones, which are at 1/4 height in the unit cell. And importantly, there is a center of inversion symmetry halfway along the c-axis in the unit cell at positions like 0, 0, 1/2. And the significance of that is that it means that if the magnetic structure breaks time reversal symmetry, crystal structure has inversion symmetry, then we have the requirements for the system to have Weyl nodes where non-degenerate bands cross in a non-trivial way and produce very strong Berry curvature, which, as you've heard from the previous two speakers, is likely to be one of the reasons why this has such anomalous transport properties. And magnetic order, of course, has been known for a long time in manganese-3 germanium. On a microscopic level, the first experiments using neutron diffraction to study the pattern of magnetic order started in 1965, and there were further experiments in the 1970s and in the 1980s. And the outcome of these experiments is that it was established by using powder neutron diffraction, actually, that the propagation vector is Q equals 0, which means that the magnetic structure has the same periodicity as the crystal structure. It was established that the spins lie in the AB plane, and that the magnetic structure is a 120-degree structure, and the ordered moment is roughly 2.5 Bohr magnetons per manganese. And in addition, it was shown that the spins on sites which are related by inversion symmetry are parallel. So in this diagram on the right-hand side, which is one of the possible spin structures, in fact, it's not the correct one, you can see that the spins, the red spin and the blue spins on the opposite side of this hexagon are always parallel to one another. So this much was known, but even constrained by these things, in fact, there are several different possible structures that satisfy these constraints. One additional thing which was not obtained by neutron diffraction, but which was known about for many years, is this weak ferromagnetism that we've heard about, which depending exactly on the sample is around about 0.006 Bohr magnetons per manganese. This, of course, one can determine from magnetization measurements. And because there are several different magnetic structures which satisfy these constraints, our experiment was really, our objective was to try to determine which of these is the correct one. For these experiments, of course, you need single crystals to get a determination. And up till now, I think the vast majority of single crystals have been grown by the from a melt by either Tchaikovsky or Bridgman methods. And our crystals instead were grown by a flux method using cadmium flux. And at some point, it would be interesting to understand the difference between crystals grown this way and crystals grown using the standard melt process methods. But from a flux, you're growing at a lower temperature and in somewhat more controlled conditions, you get very beautiful crystallographically perfect crystals which grow as needles, as you can see in this photograph. The long axis is the C axis, and then you can see this facet, which is one of the A or the B faces of the hexagonal crystal structure. And you can see from this laboratory X-ray diffraction data on the right-hand side here that the crystallographically, the crystal is very high quality in terms of its very, very sharp peaks, very narrow mosaic. And the lower two panels here represent simulations which show that you're getting the correct structure here. And measuring the magnetization at low magnetic fields as a function of temperature, this is magnetization curve. As an aside, we have a rather old squid, and we always tell our students never to exceed 375 Kelvin, because on a few occasions when we have done that in the recent past, it's burnt out some of the power cards of the squid. But unfortunately, that means that for this particular sample, the student who is measuring stopped at this point here. And if he'd gone 2 more points, then we'd have actually gone through the nail transition. So anyway, we infer from this that the nail transition is 375 Kelvin, plus or minus, or rather plus a couple of Kelvin, which is entirely consistent with previous much better data obtained by other groups, for example, this group here. And you can see the curve very much follows the same shape of curve measured previously. And if you convert this number into mu-Bs per manganese, then it agrees pretty well with values that have been reported previously. We also have data of magnetization versus field, and this shows, as you've seen before, this very, very rapid switch of this ferromagnetic signal. This is a weak ferromagnetic signal, switches very, very rapidly with a coercive field of less than 100 Oersteds from one direction to the other direction. And this is consistent with other previous measurements made by different groups. Here I'm showing the work of Kihara. In fact, the coercive field that we have here is quite a lot smaller than the coercive field here. So clearly this is something which is somewhat sample dependent. So let me say something a little bit about the special technique used to solve the magnetic structure in our experiments. In conventional neutron polarization analysis experiments, what you do is you have a polarized beam of neutrons, and then you measure the scattered polarization in the same direction as the instant polarization. So you can only measure scattering of neutrons from, say, up to up, or up to down, down to up, or down to down. You can only measure along one axis, and this is called uniaxial polarization analysis. And this tells you a lot more than using unpolarized neutrons, but it doesn't tell you everything, because what it can't do is it can't detect processes where the neutron scatters and, for example, rotates the spin by 90 degrees. You wouldn't be able to tell the difference between that, for example, and an unpolarized scattered beam. So to enable one to measure those full set of processes, this technique of zero field spherical neutron polarimetry was invented. And this works by putting the sample in a zero field chamber, and it's maintained at zero field by using superconducting shields on the outside. And then you have a polarized instant beam whose polarization can be turned into an arbitrary instant direction, but which is usually placed along one of 3 orthogonal directions defined by these axes here. So then we have an instant polarization P alpha along one of these 3 directions. The neutrons scatter from the sample, and then their final polarization is analyzed along another direction, which is one of these 3 directions here. And that's measured in a detector which is out here somewhere. So basically, we can measure all possible scattering processes, all possible polarization changes of the neutrons as they scatter. And so the measured quantity is, in fact, the polarization of the neutron beam which is scattered from the sample. And that is, as expressed here, it's the difference between the intensity measured with spins along the beta direction and the minus beta direction, divided by the sum of those 2 intensities. And this is all for a given instant polarization direction alpha. And so you can see that because there are 3 different orthogonal directions alpha and 3 different orthogonal directions beta, you can assemble all these results into a matrix which is called a polarization matrix. This is the basic measurement of this technique. this polarization matrix. And then just for those who are not so familiar with neutron scattering, and I want to know why one wants to use this technique, there are a number of advantages over conventional neutron diffraction. One is, as I've just said, you can measure these off-diagonal terms in the polarization matrix, P alpha beta, where alpha is not equal to beta. And it turns out that these terms here make it much easier to distinguish between a non-collinear magnetic structure from a set of equivalent domains of a collinear structure, which in many experiments will give you exactly the same intensities, Bragg peak intensities. In addition, it's actually often easier to measure polarization more accurately than to measure the integrated intensities of a Bragg peak, which is what you do in a conventional experiment. And that's because you don't have to worry about scanning over peaks, so moving detectors around, and you don't have to worry about the mosaic of the peak. You just sit at the maximum of the peak and measure ratios of intensities. And for the same reason, when you measure polarization, it doesn't depend upon the magnetic form factor or indeed upon the any absorption in the sample, because again, they just cancel out when you measure these intensity ratios. So these three things make measuring polarization more easy, or if you like, more accurate than measuring integrated intensity and solving crystal structures that way. But then there are also disadvantages, and one of these is that if the magnetic structure has got a propagation which is not zero, then you cannot determine the size of the ordered moment. In fact, this is not a problem for manganese-3 germanium because the propagation vector is zero, and so you can determine the size of the ordered moment from the interference between nuclear scattering and magnetic scattering. So we were able to measure the ordered moment size in manganese-3 germanium, and it was consistent with values that have been reported previously. The second disadvantage I wanted to highlight was that the scattering, because it takes place in zero field, there is a problem if the magnetic structure has a ferromagnetic component, as does manganese-3 germanium, because any internal magnetic field, or indeed any field inside the zero field chamber, will cause the neutrons to start to precess around that field and will cause depolarization. So this is potentially a very severe problem for manganese-3 germanium. And I just want to say how we can mitigate that problem and estimate roughly what the size of that issue is. So the polarization of the neutron spin in an internal magnetic field B, which in our case is due to this weak ferromagnetism of roughly 0.006 4 magnetons per manganese, this causes the neutrons to precess through some angle which is proportional to three things. It's proportional to that internal magnetic field. It's also proportional to the path length of the neutron through the sample, and it's also proportional to the wavelength of the neutron. The longer the wavelength of the neutron, the slower the neutron, so the more the spins will precess around as they traverse the sample. And if you crunch the numbers, so in our experiment, we had a neutron wavelength of 0.85 angstroms, and we had a path length with a very small crystal, so the path lengths were of the order of 0.5 millimeter. If you crunch the numbers, you find that the spin precession angle, or if you like, the depolarization of the neutron beam is roughly 7 degrees within the sample. Now this is acceptable. It doesn't make very much difference to the calculations of the neutron polarization. So this we can live with. But I'd like to emphasize that we achieved this small value by having a rather small path length and a rather short neutron wavelength. If you use a more conventional neutron wavelength, which is about 2 angstroms or double this, and you had a crystal which was bigger, say twice as big, then all of a sudden you're getting depolarization angles of around 30 degrees or even more, depending upon the size of your sample. And so this depolarization could then be a major issue that you have to worry about and that could affect your results. But I'm happy to say that in our experiments, the mitigation that we did was sufficient to make this negligible. So, what do the results look like? So I explained that what we measure in our experiments are these 9 polarization elements of the polarization matrix. And in the first experiment that we performed on the sample, we aligned the sample with the B-axis vertical, so that the C-axis, or the long axis of the needle, was horizontal. And that gives you access to Bragg reflections of the form H0L. And in this diagram here, I'm showing on the horizontal axis a series of magnetic Bragg reflections, which we measured in the experiment. And in each of these panels, there are 9 different measurements. That's the points. And these are the different elements of the polarization matrix, the 9 elements of the polarization matrix for that particular Bragg reflection. And the pink lines are a calculation from a model, which I'll explain in a minute. So this is how we're going to represent the experimental results. So what can we say about the possible magnetic structures? We can see from experiment that the phase transition into the magnetic order is continuous, or second order. And so according to Landau's theory of phase transitions, that means that the possible magnetic structures should be analogous to the basis vectors of the irreducible representations of point group. And as this is a K=0 magnetic structure, we're just looking at the point group of manganese 3 germanium, which is D6H. So this constrains the number of possible magnetic structures. In addition to that, we have the constraints I mentioned earlier about the spins in inversion related sites being parallel and the spins lying in the plane. And this knocks out quite a few irreducible representations. And eventually we end up with just 4 different irreducible representations. We have 2 one-dimensional representations at the top here, B1G and B2G. And you can see that these are the 2 magnetic structures associated with those as basis vectors of those irreducible representations. And then on the bottom row, we have a 2-dimensional irreducible representation, E1G. So these are two possible orthogonal basis vectors for that irreducible representation. And then the 4th possibility is a simple in-plane ferromagnet, which again will have 2 basis vectors with the ferromagnetic moments along either X or Y. That also transforms like E1G. So these are the possible magnetic structures. The question is, which of them is correct? One thing I would like to say, just to give a bit more insight into these structures. So one way you can classify them is according to the vector spin chirality, which is calculated by looking at the sum of the cross products of the spin vectors on adjacent sites. So if you do that sum, you find that the spin chirality of the top 2 magnetic structures is positive. So it's in, if you like, in the direction coming out of the screen. And the vector chirality of the bottom 2 structures is negative. And the thing that controls the vector chirality actually is the Zaleschinski-Marie interaction. The Heisenberg interaction is the dominant one. That gives you the 120-degree structure. But the DM interaction decides whether adjacent spins like this, say, rotate clockwise as you go from the top spin to the spin on the bottom right, or for example here they go anti-clockwise, and that's what this vector spin chirality represents. And then another thing that you can another way you can distinguish these structures, if you look at the top 2 structures, you can see that the top spin, the top vertex of the triangle, is pointing horizontal in the B2G structure and is pointing vertical in the B1G structure. If you just rigidly rotate all these spins from the B1G structure positive, so clockwise, then you get the B2G structure. So in fact, it's the orientation of these spins which controls the difference between these structures, and it's the same with the E1G, the 2 E1G structures. Okay, so back to the experiment, and we can now assess the different structures that the different possible structures against the data. So the pink, as I said, the pink bars represent a calculation of the polarization elements for each of these reflections, and the dots represent the data points. So you can see, for example, the B1G structure, which is just looking at one plane here, just looks like this. You can see that this is a very poor fit. And the B2G structure, which has this sort of kind of spinning appearance, also is a very poor fit to the data. So these 2 spin structures are not correct. We now look at the E1G structure. It's got these 2 components which I'm labeling AX and AY. In fact, both of these give a very good description of the data. You can see very good agreements between the experiment and the theoretically calculated polarization matrix elements. And in fact, from this, so from both quantitatively and qualitatively, you cannot distinguish between these two structures based on this data. So it's got to be one of these two. How do we distinguish them? Well, what we can do, and what we did, was we now turned the crystal through 90 degrees so that the c-axis was vertical. This gives you access to the HK0 plane of reflections, and repeated the experiment. And now you can see that for the AX component of the E1G reducible representation, we get poor agreement. We have these data points down here which are not, which don't fit the calculation. Whereas for the AY component, we again get very, very good agreement. So you can see that we've unambiguously shown that this structure here, the AY structure, is the correct structure.
Andrew, can I ask, do you do any field training of the sample? I know you do it in this Meissner shield in a very low field environment. Is it always just the spontaneous moment that it has at room temperature, or have you prepared the sample in some way?
Good point. Yes, I should have said that. We did actually train the sample in the sense that we applied a field at room temperature, a field large enough to produce a significant, well, it doesn't need to be very large to polarize the ferromagnetic moment. So I think it was around a Tesla. We put the sample, and then we put it into the zero field chamber. I'm not sure it would make that much difference because when we performed the second experiment, we had to take the crystal out of the chamber, warm it up. We then didn't apply any field. We didn't train it again. Just put it back in again. And we didn't really see any evidence that there was any changes in those reflections, which are common to the two orientations. So I'm not sure it's actually necessary to train it, but for the record, we did train it. In fact, the reason why we did apply the field and sort of fully polarized was we thought it was an advantage to have an imbalance of domains, and in fact that probably does turn out to be important for distinguishing the two structures. So yes, so the central result of this study is really the fact that we've established that this is the solution for manganese-3 germanium. So I want to say something about this solution and sort of interpret it a little bit. So the first thing to say is that this pair of solutions, which I'm labeling AX and AY, and the ferromagnetic moment, or ferromagnetic magnetization, which I'm calling M, these both have the same symmetry, so they can couple. They're allowed to couple, providing there's an interaction which couples them together. And in fact, there is an interaction which allows them to couple together, and that is the orthorhombic anisotropy. So on this diagram on the right here, if you're sitting on one of the manganese spins and you look around you, if you look in the horizontal direction, you see two germanium spins along a line, on the horizontal line, but you don't see those two along the vertical lines. The next nearest neighbor spins are in fact manganese, and the next germanium is further away. So locally, the anisotropy is orthorhombic-like. So there'll be an easy direction which is either horizontal or vertical in the plane here. And in fact, if you go through the symmetry analysis, and we do this in our paper, what you find is that the thing that couples together the 120 degree structure and the weak ferromagnetism is in fact this orthorhombic symmetry. And what that means is that you can interconvert between the AX and the Y components of this symmetry by applying a magnetic field and then just rotating the field around. You wouldn't be able to, I should say, you wouldn't be able to do that were it not for this orthorhombic anisotropy. If there were no orthorhombic anisotropy, there would be no coupling, there'd be no weak ferromagnetism, and there'd be no coupling to an external magnetic field. So that's actually crucial to the formation of this weak ferromagnetism. And in fact, the size of the weak ferromagnetism is just related to the difference in the anisotropy horizontally and vertically, or if you like, perpendicular to the vertex of the triangle and parallel to the direction from the center to the vertex and perpendicular to that direction. The difference between the anisotropy in those two directions is directly related to the size of the magnetization, the weak ferromagnetization that you see. And in fact, the orthorhombic anisotropies, it does not lift the degeneracy between these two structures. These two have exactly the same energy, even with orthorhombic anisotropy. What lists the degeneracy between these structures is actually the 6th order, the hexagonal anisotropy on the manganese sites. So that's what's important for selecting the AY structure over the AX structure. Does all this matter that we have gone through this quite excruciating process of determining which of these structures is correct? Well, the answer is it in fact does matter, and one can illustrate this just by looking at the calculations, for example, in this paper by Kubler and Felser. It's an early paper from 2014, before the key measurements had been made, and they calculated the Hall conductivity, the anomalous Hall conductivity in a number of different orientations for a number of different spin structures. It doesn't matter what these spin structures are, but they're just different possible spin structures. And you can see that in some cases, symmetry actually forbids there being an anomalous Hall conductivity component. In some cases allowed, in some cases very large, in other cases very small, and it changes sign and so on. So in fact, the different magnetic structures have got different symmetries. This will then affect the band structure, push around the Weyl points, which will change the Berry curvature, which will therefore affect the anomalous Hall conductivity. So in fact, it really does matter which of these magnetic structures is the right one if you want to get an understanding of the anomalous transport. And the second point I want to make is a bit tricky, but we found 8 calculations in the literature of the magnetic structure by ab initio methods. Density functional theory is incredibly powerful technique for calculating not just band structures, but also for calculating magnetic ground states and exchange interactions and so on. But it still has a non-negligible resolution of a few milli-electron volts, and so it's not always easy to get exactly the right ground state if you include magnetism. So you can see that in this case, although most calculations did in fact get the observed ground states, not all of them did. So being an experimentalist, my view is that there is still no substitute for actually going ahead and doing the experiment and checking it out experimentally. Okay, so I'm going to conclude. Central result is that we have an unambiguous solution for the ground state magnetic structure, and it turns out that the existence of this weak ferromagnetism is an inevitable consequence of the symmetry of the magnetic structure and the orthorhombic anisotropy. At one stage, people weren't sure whether the weak ferromagnetism was in fact intrinsic to the manganese-3 germanium phase, or whether it was some sort of impurity or due to defects in the structure. But I think these experiments and the symmetry analysis show that this is in fact intrinsic to the material, and it's an inevitable consequence of the particular magnetic structure that forms. And as I said just now, the degeneracy of the 2 components of the E1G representation is lifted by the 6th order anisotropy, and that's the thing which decides which of those 2 is the ultimate ground state. So as I said at the beginning, this work was published a few months ago. In fact, just a few weeks ago, the group of Colin Broholm published a paper on the magnetic structure and dynamics, which I think Colin will probably talk about a bit later today. They have some complementary experiments which actually determined the same magnetic structure by different methods. So I'll stop there and I'll thank you very much.
Thank you so much for this. I'm a theorist, but I agree that there is no substitute for experiments. So the talk's open for questions and comments. Feel free, shoot away.
I have a question.
Please.
Oh.
Can you tell us something about any counting C-axis orientation of spins or not?
Well, we are sensitive to that in the sense that if there was any canting, then these experimental results for the polarization matrix would give disagreement with the calculated spin structure. So to the extent that the agreement is pretty good, we don't see any canting to within the precision of the data. However, I can't at this point in real time tell you exactly what that would correspond to in terms of an actual real angle. But I think it means it would be rather small if it did exist.
If I understand correctly, you can explain ferromagnetism just with in-plane spins.
That's correct.
Okay.
That is exactly correct.
So I have a question and a bullet comment. You have a slide comparing these two states and saying that if you rotate the field, actually you can go from one to the other. And my understanding is that then the orientation of magnetic field, if you use the magnetic field to train the state and you do it, basically you can go from one to the other. And what I can say is that we measured Hall effect, anomalous Hall effect, for both orientations of magnetic field. And then the anomalous Hall effect is within experimental, uncertainty is the same. Because there is one important detail. If you want to measure a Hall effect, you need also to rotate your electrodes. And this is what we did with these triangular samples. So, and basically, if you have the configuration at the left and the configuration at the right, and you have electrodes also following the direction of magnetic field, the anomalous Hall effect is basically the same. So you are right that in general, anomalous Hall effect does depend on orientation of spins, but at least for this particular case, I think the difference is small.
Well, that's an interesting point. So it would be very interesting to do the calculation of the Berry curvature for these two magnetic structures here to see whether they in fact give you identical or near identical values for the anomalous Hall effect. I don't know whether any of the theoreticians have done precisely that calculation, but interesting to just run through to see what's consistent with your observations.
I did a calculation before, they are very close, but not exactly the same.
Okay, so that's consistent, very, very close, consistent with Herman's experiment. Then that's nice.
So, Andrew, I had a question about the, sorry. I had a question about the crystals. So you mentioned that you grew the crystals out of flux and that historically people had used sort of crystal pulling methods. And you also indicated that you saw different coercivities. Do you have any indication with the flux-grown samples that the vacancy concentrations are different? I mean, you have different triple Rs compared to the other crystal growing methods?
Yeah, so that's a question. So I'm asking the question, but when you're a neutron scatterer, you have to apply for beam time, and we did this experiment to magnetic order, and then we applied for beam time to solve the crystal structure and to determine to what extent there is an manganese and whether there's a degree of site mixing sites. And unfortunately, the COVID thing and they beam time. So the whole time scale of the experiments has been strung out. So we're still waiting to do the experiment to figure precisely what our crystal is. There is any different from what's been reported in the melt crystals. So I'll know the honest answer to the question later. I mean, one of the reasons why we thought flux was because flux, of course, grows at a lower temperature to melt. So you cool very slowly. You're sort of in equilibrium, more in equilibrium. Now that can go the way. That can either give you stoichiometric samples or less stoichiometric samples. But we thought it might give us a different, a possibility of a different stoichiometry. I think we'll have to let you know when we've got the data as to whether these crystals are in fact compositionally more stoichiometric or stoichiometric than what other people are reporting. I guess the fact that the coercive quite small kind of suggests there's fewer defects, but this needs to be confirmed.
So Andrew, I had a question. Sorry, go ahead. Who is this?
Hey Andrew, that was a beautiful talk, very impressive. And I had maybe two questions. One is it possible to constrain the magnitude of the in-plane ferromagnetic moment from these data? And the other question has to do with the image that's on the screen now. And so to understand what you're saying is that the image on the right shows the structure that spontaneously forms in the material, so it must have the lowest energy state, but a small field you believe can actually drive it into the somewhat higher energy state, which is on the left.
Yes, but I think if you took off the field, it would probably go back to the one on the right. Your first question was, can you relate the direction of the weak ferromagnetism to this magnetic structure? And the answer to that is yes. Actually, if I can just go to another. So this formula here is actually the form of the orthorhombic anisotropy in this material. So there are two dimensions in which you can resolve the anisotropy, which are called here U and V, and of course locally these are 180 apart on each vertex. So this is the sort of conventional way of writing the single ion anisotropy. And you can write this, you can transform this into the basis of the magnetic order parameters, which are S prime, A and M, if you like, where A and M are the two that we're concerned with here. And this last term on the right-hand side, this is the coupling term between the A order parameter and the weak ferromagnetism. So you can see that actually the first thing you can see is that this depends on the relative directions of A and M, but doesn't depend on any absolute direction. And it also depends on the difference, I mentioned this, on the difference between the anisotropy constants, sort of horizontally and vertically, if you like, in the U and the V directions. So if there was no anisotropy, you wouldn't get this coupling. And from this term here, if I can just flick back, picture this one, what this tells us physically is that if you have the spin structure on the right here, the direction of the ferromagnetic moment would be vertical. It would either be vertical, it would either be up or it would be down, but vertical direction. And whether up or down depends upon whether K1 is greater than or less than K2. Depends upon whether the anisotropy is easy axis. It's the easy axis in the horizontal direction or the vertical direction. So that's how we can determine the direction of the weak moment relative to this magnetic structure.
But is there evidence in the diffraction data itself for the presence of that ferromagnetic component? In principle, it should give rise to an effect in the polarimetry too.
I think no, it's
too small.
It's too small. I mean, it's 0.006 mu Bs, and that's just too small to have any effect on the diffraction. Given that as you know, the intensity goes as a square of the moment, so it really has a negligible effect.
Okay. Thank you.
Thank you all, and thank you again. Any other questions, comments before we sort of break for breaks or stretch legs or whatever? Yeah.
So I was going to ask a similar question to Colin's about the orthorhombic anisotropy, but more specifically now I've heard that about the sixth order term that's lifting the degeneracy between these two. So orthorhombic anisotropy I can picture quite easily like a strain field stretching my triangle or providing a single line axis to this. Is there a picture, a simple cartoon picture of the sixth order term that lifts the degeneracy between them?
Well, if you think about this in terms of single ion anisotropy, then it's all to do with the local bonding. So
okay.
So the germanium atoms, if you look at that picture on the right hand side, the germanium atoms are the closest and give rise to an orthorhombic anisotropy just because of bonding horizontally and vertically. But if you go further away, then you'll find that there will be some six-fold patterns of atoms surrounding, so nearest
okay,
atoms.
so it really is just that next nearest neighbor
pattern,
not a distortion of the triangle. Okay.
There's no evidence for a distortion of the triangle.
May I confirm? I think you had this discussion earlier, but with polarimetry in zero field, let's say you don't play with the domain of your sample and just cool it down and you do the measurement, do you have differences for AX and AY in a purely multi-domain state?
So it took the sum of the magnetic ordering temperature and then took off the field and then just cooled it so that you had a multi-domain sample. I think you'd have multiple domains of AY, so just the right-hand structure, and some of those domains would, if you like, point upwards, and some of those domains would point downwards. And then, of course, they'd point along the equivalent 120-degree direction. So you'd have actually,
what I mean
you'd have
is that,
6 possible domains.
Yeah, what I mean is that just by itself, if you take the calculated polarimetry, all the polarization matrices for every Bragg peak, assuming AY with 6 domains, and you compare it to AX with 6 domains, and all the 6 domains are equiparable, those two diffraction, like those two polarimetry pattern will be different?
They wouldn't. If you had equally populated domains, they would be the same. And it's the fact that we, in fact, we have an outer population in our sample. We did apply a field before cooling.
So you do rely
that's what gives us a sense to.
Yeah. So you do rely on the applied field to be successful in doing this well, because you apply it at 300 Kelvin and then you release it and you cool it down and you hope that basically the domain is do you have measurement where you can compare the polarization matrix for a sample that did not apply the field and one that has been applying a field, so you can see the difference in the domain selection?
As I say, in practice, we did field and then cooled. We got an imbalance of the domain. And then for the second experiment, which actually was the one where we could distinguish AX, why we did the field. But of course, we did the sample above, and so it probably maintained an imbalance of domains from the first experiment. So in both experiments, we had an imbalance of domains, and that's how we could distinguish the two structures.
May I ask what kind of volume fraction you get from the refinement of the domains?
Oh, okay. So this is written in the paper. I don't remember exactly, but it's something like 60-30, 60-30-10 or something like that.
Okay.
We refined each. There was a non-negligible population of each domain, but it was quite significantly different for different domains.
I see. Thank you.
Well, thank you so much. Let's take a break. My clock here in US Central is 17 minutes past 12, and we'll reconvene at 12:40. So whatever hour, 40 minutes after whatever hour you find yourself, wherever you are in the world. And I'd like to thank the first 3 speakers for these exciting talks, and we'll return with Cristia Baptista from University of Tennessee in Oak Ridge.
Thank you.
Okay, thank you, Ule and Ross and the rest. Oops. Can you hear me?
Yeah, sorry, I screwed up. I muted you instead of me.
No problem at all. Okay, so thank you, Ule and Ross and the rest of the organizers for allowing me to be part of this very interesting meeting. Today I will talk about real space-vary curvature in itinerant electron systems with spin-orbit coupling. This is work that we did in collaboration with Shenxun Zhang, who is a postdoc in my group, Hao Zhang, that is a student, Hiro Ishizuka is an assistant professor at the University of Tokyo, and Gabor Halash is a staff member of Oak Ridge National Laboratory. The work is published in this reference that you can find below. So the presentation is basically about this work, and you can find more details there if you need. So the outline of the presentation is very simple. I will start with a very brief introduction to intrinsic anomalous Hall effect, and then I will focus on something that actually was mentioned and discussed in some of the previous talks, that is this idea of real space-vary curvature associated with a geometric property of the underlying magnetic ordering. But what I want to do in this talk is to extend that notion, right, of non-coplanarity or scalar spin chirality to the case in which there is spin-orbit coupling present, which is indeed the case of interest, of manganese-3 tin. And let me say that this work actually was motivated by a question that came from Satoru Nakasushi, right after he found this material, right? So I will mention that later. So in any case, so as you know, this story starts, with Edwin Hall in 1879. He reported, what we nowadays know as the Hall effect. And in his own words, he said that when a current conductor is placed in a magnetic field, the Lorentz force presses its electrons against one side of the conductor. And as a consequence, you get an off-diagonal component of the resistivity tensor that, nowadays we know as the Hall resistivity, to be proportional to the external magnetic field. And the proportionality constant is this Hall coefficient that, depends on a very simple property of the materials, which is the sign and the concentration of the carriers. Now, what is not so commonly known is that 2 years later, the same Hall, Edwin Hall, measured the Hall effect in ferromagnetic materials, and he found that they can have a much higher Hall effect, right, due to an anomalous contribution produced by the magnetization of these ferromagnetic metals. And actually the coefficient that, the proportionality coefficient between the magnetization and the Hall resistivity when the magnetic field, for instance, goes to 0, turns out to be strongly dependent on details of the material, right? So it took many, many years, to understand the different contributions to this so-called anomalous Hall effect. And one of the important contributions came from Robert Karplus and Lattinger in 1954, when they identified an intrinsic contribution to this anomalous Hall effect that basically has to do with the spin-orbit coupling. Once you have magnetized electrons, once the spin of the electrons is polarized, because you have a ferromagnet, through the spin orbital coupling, you have an orbital coupling, right, to this magnetization that will lead an orbital effect that will lead to an additional contribution to the Hall resistivity. The rest of the story, I think, is known by most of you. I mean, you're working on manganese 13, so I will not spend time on this. What I would like to basically focus on today is on the following thing. I mean, later on it was recognized that, even in ferromagnets, this anomalous Hall contribution is not really proportional to the magnetization. And, that makes you think that, there are other aspects of the material, other properties that, can produce anomalous Hall effect. And the first thing that one can ask is, if antiferromagnets, for instance, can also give an anomalous contribution to the Hall resistivity. And this is something that, by now we know the answer. We know that the answer is yes. And I will start by illustrating, the simple mechanism by which, one can produce anomalous Hall effect with antiferromagnetic ordering by using a very, very simple model, a toy model that, will allow me to dive inside the black box of, LDA calculations if you want to understand, what is the mechanism and, how this mechanism basically gets generalized, when you have spin-orbit coupling, like in the case of manganese 13. For this purpose, I will use this so-called SD model. It was introduced by Shubin and Bonsovsky in Russia in 1936. Unfortunately, Shubin perished under Stalin, during the Stalin purges. But then the model was rediscovered by Zener in 1951. It was a model that was introduced to describe the electron materials with partially filled shells. And what you have is two contributions. You have a contribution from, if you want, itinerant electrons that are described by this type banding term. For the moment, I will assume that the model is SU2 invariant. There is no spin-orbit coupling. And then there is also a Hund's coupling, if you want, between this, the spin of the itinerant electrons and localized moments. Actually, they don't really need to be localized, but here, for simplicity, we will assume that they are localized. And that they can be described by classical vectors, so we can use a semi-classical approach for describing the localized magnetic moments. Moreover, I mean, as you know, this model, for instance, has been extensively used to describe the manganites and other materials. And the other thing that I will do is I will take the large J limit, so the so-called double exchange limit that was introduced by Anderson and Hasegawa in the 50s, to basically reduce this model to an even simpler model, right? So if J is much bigger than T, then the spin of the conduction electrons will be forced to be parallel at low energies, to the local magnetic moments, which are the orange arrows in this plot. And consequently, we will end up with a spinless model at low energies, right? Once again, because the spin of the conduction electrons is no longer a degree of freedom once J is much larger than T. But the important thing to notice is that the renormalized hopping, the effective hopping of this spinless model, right, will be the original hopping, let's call it T21, between sites 1 and 2, times this overlap, because what happens now is that when the electron hops, preserving the spin orientation, now we have to project, right, this spinor, now that is pointing in the N1 direction, on the N2 bra, right? So the renormalization of the hopping is simply the inner product between the N2 ket and the N1 ket and the N2 bra. And the important thing to notice is that this not only renormalizes the magnitude of this hopping, right, but it introduces a phase, right? So now the hopping, the effective hopping for the spinless electron between two sides has a phase, and that phase can be computed. It's easy to, it's a simple exercise to do. That phase turns out to be a geometric property that is simply the half of the solid angle, right, spanned by these two vectors, N1 and N2, and a third vector that, is our choice of the quantization axis, right? So this phase, right, this phase of the effective hopping between 1 and 2 will depend on our choice of the direction of n. But if instead of focusing on the phase of only one bond, we focus on the circulation of the phase, so the sum of the three phases when the electron moves around this loop, what we will have is basically, as I said, the sum of the three phases or the argument of the product of these three matrix elements, or these three overlaps. And what you can see immediately is that now we will get the net solid angle spanned by these three vectors, because I have to add these three individual solid angles. So now we will get the net solid angle spanned by N1, N2, and N3 divided by 2. And of course, this result, unlike this one, is independent of our choice of the quantization axis. So the very phase that the electron picks up, the wave function of the electron picks up when it moves around the loop, is a geometric property, right, that is independent of our choice of the quantization axis. Moreover, I cannot distinguish that very phase from the Bohm-Aharonov phase that the same electron will pick up if it were moving in a plaquette that contains, some real magnetic flux, some, magnetic field going through this plaquette. And actually, we know that that Bohm-Aharonov phase is 2 pi, phi is the flux divided by phi naught. So now we have an equivalence between this non-coplanar magnetic ordering and an effective magnetic field that I think was mentioned before. And it turns out that when these three spins in the long wavelength limit, when these three moments are quasi-parallel to each other, this solid angle is simply the triple product of the three spins. So we end up with a very nice result, that is that these non-coplanar magnetic orderings produce an effective magnetic field that acts on the conduction electrons that is proportional to the so-called Skrimion density, or scalar chirality. Moreover, if you make this spin configuration or this local moment configuration time dependent, then you replace one space derivative by a time derivative, and you get also an effective electric field that is coupled to the conduction electrons. So in general, what we have here is an emergent compact U1 gauge field produced by these underlying magnetic moments when they interact with the conduction electrons. And what this clearly shows is that if you have any non-coplanar ordering like a Skrimion crystal, right, it will produce an effective field, right, and it will indeed produce an anomalous Hall effect through that effective field. And actually one can compute the number of Skrimions by integrating the Skrimion density, right? So what we can see here is that according to this formula that I showed here, each Skrimion will introduce a flux quantum. So basically the Skrimion density will tell us, what is the density of flux quanta, or the effective magnetic field. And something that is, I think it was already mentioned, this effective magnetic field can be as large as 10 to the 4 or 10 to the 5 Tesla, right? In ideal conditions, which is, astronomically high if we compare to the real magnetic fields that can be generated in the lab. Moreover, I mean, you can, you don't need to have Skrimions, you can have, an antiferromagnet like this one. This is work that we did with Ivar Martin, now he's in Argonne. in this 3/4 field triangular SD model, it turns out that, on a triangular lattice at 3/4 filling, because there is perfect nesting, right, in the Fermi surface, it's a perfect hexagon, you get triple Q ordering that in real space corresponds to a 4 sublattice ordering. So you have A, B, C, D sublattices, and the spins are pointing in the all-out directions of a regular tetrahedron, meaning that each triangle of this triangular lattice basically contains, spans a solid angle that is a quarter of the solid angle of the sphere, meaning that, you have a quarter of a flux quantum on every single triangle. And because of that, this magnetic ordering, actually gaps out completely this Fermi surface. These are the reconstructed bands. And in this particular case, not only you get anomalous Hall effect, right, out of this effective magnetic field produced by the non-coplanar ordering, you get quantum Hall effect, right? So you get a spontaneous Chern insulator. And this is interesting because, if you have a spontaneous Chern insulator, for instance, at ambient temperature, you have dissipationless currents, as edge modes, that will be even interesting for technological applications. So, we had many discussions with Satoru about this. And a few years later, he came back, with the results on manganese-13, and he told me, well, I found an antiferromagnet that, has a very large anomalous Hall effect. But, the bad news are that, the magnetic ordering is coplanar. So this really triggered, my interest in understanding, how does it work? How is that the previous picture that I just described, gets modified in the presence of spin-orbit coupling. And in order to understand, how spin-orbit coupling can modify this real space curvature, or this effective magnetic field produced by the antiferromagnetic ordering, the only thing that we need to do is to add the spin-orbit coupling in this model, in this toy model that I'm using to understand the physics. So the way the spin-orbit coupling enters, right, in the hopping, or in the Taiwan and Hamiltonian, is through these unitary matrices that appear in the hopping terms, these UKJ, they are Von variables. What they are telling us essentially is that, when the electron hops, instead of preserving the spin orientation, actually the spin rotates. And it rotates around an axis that depends on the particular crystal that we have. So it is constrained by symmetry considerations, and it rotates by an angle alpha, right? That is determined by the strength of the spin orbit coupling. So this is the important difference. Once we have spin orbit coupling, we have actually, in terms of in terms of gauge theories, what we have is really a static SU2 gauge field. Look at, these are Von variables, right? SU2 matrices that exist on bonds of this model, and that they are minimally coupled to the conduction electrons, right? So, an important thing to notice is that, this is a static SU2 gauge field because it depends on the position of the ions, and we are not considering any lattice fluctuations or motion. This field will be fixed, will be static. So now the important thing is that, because of what I just said, right? Because there is an additional rotation of the spin when the electron hops. Now, the effective hopping is not given by this overlap between the initial and the final state, but now I have to account for this rotation, right? So my initial state was Nj, the spinor Nj. Now I have to apply the rotation UKJ, right? And then take the overlap with the spinor associated with the NK, right? So now the very connection, or the phase of the effective hopping, is the matrix element of this matrix UKJ, okay? So that is the generalization. We have to account, so we have to compute this matrix element. There is a geometric answer that you can find in our paper. I told you before that the very phase, right, for a closed loop was basically the solid angle spanned by the three vectors. These three vectors, actually, when you have this spin orbit coupling, it turns out to be the solid angle is the area of a spherical triangle. When with the spin orbit coupling, it turns out to be the area of a nonagon, where we can discuss later if you want, what are the vectors that appear on that nonagon, right? It's a nonagon. The nonagon is a polygon of 9 vertices inscribed in the unit sphere. And what I will do, instead of discussing the geometric answer, I will discuss the algebraic answer. And for that, what we are going to do is we are going to exploit the fact that the very phase that the electron picks up when it moves around this loop is independent of the local reference frame that we use to describe the system, right? The local reference frame that we use for each site, right? For each spin. So we can apply a local SU2 rotation, right, to the reference frame of each of these three individual spins, right? These are these calligraphic U's, right? And once we do that, we have to also transform these SU2 gauge fields or these spin orbital fields in this way, right? You can see that, the very phase will be invariant under this transformation because for each U that acts on a ket, we have a U dagger that is acting on the transformation of this operator. So the very phase will be invariant under this transformation. And finally, we have to rotate also the local moments using the the SO3 matrices associated with these SU2 rotation matrices. We do this to preserve the form of the Hund's coupling, right? The Hund's coupling, we want it to be invariant under this transformation. So basically, I'm going to exploit this in order to remove the spin orbital coupling from two of the bonds, right? I will accumulate all the spin orbit coupling on this bond by performing one of these transformations. And you can easily find out, what is that local rotation of the three reference frames. Actually, you don't do anything on site J, but you perform a rotation on sites, an adequate rotation on sites K and L, right? You do the same thing with the local moments. And in that way, you can remove the spin orbital field from these two bonds. Now, the generalization of the notion of flux, the flux that in SU2, for U1 gauge theories, for SU2 gauge theories is what we call the Wilson loop operator. That is simply the product of the three U matrices on these consecutive bonds, right? So in particular, for this transformation that I'm doing here, this Wilson loop operator remains invariant, right? It is another SU2 matrix that has a rotation axis that I will call A, J, K, L, and a rotation angle that I will call alpha J, K, L, right? So now, because I removed the spin orbital coupling from these two bonds, now I accumulated the whole Wilson loop operator in one bond, right? And the advantage is that now I can use for these two bonds that do not have any spin orbital coupling, I can use the previous formula that I derived for the SU2 invariant case. And only for this bond, I will have to, modify the equation, right, for the phase. So remember, I get the very phase as the sum of three contributions, three phases, right? And for two of them, for this one and this one, I can use the previous equation that I derived. Remember, it was the solid angle spanned by these vectors now n prime, right, in the new reference frame, and the quantization axis that I will choose it along the direction of the Wilson loop rotation operator. For the last one, for this bond, right, I have to modify the formula, right? And actually the way it gets modified is that the solid angle now, the difference between the azimuthal angles gets shifted by alpha, JKL, this angle that appears here. And there is also an intrinsic contribution also coming from the Wilson loop operator of the SU2 gauge field or the spin orbital field. This, if you want, this Wilson loop operator in some sense measures the strength of this spin orbital field. Good, so having done this, now I can express my very phase as the sum of two contributions, right? The first term is once again the solid angle spanned by these three vectors divided by two. But I want to emphasize the prime here, right? These are the three vectors in the new reference frame, right? Where we have basically removed these spin orbital fields, plus another contribution, gamma hat, right? That is related to the strength of this Wilson loop operator, right? So it's non-zero only when this alpha JKL is non-zero. That means that if we had a situation in which we can gauge away completely the SU2 gauge field or the spin orbital field, meaning that this Wilson loop operator is the identity, right? So alpha JKL is zero. We will end up, this term will disappear, this contribution, and we will have simply that, the very phase is half of the solid angle spanned by these three vectors. But here is the important observation. it is half of the solid angle span by these three vectors only in the reference frame where we were able to gauge away this SU2 field, right? In other words, to be more explicit, let's consider a particular example that actually is relevant for manganese 3 tin. Let's assume that the three magnetic moments form a coplanar magnetic ordering, like a 120-degree magnetic ordering with the opposite chirality to the one that appears in manganese 3 tin, but that doesn't really matter for this example. And let's assume also that the spin orbital fields are pointing along these high symmetry directions. These are basically the rotation axis, right? So if we assume that the spin orbit coupling is weak, and we linearize, so basically we compute these rotation matrices to linear order in the rotation angle alpha, then we can see that what appears in the exponent of the Wilson loop operator basically is simply alpha times the sum of these three vectors, right? But the sum of these three vectors is 0, right? Because they are pointing along these symmetric directions. So that means that to first order in the spin orbit coupling, the Wilson loop operator is the identity, right? And then we can gauge away to first order in the spin orbit coupling this spin orbital field. But the important thing is that in the process of gauging away the spin orbital field, now we ended up with a non-coplanar magnetic configuration, right? So what was coplanar in the lab reference frame is non-coplanar in the new reference frame. Consequently, even this coplanar magnetic ordering with the spin orbital fields will produce a non-trivial Berry phase, a finite Berry curvature, right? Because this structure is non-coplanar, and actually the Berry phase is half of the solid angle spanned by these three vectors. That is what I was telling you here, right? So this is a very important observation. It is telling you that coplanarity is a non-covariant property. Once you have spin orbit coupling, you have to forget about the scalar spin chirality or the coplanarity as a property that defines the real space Berry curvature, because that is a non-covariant property. Good, so to understand this in the continuum limit, I gave you the equations in the continuum limit for the SU2 invariant case. What you have to do is, you have to rewrite the Hamiltonian now in the continuum limit, and notice what I was telling you before, that actually the way the spin orbital coupling enters in the Hamiltonian is through minimal coupling, where now we have a vector potential that is a 2 by 2 matrix, right? It's a SU2 vector potential. It has two indices, A that has to be contracted with the Pauli matrices, and then the usual time space index, right? 0, 1, 2, 3. That for the space index, here this will be, or if you want X, Y, Z. This corresponds to three directions in space. Remember that these are bond variables. And for the spin orbit coupling, the relativistic spin orbit coupling, this field is actually perpendicular to the bond direction, to the J direction, and it is also perpendicular to the direction of the local electric field. For the time component of this SU2 vector, SU2 gauge field, what we have is actually is determined by an external magnetic field. So if you include a Zeeman term in the Hamiltonian, the time component of the SU2 vector potential is proportional to the external magnetic field. So you can verify that if you construct the action associated with this Hamiltonian, this action is indeed invariant under a local rotation, and the rotation of the local reference frame that in particular can be dependent on the position, as I did before, but also on time, right? So if you transform the spin or the matter field in this way and the SU2 vector potential in this way, you can verify that this action remains invariant. So this is just to emphasize once again that adding spin orbit interaction, it corresponds to coupling our electrons, our spinor field, minimally to this SU2 vector potential. And you can find this in detail in this review of modern physics of Froelich and Studer. Anyway, so I will save you the derivation of this, but if you now derive the very phase that the electron picks up when it moves around an arbitrary loop that encloses an area SC. So C stands for the loop, right? And SC is the area enclosed by the loop. What you find out is that the generalization of this formula that I was describing before, the so-called scalar spin chirality, is now this expression that is the covariant right, a version of the scalar spin chirality. Now notice that here I don't have anymore a partial derivative. I have the partial derivative minus the contraction of the generators of the group SO3, the usual components of the orbital angular momentum, and the SU2 vector potential. So this accounts for what I was telling you before. You know, this expression has to be covariant, right? So this can be non-zero even if you have a coplanar order, right? And the other contribution is intrinsic, right? And what it is the projection of the strength of the SU2 gauge field, right, the mu, along the direction of the local moments. So if you want, this has to do with the Karplus and Latinger contribution, right? It's an intrinsic contribution that comes from the spin orbital coupling, while this is the generalization of the geometric contribution that I think was discussed also in previous talks. And it is because of this, right, that, you know, in manganese 3 with a coplanar magnetic ordering, you can have anomalous Hall effect because it's the combination of that coplanar magnetic ordering with a finite spin orbital field. In order to make the point that, you know, indeed, you know, this mechanism, you know, can account, you know, for what is observed in manganese 3, we kept using this toy model. Of course, you know, it's not realistic at all. We fixed the magnetic ordering, you know, basically the magnetic ordering that was discussed in the previous talk, right? And we use a symmetry analysis to determine what are the allowed directions of these spin orbital fields. Remember the rotation axis, you know, on each bond we have a spin orbital field that has a rotation axis, A, right? And symmetry constraints is constraining the possible orientations, right? Or the possible components, the non-zero components of this SU2 vector potential. So something interesting that, you know, one can see from this analysis that, you know, the direction of these vectors is perpendicular to the plane for these bonds that are connecting manganese sites on the same layer, and it's only, you know, and while it can have an in-plane and an out-of-plane component for the bonds that are connecting different layers, right? For these triangles that are connecting different layers, and actually it's the in-plane component, these red arrows, which are responsible for the generation of a non-zero Berry curvature on these triangles that are connecting different layers. Once you understand that, you know, you can have a non-zero real space Berry curvature, you can compute the momentum space Berry curvature and see, you know, what do you get. As you all know, you know, you get anomalous Hall effect, and you also get, you know, a distribution of Weyl points, which are drains and sources of Berry curvature. This is what I was trying to say before. The real space Berry curvature is localized on these triangles that connect different layers, different manganese layers. These are the Weyl points that we obtain with this really toy model or simple model, right? You know, interestingly enough, you know, the Weyl points tend to also appear also in the corners of the brilliant zone. And you know, if you put, you know, reasonable parameters, of course, you know, again, this is not very realistic, but, you know, if you put reasonable parameters and you put a spin orbit strength or coupling that is of the order of 10 to the minus 2, and then you plot the sigma yz as a function of the chemical potential, you get an order of magnitude, right, for the typical value of sigma yz that, you know, coincides, you know, with experimental observations of the order of 100. 1/1 centimeters, right? So this indicates that, you know, somehow, I mean, this simple-minded approach, you know, basically can in principle account for the intrinsic, you know, Hall effect that is observed in manganese 310. So to you know, conclude, you know, let me first say that in SU2 invariant systems, yes, the scalar spin chirality is what generates, you know, an effective magnetic field that couples to the conduction electrons and produces, you know, anomalous Hall effect. But in general, when spin orbit coupling is present, right, it really corresponds to an SU2 gauge field that is coupled to your conduction electrons. So non-coplanarity or coplanarity is no longer a covariant property. One has to generalize this scalar spin chirality, and actually this is the generalization, right? This second term. As I said, this is the intrinsic contribution coming from simply the coupling, what I explained before, you know, from Karplus and Latinger. And, you know, one question that you may ask is, why do we care? And I think, we care for many reasons. First of all, because collinear and coplanar antiferromagnetic orderings are actually more common than non-coplanar orderings. Because spin orbit coupling is always present and actually is strong in 4D, 5D, and F-electron materials. And finally, because the SU2 gauge field associated with the spin orbit coupling is a bond variable, meaning that it should be sensitive to pressure and strain, right? So in principle, we can, according to the usual mechanism of the scalar spin chirality, normally you need to use a magnetic field through the Zeeman coupling. You can control the scalar chirality. Now, because the spin orbit coupling contributes also to this Berry curvature, you can also use, a strain or pressure to control it. So thank you very much for your attention.
Thank you so much. Paper is open for questions, discussions, comments. I'll be happy to start. So I think this is very interesting work and very well presented. So if I understand it correctly, there's a very sort of complex interplay between, on the one hand, real space and reciprocal space, right? The yes. Magnetic structure, spin orbit coupling, give rise to a magnetic texture, a magnetic order, which gives rise to both a real space and a reciprocal space Berry curvature, because the Berry curvature in reciprocal space also depends on the magnetic order, right? Correct. So you can have combined reciprocal and real space Hall effects. I mean, from the reciprocal space Berry curvature and topological Hall effect that are very interdependent on one another. Is that correct?
Exactly, that is correct. The thing is that, knowing the real space distribution of the Berry curvature, which is what I was discussing here, so basically what I was discussing is how is that this real space Berry curvature is distributed, right? So you can compute the effective flux on each plaquette. The point is that, that alone does not determine the distribution of momentum space Berry curvature. Because, for instance, the magnitude of the hopping, something that I have skipped completely, right? So not the phase, here I focus on the phase, right, of these effective hoppings, for instance, but the magnitude can change, and different magnitudes of the hopping, right, with the same Berry curvature, with real space Berry curvature will give you different distribution of momentum space. Right. This is more like about understanding what is the origin in real space, of this effective flux, right? That leads to this momentum space Berry curvature. And the trick is that, essentially what I'm doing here is I'm projecting an SU2 gauge field that, intuitively is not easy to see, how it acts on the charge degrees of freedom. By taking this double exchange limit, I am projecting it into a U1 gauge field, right? So essentially you can see that in this projection, right? So yeah.
Thank you.
So I have a question, Ollie.
Yep.
Yeah, great talk, Christian. Thanks a lot. I mean, Ollie, I kind of asked in the same direction that I have, but maybe let me try to understand a little bit more the size of the contributions that come from. I mean, I know this depends probably on the strength of spin orbit coupling, but if you say you have also Berry, sources and sinks from wire cones, and you have this additional real space modulation, which I'm just thinking of this as being an effective magnetic field in real space, and you're doing a Fourier transform to get the K-space Berry curvature. Like, how do they compare in terms of their magnitude? Is this for realistic parameters relevant, or is the Weil contribution dominates, or are they comparable? I kind of didn't catch that point.
Okay, so right, what we did is to estimate the magnitude of the effect, because this is not a realistic model. We moved the chemical potential, right? We ran, we changed the chemical potential or the possible values, and then we computed the sigma xy, right? So using, sorry, not xy here is, sigma xy is 0 actually for manganese 13. So we computed the only sigma, the sigma for the only plane for which, so there is still a one mirror symmetry plane, vertical plane that survives here. So, it's only in that plane that you have anomalous Hall effect, as it was also explained in a previous talk. So what we did is, we computed directly sigma, in that plane, sigma yz with this model. And what we found is that, well, what I was saying here, right? That, you get the magnitude of the effect that you get is, the order of magnitude is correct, for a very small spin orbital coupling, right? What controls the spin orbital coupling is this alpha here, right? Now, we cannot do much more, right, with this because, this of course is I mean, a very simplified model, right, that we are using to understand, right, if one can get an anomalous Hall effect of this magnitude, putting a realistic, spin orbit coupling. Correct. Now, the position, so there are things that, I do not understand, like, why, these Weil points tend to appear at these corners. I mean, this seems to be a generic property, but in general, I don't expect, the position of the Weil points to be generic, right? Like, my guess is that, if you change, from one model to another one, they can move around simply because of what we were saying before, right? That has to do with the distribution of the momentum space curvature, which depends on variables that, are independent of the real space curvature, right? I don't know if that answers your question.
Yeah, maybe. I mean, can I follow up? Maybe I don't fully understand it yet. I mean, could I imagine like having the same effect in a band structure, which by itself would not have a Weil point? I mean, so all the momentum space curvature comes from the spin.
No,
structure.
I don't think so. Right.
Okay.
Yeah, I don't think you need necessarily to have Weil points in order to have
Right.
a anomalous Hall effect.
But even for your coplanar, I mean, even in a coplanar case, using the same mechanism you've described, it could work, right? You don't need additional Weil points.
No, right.
Okay, thanks, yeah.
Yeah.
Other questions, comments?
I would have another question, but maybe we can wait a bit more.
No, go ahead, Peter. All right.
So you also mentioned in the summary that collinear orders, it could also work for collinear order.
Yes.
Is it this? I mean, maybe it's not entirely obvious to me, but then collinear order would also be transformed into like a non-coplanar, non-collinear order using spin-orbit coupling that could work if the spin-orbit coupling fulfills certain properties, or would I have to?
Right. So collinear order, I mean, can give you I mean, one way of understanding that, collinear ordering can give you net flux is because, maybe, let me see. So because of this component, so two things, one is, even for collinear ordering, you can put, some spin orbital fields and verify that that you can gauge away, let's say, so the Wilson loop is identity, and see how the collinear ordering becomes non-coplanar. So you have a finite contribution, due to this part. But this part already tells you that you can have a finite flux due to collinear ordering, and maybe intuitively thinking of the following way: if you have 3 parallel spins, like a configuration that is locally ferromagnetic, right? The 3 spins are parallel, and the spin orbit coupling is along the direction of the parallel spins, right? So let's say the spins are along the z-axis, and you have a spin orbit coupling the z component of the spin to the orbital angular momentum, z component of the orbital angular momentum, you will immediately get a non-zero Berry curvature, right? So you get a finite phase, and that is actually the Karplus and Lattinger mechanism. Now you may tell me, well, that only works for ferromagnets, but actually the answer is no. Even if you have a collinear ferromagnet, antiferromagnet, right? You may have different kinds of triangles, right?
Right. Yeah.
And it's like this Haldane model, right? And you may have opposite flux on both inequidistant triangles, but that alone is enough to produce anomalous Hall effect. Yeah.
Right.
So yeah, it
Thanks.
works also for collinear.
Right.
So yeah, one comment is so I think one of the outcomes of this talk is we shouldn't think always that we need, even for the domain walls or things like that we need a non-coplanar ordering at the domain wall to have an additional contribution to the anomalous Hall effect. Right. So these are things to keep in mind. When you have spin orbit coupling, you don't need the non-coplanar ordering to have an anomalous Hall effect, even at the domain walls.
Well, thank you. So if you unshare,
Sure.
and Colin, we have the East Coast guys now coming in here. So Colin Broholm first. Can you hear me?
Yeah.
Okay. You want to go ahead and share?
Yeah, let's see. Okay. And does that show?
Yep, it does. Very good.
Excellent. So thank you for the organizers and all the participants. It's a really interesting meeting on interesting set of compounds. I decided to focus my talk on our work on manganese germanium. And I hope this will be a complement to the earlier talk by Andrew Boothroyd. This is also a neutron scattering experiment on manganese germanium. The paper was in FISRIP B, came out early in August. So this will be the outline of my talk. In section 1, I will talk about the antichiral magnetism and its field dependence. I think that this method of spherical polarimetry is really the gold standard for low field measurements of the ordered magnetic state for this kind of non-coplanar or non-collinear spin structure. We used a different method which allowed us to do experiments at high magnetic fields, and so I think we have complementary information regarding the impact of applying an in-plane field on the magnetic structure of manganese germanium. In the second part of my talk, I'm going to discuss magnetic excitations, also neutron experiments. Broadly speaking, we have at low energies Goldstone-like modes of excitation, and we've tried to understand and classify those excitations using with the help of our theoretical colleagues, Oleg Chernyshov, and they developed a field theory which was able to connect in the long wavelength limit a model spin Hamiltonian to our measurements with neutrons of the excitation gaps and the spin wave velocities. At high energy transfer, we see really a continuum of scattering. It seems that there's very heavy damping, or maybe electron hole pair continuum really eventually dominates the excitation spectrum. And I'll have some conclusions. Okay, so this is, as I said, recently published work in FISRIP B. I wanted to introduce you to the individuals who put a lot of work into this, actually, and I think both Yoshi Chen, Jonathan Godet, at least I know that they are on the call, maybe also others from our group. It was all really done under the auspices of Institute for Quantum Matter Energy Frontier Research Center. Guy Marcus was the person who early on did all of the experiments, actually, and then the analysis was a good part of the inelastic experiments, and then the analysis was conducted over some time following that. The materials and many of the ideas of doing these projects came from Satoru Nakatsuji, and he's been very actually involved in thinking about these results as well. And Oleg Chernyshov was guiding us in the theoretical analysis. So as Andrew mentioned, when we have a second order phase transition, that really constrains the kinds of magnetic structures that should be able to develop through that transition. And so as part of this project, we took it upon ourselves to examine whether the transition actually appears to be second order. And so we did these experiments. This is a specific heat measurement in this high temperature regime. And we find really a quite beautifully looking lambda-like anomaly that I think does look like a second order phase transition. It can be difficult to be quite, probably is not appropriate to be completely descriptive about this, because there are ways that one could have a weakly first order transition, but we think it looks really like a second order transition. From these data, we can also extract the change in entropy at this transition. And that's actually quite a small change in entropy of about, oh, that looks too small. Sorry, I should not have the percent sign. It's 4.7% or 0.047 times r log 2 s plus 1, where s, if we take s to be 5½ corresponding to really kind of a localized manganese spin. So it's significantly reduced compared to that localized spin limit. Not a surprise, since we're working with an itinerant magnet. And so perhaps a way to think about this is that a small part of the Fermi surface is being gapped at this transition. It still remains conducting below the transition. One could also think about the presence perhaps of short-range spin correlations above TC. But we haven't really been conducting experiments beyond these specific heat and diffraction experiments in this high temperature limit so far. We also looked at the temperature dependence of magnetic Bragg diffraction shown here on the right. And from this, since we're measuring then an order parameter squared, we can extract a order parameter critical exponent, which we find to be 0.21. For these kinds of transitions at such a high temperature, you can get pretty good measurements. It's quite easy to stabilize the temperature enough to get into the critical regime. And so here are shown the diffraction data that we collected very close to TC. And the critical exponent actually ends up being 0.21 with an error bar of 0.01. And this differs really from, this really differs from what one might have expected for either Heisenberg or XY 3D magnet with a collinear magnetic order. It's from an experimental perspective, my experience with this has been that usually when you get a small critical exponent, that's difficult to get by some sort of experimental error, or we should say by experimental challenges, but it's quite easy to get a critical exponent near the mean field critical exponent due to addition of diffuse scattering or due to distribution of critical temperatures in the sample. So we were quite interested to see this rather small value of the critical exponent beta. It turns out to be similar to the U1 cross Z2 universality class, which Kawamura has spoken a lot about in triangular lattice 2D antiferromagnets. This really will turn out to be, or really is, a three-dimensional ordered magnetic system. So it's only not quasi two-dimensional. But this kind of critical exponent has also been seen just phenomenologically and experimentally in a number of other stacked non-collinear magnets, and some of them are listed here. So I would say that so these are results about the character of the second order phase transition, but we do not have a real understanding of its universality class at this point. Okay, so then let me turn to the what we can say about the magnetic structure, so we have the experimental result really from magnetization measurements that there is a ferromagnetic moment in the system, and actually remarkably stable, it seems, in bulk single crystals around 7 millMeV per manganese. And we have the result of a second order phase transition, and that Q is equals to 0 for the ordered magnetic structure. And this actually only allows one IREP to be brought in, namely one which can accommodate the ferromagnetic component as well as the Q equals to 0 antiferromagnetic ordering. And this IREP is the one that Andrew Boothroyd was describing to us earlier in the day. And the way I'm discussing it here is in terms of two different components that can all be superimposed, and still you have this gamma 9, we call it gamma 9 IREP. And so on the left, I'm showing the anti-chiral antiferromagnetic state, and it has this angle theta chi, which is a variable, and I can dial that angle in at any value, and then we'll have part of the gamma 9 IREP. And also as part of the gamma 9 IREP is a ferromagnetic spin configuration, a collinear ferromagnetic spin configuration as shown here. And again, there's a degree of rotational freedom theta f that forms part of this IREP. And so we could say that determining the magnetic structure in zero or indeed an applied field really is a question of determining the values of these angles theta chi and theta f. But these are actually quite tricky to determine, as Andrew also pointed out, because in neutron diffraction, in a multi-domain state, those are not accessible. The diffraction pattern is not dependent at all on those angles. The other challenge really is that the magnetic and nuclear Bragg diffraction are superimposed in the system. So the Bragg peaks will both have nuclear and magnetic character to them. And that actually makes it a little tricky to separate actually those distinct contributions. And the method that we used, which is distinct from what Andrew was describing, is to use the polarized beam method, but in the presence of a magnetic field that can influence the spin configuration. But we're using the uniaxial polarized beam method, so that we are only having this limits what we can actually extract from the diffraction experiments. We're going to have the field at the sample position either vertical, that is perpendicular to the scattering plane, or oriented along the wave vector transfer direction. So let me first show you in a rather compact form the experimental data that comes out, and actually it also has the comparison between the experimental measurements of the observed structure factor and the calculated structure factor. And there's actually quite a lot of information in this plot, but it's not particularly accessible, but it shows you the kind of measurements that we did. So on the left is shown 0 Tesla measurements, and so both of these are low temperature measurements, and this is on the left is 0 Tesla, so that's in a multi-domain state. And so there we've collected vertical and horizontal field polarized diffraction data in 2 different reciprocal lattice planes, either HOL or HHL planes of this hexagonal structure. And on the right are corresponding measurements now conducted at 2 Tesla, again for the 2 different reciprocal lattice planes. And now we're distinguishing, let's say, up measurements with neutron spin is up when it comes in and up when it comes out, and also down. These are now being distinguished because we have a field at the sample position. So this is the set of data that we collect, and these are now in a conventional least square method are now being compared with models of the nuclear and magnetic structure, because since the nuclear structure comes on top of the nuclear and magnetic Bragg diffraction is at the same positions, we have to solve both of those at the same time. And then shown here are now the 2 Tesla data. So this is now with a field. I should say, sorry, let me step back one point, which is the 0 Tesla data basically confirms the presence of the gamma 9 structure, in the sense that we actually do see, and I'll return to that in a little bit, the evidence for ferromagnetic Bragg diffraction. Quite a surprise, which, as I'll mention. But now I'm going to then turn to the 2 Tesla measurements. So this is now in the presence of a magnetic field. And what's shown here on the left is the goodness of fit, so the chi-squared, as a function of these 2 angles that I indicated previously. So theta chi is the clockwise rotation, of the antichiral structure that I'm indicating in this direction. So this direction of rotation of each of the spins in their local frame. So this is theta chi, and theta f is the, again, clockwise rotation of the ferromagnetic component of the spin. And so this is, as it comes out, with diffraction data in those 2 different planes, and the white lines indicate the regions which we think are consistent with the diffraction data. And these other regions, including these red regions, would not be consistent with the diffraction data. And so shown then here in the spin structures are the antichiral component of the spin structure and the and the ferromagnetic component of the spin structure. And we'll be happy to see that this spin structure that's shown on the top is the same structure that Andrew Boothroyd was talking about, and was identifying in the zero field state, but now in the presence of a 2 Tesla field applied along the indicated direction. The error bar is quite large, as you can see, plus minus 45 degrees. It seems outrageously large, but that's what one can obtain with these kinds of uniaxial polarized diffraction data. The surprise here to us was that there's also this transverse ferromagnetic component. I'm going to return to that in a little bit. And we have, of course, would of course have 2 different possible orientations of that transverse component of magnetization. The other field direction would be that we have probed is for fields along a lattice direction, so along an A direction. And again, the ferromagnetic transverse component is found to be perpendicular to that field direction. And the antichiral state is shown here, and one has to possibly stare at this kind of picture a little bit. In this state, we would expect 2 different domains, or in fact 2 different configurations are consistent with the data, and those are shown here. So I can show this picture and this picture. And maybe what one can notice is that this spin that I'm indicating here is more or less parallel to the applied field, or in the two configurations that we see. That spin is kind of is bracketing the applied field direction. So this is the high magnetic field applied along the A direction. This is the spin state that we find from the diffraction data. Okay.
Colin, could you comment on, so in both those cases you were showing that the ferromagnetic component of that gamma 9 IREP is perpendicular to the applied field? Yeah. Is that obvious why that should be? Because I would have thought it was the opposite naively.
Well, so what we're reporting, specifically is the result of a diffraction experiment. And the next question is, how could that be possible?
Exactly.
And I'm now going to dive a little bit into that, because we are actually quite puzzled about it. And I'll, and so let's.
Okay, good. It's not just me being puzzled. Good. Okay.
No, it's not just you. We were quite puzzled for a while, and we did many things. We did many things to really convince ourselves. And now I'll see if I can also convince some of you. So
cool, thank you.
So what I have here on the left is plots of chi-squared, so the goodness of fit, as a function of the magnitude of the spin, or the dipole moment on sites for the antichiral state here, and then here for the ferromagnetic component of this state. So let's, first looking at the antichiral component, this is not a big surprise. We're getting a value for the antichiral amplitude, which is quite consistent with previous reports that Andrew cited, that can be obtained also from powder diffraction data. So that this is consistent. We're pleased to see that. But what we are surprised to see is this improvement of the fit when we put in a transverse ferromagnetic component. And the value is also very surprising, 0.2 Bohr magnetons. And this is to be compared to the remnant magnetization that was measured in the very same sample that we did the diffraction experiment on. So it's not a question of the sample being different. When we put that same sample in our squid magnetometer, we find a remnant magnetization. You can see the value here, which is consistent with values that have been reported in the literature, around 7 milli-μb per manganese. So something that we would not be able to really see at all with diffraction. So is there an inconsistency, we could ask? And so let's take a look at the actual polarized diffraction data. And I'm showing you data on the left, and this should have been marked here, but this is actually horizontal field polarized diffraction data. So the field is applied along the, this is a very small guide field, which is applied along the C direction. And so this is, for the purposes of the physics of the material, there's really no field on the sample. It's in the 30 Ørsted range, but this is along the C direction. And what's then shown here are spin flip scattering at 400 Kelvin, which is in the paramagnetic state. And there we do not see magnetic spin flip Bragg diffraction. But in the at 10 Kelvin, again in the spin flip channel with horizontal field, we do see Bragg diffraction at the 002 peak of manganese 3 germanium. So this is really, you know, I'd say strong evidence for a magnetic component which lies in the plane perpendicular to the z-axis, so in the basal plane. That's really what the presence of this peak indicates. Now, if we then look at the certainly at the non-spin flip part, then we find that indeed there's no temperature dependence to that, because that should only be coming from nuclear scattering. And here I'm getting a little bit into the weeds of magnetic polarized beam diffraction. So bear with me a little bit. I think I'll be zooming out a bit later. So this is the horizontal field. This is then the vertical field. And there we find that there's no significant difference between vertical field up and down diffraction. And that's consistent with the absence of a field, with the absence of a magnetization along the applied field direction. So this is in now 2 Tesla applied in the basal plane, but the absence of a difference between vertical field up, down is fully consistent with the squid magnetometry. What we do see in that configuration is in the spin flip channel, completely consistent with the horizontal field situation. We find evidence for magnetization in the basal plane and perpendicular to the field direction. So it's quite a puzzle. So, you know, we were thinking about various possible explanations for this, including multiple scattering, and we tested for that both. This was done at room temperature, non-spin flip and spin flip, and found that it isn't multiple scattering. It really is a single diffraction event. So I think we have to we took this as a serious indication of a transverse uniform magnetization. And we have various kind of thoughts about where this could come from. But firstly, as I like to emphasize, that there's no inconsistency with the diffraction, between the diffraction and magnetization data. They're measuring different things. And possible explanations for this unusual transverse magnetization is a screened tetragonal manganese germanium component. And this is, as many of you are aware, that there's a tetragonal phase of manganese 3 germanium. It actually turns out to be a ferrimagnet, and quite an anisotropic ferrimagnet. So if there was a small concentration of the tetragonal manganese germanium in this system, then it would be possible for that to give rise to this 002 Bragg diffraction. It would have to be epitaxially ingrown with the hexagonal structure, which is perfectly possible because there is a lattice. It really is a small rearrangement of the hexagonal structure, which will produce the tetragonal anisotropic ferrimagnetic manganese 3 germanium. So I think that's a pretty likely explanation, and it turns out to not be an unreasonable fraction of that second phase that would be adequate to produce this transverse magnetization. But it would need to be screened in order not to disturb this conventional magnetization measurement, which consistently in these samples still gives the 7 mmB. So I think this is a surprising result that I think is representative of what magnetism exists in the kind of samples that that many of us are looking at. How am I doing for time? I feel I might be a little long.
Let's see. You're supposed to be done in 5 minutes, so you're actually doing just fine.
Okay. So now I'm going to turn from the discussion of the static spin configuration to the excitation spectrum. And so we're going to start by looking at the long wavelength spin wave excitations. And so what I'm showing you here is measurements done at the spallation neutron source from 0 millielectron volt to 30 millielectron volt transfer. as a function of a path along high symmetry directions of reciprocal space. And you see that there are dispersive modes of excitation that we would describe as collective modes of excitation, reaching almost all the way down to zero energy. And we would describe these as spin wave-like modes, and they are propagating in three-dimensional space. This trajectory takes us all the way through through a three-dimensional reciprocal space. And actually, when we look at a cut or at a slice at constant energy transfer, then we find a ring of scattering. This is actually a ring that lies in the basal plane, reciprocal lattice basal plane. And if we look in a slice which contains both a basal plane direction and a c-axis direction, then we see that it's actually an anisotropic shape that emerges. It's more extended along the c direction, which indicates that we have slower magnon propagation, albeit still perfectly well-defined three-dimensional propagation of spin waves along the c-axis as well. And this is why I'm saying this really is a three-dimensional magnetic system. When we look more carefully in the low energy regime, just kind of zooming in on this regime around the gamma point, then one sees that there is some structure in the spectrum, and there is a suppression of spectral density at really low energy transfers. And then there's some kind of features that seem to show up. Here again, we have, this is actually the c direction, and this is an in-plane direction. So we can see that there's a larger velocity for spin waves propagating in the basal plane than along the c direction. So there are features here around 3 millielectron volts, 14 millielectron volts, and 17 millielectron volts. And we're going to look at those in just a little bit, because I want to, before discussing more these collective excitations, take a look at even higher energy transfers than 30 millielectron volts. And for that, we need a different configuration of the instrument. And one finds that up around 70 millielectron volt, there's a very broad band of excitations, really no vestige that we could see of well-defined collective modes of excitation. So these look more like very heavily damped spin waves, maybe by interactions with the electron-hole pair continuum, or maybe we should think of these really as the electron-hole pair continuum itself, and something not unexpected, I'd say, for a non-collinear magnetic semi-metal. But this does give you the bandwidth. It also shows you kind of a challenge in thinking and working with these kinds of data for manganese germanium, is that we really don't have a lot of information about the spectrum of spin wave excitations. It's really only very close to the gamma point that you can resolve really collective propagating modes. And so for this, it became very useful and very helpful to talk to Oleg Chernyshov and Sayak Dasgupta, who developed a field theory of three sublattice antiferromagnetism. And they actually have a very nice paper, I think it's still living on the archive, which in general terms classifies the kind of long wavelength excitation that you could expect to have in these systems, and also makes connections to phenomenological model Hamiltonians. And so what they describe is that in the at low energies, you have these three modes of excitations available. One is really the rotation of all of these three spins, which is the same mode that we've been discussing responding to a in-plane magnetic field. And so that's a mode that we would expect to be very soft in the system because of the soft response to an applied magnetic field. And then there are out-of-plane excitations, and they actually form a doublet, which becomes split only in the presence of crystalline anisotropies. And so then this then becomes connected with a spin Hamiltonian, which we've written in this form. I think is consistent with what forms that others have discussed today. So there's an isotropic exchange interaction, DM interaction, and the crystalline anisotropy term. And the exchange interactions that they consider are the near neighbor interaction, which is actually an out of plane interaction, so between the neighbor and Kagome layers, shown with a dotted line here. And then the Kagome layer interaction is a solid line. And then the dashed line is the third near neighbor interaction. There's an additional interlayer coupling, which we call J4, which is indicated here. And if you look at the spin structure, which is also shown in the sketch, you can see that the dashed interaction here actually connects spins that are parallel to each other. And so a ferromagnetic J4 would encourage the type of structure that is seen experimentally, and an antiferromagnetic near neighbor interaction J1 would also. And so that actually ends up being the conclusion from this. But before getting to that conclusion, let's take a look at the spectrum of excitations at the gamma point. So that this is shown here. This is at the 110 reciprocal lattice point, and these are the measurements as they come off the machine. And there were basically two different models that we considered as we looked at this data, and it was because we were told by our theorists that there were supposed to be 3 modes of excitation, and lo and behold, we see one kind of broadish peak and then 2 smaller peaks up here. And so it would be quite natural to consider having this be, let's say, the alpha mode, and then this could be the doublet of beta modes. And that kind of model can describe the spectrum. However, the intensity actually turns out to not be consistent with what is seen experimentally. This kind of description tends to produce too much intensity in the delta 2 and delta 3 modes of excitation. It also is difficult to reconcile the large value of K that is needed to produce this dashed line, because as we've discussed previously, this is a soft material, and it's a material with a very small canted moment, and so the dashed line does not seem appropriate. And on the other hand, the solid line corresponds to to K being actually equals to 0. K is the in-plane crystalline anisotropy. When it becomes 0, then the alpha mode actually becomes gapless, as we had anticipated in a sense. But the beta mode and the beta mode now becomes really degenerate. So K becomes 0, then the 2 beta modes actually coincide with each other. And so that's the mode that's the model that we think is more relevant for the data. Now you could ask, if I have an alpha mode which is gapless, why are you not seeing intensity all the way down to 0 energy? And this is a feature that is well known in inelastic neutron scattering from 3D dispersive systems, is that if you look with sufficiently broad momentum resolution, then momentum space is expanding so rapidly as you come up in energy that you actually have an increasing intensity, even though the mode is gapless. So the alpha mode can actually be hiding down here. And then this broader mode is the conglomeration of the beta doublet. And these modes here are now left without a full, are now not part of this magnetism only model. But it turns out that those modes appear, in fact, to be vibrationally related. And so what's shown here is the momentum energy plot, but shown on a scale where we can see the acoustic phonons as well as an optic phonon that happens to lie right at those energy scales where the delta 2 and delta 2 modes, delta 1 and delta 2 modes were observed. And also the intensity of those modes actually grows with Q squared, and that indicates that they have a vibrational, that they actually have a vibrational character. So then the final thing that I wanted to mention is that we can now take the velocities that we extract from the inelastic measurements that I showed previously, and then using the long wavelength theory that Oleg and Sayak developed, then convert into values of exchange constants and DM interactions and single line anisotropy terms using these expressions for the velocities. And lo and behold, the J4 interaction that I mentioned previously turns out to be ferromagnetic in this picture. And J2, which is the in-plane Kagome interaction, is the strongest interaction and is then antiferromagnetic. The DM interaction, which is, of course, critical for stabilizing the antichiral state, we also get a value for that. And the K term is then very weak, as is pointed to by various results. So to conclude, we've been looking at the field-driven magnetic structure of manganese germanium and found this surprising transverse ferromagnetic moment, which we think may be related to small inclusions of ferrimagnetic tetrahedral manganese germanium. We've looked at the excitations, which are spin wave-like at low energies and then become very broad and really form a continuum at higher energies. And we've classified the excitations based on the long wavelength field theoretical description. And this area I didn't get to. So with that, thank you for your attention.
Thank you so much. We're a little over time, but so what? This is informal. We don't care so much. There are no parallel sessions. So any questions or comments on Colin's talk?
I have a question.
Yeah.
Should I go ahead? Or?
Yeah, go ahead.
Please. Okay. Very nice talk, Colin. This is Christian Batista. I have a quick question about the parameters of your Hamiltonian, your spin Hamiltonian.
Yes.
So you mentioned that you only include the DM interaction in the bonds in the intralayer bonds.
Yes.
Although if you do a symmetry analysis, DM interaction is also allowed in the interlayer bonds.
Yes.
So is there any reason for not including those?
Only Occam's razor. I mean, really, the situation we have is that there's quite limited information from the inelastic scattering. So we had to really cut it down to the simplest possible set of parameters that would be able to describe the spectrum. But I agree that in principle, that term would also be there.
I mean, the reason why I'm asking that question is because if you compute the thermal Hall effect, with this magnon dispersion, so the thermal Hall effect due to the magnon contribution, I think without those terms, you will not get it.
Without the interlayer DM interaction?
DM interaction, yes. Yes. So, this is closely related to what I was explaining in my talk, right? Those spin-orbital fields, right, that, live on the interlayer bonds actually are also responsible for the anomalous Hall effect in the charge response. So they are somehow, what tell the lattice, the spins that, the lattice has, a symmetry that is low enough to produce the anomalous Hall effect. So my guess is that they should be there.
Yes. Yes.
I have a question.
This is Andrew again.
Hey.
Thanks very much for describing the work you've done there. So I just wanted to come back to this very interesting observation that you have of the 2/10 of a μb transverse ferromagnetic component. So according to the kind of calculation I sketched in my talk, this should give you very considerable depolarization of your neutron beam. In fact, it would be probably full 360-degree precession of the spins in that kind of magnitude of internal field. So how do you square that with the other results that you've got?
Yeah, I was thinking about that when you're giving your talk, what we did to address that question, and I think it's a very important point, but what we did to address that was we had in our refinement the sample depolarization as a parameter. And so that actually enters into determining the intensity of non-spin flip nuclear Bragg peaks. And so we do have information about this, the potential depolarizing effects of this magnetization. And what we found was that if we what we tried was to say, let's ask whether it's possible to account for the diffraction data by not having the transverse magnetization, but only having a full sample depolarization. And it turned out that we couldn't get that to be a consistent description of the data. So in other words, the nuclear Bragg peaks are part of the refinement as well, and so if there was strong sample depolarization, then the nuclear non-spin flip Bragg diffraction should also have been impacted by it, and this did not seem to be the case.
So could that simply mean that the 2/10 of a Bohr magneton ferromagnetic component isn't there, and it may be some other artifact? Sorry, I'm being very, very devil's advocate here.
No, it's appropriate. Well, that it was not. Yeah, we couldn't find really a way to account for this to this horizontal field spin flip scattering that appears at low temperatures apart from this transverse moment. Yeah, I think that is the kind of the raw experimental result that we're dealing with. I mean, I was mostly thinking about multiple scattering as a possible thing, but it was not multiple scattering. So I don't think that is a consistent explanation. I don't think we can get rid of this transverse moment, but the idea that that is a inclusion of this ferromagnetic manganese germanium, I think to me seems like a pretty reasonable possibility. Many of you are probably aware of that ferromagnetic structure and has exactly the same lattice spacing. So the 002 reflection from manganese germanium would then be the 112 reflection from tetragonal manganese germanium. It's a very insidious type of thing. So it would be fully, epitaxially oriented. And we will just be diffracting also from that ferromagnetic inclusion.
So would the volume fraction of that then vary from sample to sample, measurement to measurement? Because you also mentioned the possibility of that ferromagnetism having an orbital origin. What made you conclude away from an orbital possibility?
The orbital possibility we liked very much until we thought about the other description. I mean, I didn't really mention this as an option, but I can describe what I mean by that. So this has to do with, in an actual magnetization measurement on the squid magnetometer, we're really looking at the sample averaged magnetization. In the neutron diffraction experiment, we get ferromagnetic Bragg diffraction as long as we have coherent uniform magnetization throughout the coherence volume of the experiment, which may only be, maybe 1,000 angstrom or something like that. So all we need is actually little droplets of ferromagnetism, and that will produce Bragg diffraction. It will be perfectly, sharp Bragg peaks, resolution limited, and everything. So that is the manganese germanium description. The orbital description has to do with the form factor of the system. So again, in squid magnetometry, obviously it's the full magnetization that's being measured, but in neutron diffraction, you're weighing in accordance to the form factor of the that produces the associated with the entity that produces the dipole moment or the magnetization. And so if you were to have a local moment generated a ferromagnetic component, which was partially screened by an orbital magnetization, or let's say almost completely screened by an orbital component, then with neutron diffraction, we would not see the orbital component at all, because its form factor limits the diffraction it can do to very, very low wave vectors. So we would only see the local moment component. So this seemed like a very interesting possibility, and I don't think it's inconsistent with the data. So we still have it as a possible description, but I'm right now more worried about the inclusion of ferromagnetic manganese germanium.
Can I ask a question?
Yes.
Well, there is one other possibility. As you know, Mn3Ge is not stoichiometric. There is an excess of manganese, which is believed to occupy germanium sites. So I was wondering, can they play any role in ferromagnetism? You know, this is an experimental fact that it is not Mn3Ge, as Nakatsuji knows also. They
yes.
have quantified. It is Mn3.06 or 5. So it's 5%. And if you have 2 μb per manganese site, which are occupying the germanium site, this may give you what you don't even need this tetragonal structure. Have you thought about this possibility?
Yeah, we have thought about that possibility, and we have actually, in the neutron experiment, it turns out that we have very, very good contrast between manganese and germanium. So we can actually see these mixtures, and we can confirm this stoichiometry excess manganese. But have I thought about the possibility that this excess manganese would be producing the transverse moment? Yeah, I think that seems like a possible thing as well. I mean, for me, it almost falls into the I mean, this implies some form of a disorder in the planes, and it's kind of it's a similar scenario as the ferromagnetic inclusion, though I agree that it now has to do with an off stoichiometry.
So maybe I can just make a point. You have the curve of magnetization on this slide. So yes. This is in plane magnetization, which has a jump. Now, if you look at out of plane magnetization, there is no jump, but yes. The slope is similar. So what has always puzzled me is that the slope of magnetization, basically high field susceptibility, is isotropic.
Yes.
Doesn't care about the orientation of magnetic field.
Yeah. Yeah, I would say one thing is that the induced magnetization that corresponds to that slope would not be enough to account for this transverse moment, and furthermore, it's not oriented in the right direction. But what you're indicating is that you're asking, or are you indicating that maybe the slope has to do with this excess manganese?
This is what I was wondering, but okay.
But the thing that really has been puzzling to us is that this 0.007 μb per manganese is really very stable, I think, across different groups and the different samples. Initially, I was thinking, well, that would be too variable to be really reliable, but it really is consistent, including in our samples. And yet we have this relatively large transverse magnetization that we find. So whichever explanation is eventually found, it has to account for the screening of this ferromagnetic component. So it's a little bit of a puzzle, and there you have it.
All right, thank you. Good discussion, but maybe we should get Colin off the hot seat for a few minutes and turn to Peter Armitage. So Peter, you unmuted? Nope. There you are.
Sure. I'll
right.
Let me share my slides here.
All right. Please go ahead.
Okay. Sorry, slow. Can you see that?
Yep.
You do?
Yep.
Okay. Zoom is always changing around on us. It usually comes up with some kind of border around the whole thing, but apparently not today. So, okay, you can see my title slide here, right? Great. So, yeah, thanks very much for the invitation to talk and tell you a little bit about various different things we're working on. It's also great to hear about all the progress that has gone into hearing about these interesting materials. So the talk that I'm going to give today is about, it's in part about manganese 3 tin, but I thought it might be interesting for this audience to give a kind of overview of a number of different things that we're doing on the general topic of topological semimetals. And so we do primarily in my group, we use terahertz spectroscopy to investigate materials on their low frequency scales. But in the case of some of these topological semimetals, and particularly in the case of a material cadmium arsenide, we can actually use the topological semimetal and some properties of it to generate terahertz light. So we're in a stage now where we are able to study not just what these materials are, if you will, but also what they can do. And so since most of us got interested in condensed matter physics because materials can do interesting things, this kind of fits into that general context. So I'm going to tell you about 3 different materials, and each of these materials corresponds to the name of one of these gentlemen up here on my title slide, Weil, Dirac, and Luttinger. And we have, of course, Weil and Dirac systems, semimetals. The notion of a Luttinger semimetal may be less familiar to people in the audience, but I think equally interesting, and I hope interesting to this audience. I'm going to give you a broad overview on a number of different things here, so I'm not going to go into anything remotely as much detail as many of the other talks are, but I'm just going to kind of give you a rather broad feeling. There are papers about these things that give all kinds of details. And if people have questions as we go, just please let me know, and we can talk in further detail. And I would say that the majority of this work was done in the context of our Institute for Quantum Matter, which is EFRC, funded by Department of Energy, of course. Okay, so before I tell you about it, let me thank the people who made this work possible. So first and foremost, my former student, Bing Cheng, who I noticed is on the call. Bing's graduated and moved on to bigger and better things as a postdoc at Stanford now. And he was in much of this work. We have tried to have a rather collaborative enterprise and was aided by a number of my group members whose names appear there. Some of the work was done in collaboration with Matsunaga's group at the Institute for Solid State Physics at the University of Tokyo. And I spent a wonderful 6 months on sabbatical there. And so this is a picture from when we could all, a time when we could all go stand outside in close proximity to each other. But I appreciate his hospitality in my sabbatical there, and some of the work was done there. We've had great collaborations with Satoru Nakasuchi, who is a long-term collaborator, also at the Institute for Solid State Physics, but is also a research professor at Johns Hopkins, a number of other people, including Mick Lipma, who's at ISSP, and then a great collaboration with Suzanne Stemmer from Santa Barbara on the cadmium arsenide films. I'd like to give my conclusions in advance, so when I invariably run out of time, you've already seen them. But in keeping with the topic of this talk, I'm going to tell you about manganese 3 tin and the work we've done on that. This is, of course, an antiferromagnetic Weil semimetal, and I'll tell you about the terahertz range intrinsic anomalous Hall effect. I'll tell you about the work we've done on cadmium arsenide, and cadmium arsenide is a canonical Dirac semimetal. So there we have evidence for a number of interesting things. Circularly polarized phonons under magnetic field. Coherent generation of high harmonic light. So as I said, we can use these materials not just to be probed with terahertz light, but we can use them as sources of terahertz light itself. And also finite frequency manifestation of the chiral anomaly. So that's the Weil and that's the Dirac aspects of this. The Luttinger aspects of it is this material praseodymium iridate, which is unlike the Weil and Dirac systems, which are linear band touching systems. Praseodymium iridate is a quadratic band touching system. So it's also a semimetal, has many properties which are similar to the linear systems, but the quadratic systems present interesting effects on their own accord that are mostly in the context of very stronger interactions. And I'll tell you a little bit about that. And I think that there are a number of people here who at least had a history in things like oxide MBE. And so I keep pushing the fact that we still don't have such a thing as an oxide topological insulator. And I think strained films of praseodymium iridate are the best bet for that. Okay, so let me start here with telling you about manganese 3tin. And I'm going to basically have, since we've had so many great talks on this, I'm not going to say anything at all about the background material, but just mostly about what we've learned about manganese 3tin. So for the terahertz experiments that we do, much of the time, the best experiments can be done on films. And so it's a bit of a constraint for our technique. The best experiments are done on films, typically in transmission. And so that's why we enjoy having collaborations with people making all kinds of high quality thin films. In this particular case, these were manganese 3tin films grown by DC magnetron sputtering onto silicon substrates. These were done in Satoru Nakasuchi's group at ISSP. They, to investigate things like anomalous Hall effect, they have to, of course, be, the C-axis has to be in plane, as we know. And so these are films which are actually randomly oriented with the C-axis in plane. Still interesting from a perhaps technological perspective. And so one of the things that we were interested in here is, for instance, trying to understand what happens with the simple resistivity curve that you might measure by DC resistance. And on these particular films, in fact, resembles quite closely what happens in the context of single crystal transport, so transport in single crystals of manganese 3tin. So, you know, of course, decreasing as a function of temperature. Now, we did terahertz spectroscopy on these films, and I plot here on the left panel the optical conductivity as a function of frequency in the terahertz range of the real and the imaginary parts of the conductivity. So conductivity is a complex quantity. There's a real part and an imaginary part, and they both give us information. Of course, they're all related to some kind of complex response function. And depending upon what we're interested in, some physics can appear more in the real part or the imaginary part or both, for instance, right? In superconductors, it's actually the imaginary part of the conductivity which is most important, okay? So we can-
Peter, could you?
Yep.
Sorry to interrupt. Could you just comment on the temperature phase diagram? Does it look exactly the same as the bulk? I know in the bulk there's this sample to sample variation of the low temperature phase, whether it's below 50 Kelvin to room temperature. What does that look like? I kind of see your cartoon top right, but
yeah. Sorry, what do you mean by sample to sample variation?
So in the bulk materials, the low temperature phase can vary from 50 Kelvin to room temperature.
Oh, I see.
Yeah, and so in the films, is it in the, let's call it the interesting phase, for want of a better phrase, but the phase that's showing the anomalous Hall all the way down to low temperature, or is there? It's not obvious.
So you'll see some data. You'll see some data on the next slide on the Hall effect. But you know, of course, because it's films, and I think there's just a single group which has made them. There's far less, I think, statistics on what is the scope of variation. But generally, what you can see, for instance, on the data right here, below 200 Kelvin, there start to be resistivity anomalies that are also, you could see, they're also in the resistivity here. And that seems very much to be the frequency range where you kind of go from this inverse triangular spin state to the lower temperature helical phase. Okay. One has a hard time doing diffraction experiments on films like this, and so I think we know less about the actual symmetry in films.
But the relevant temperature is around 260 Kelvin, not.
Yeah, that's right. Yeah, around.
Okay, thank you.
Yep. And I think also, I don't think I have the plot of that here and now, but one sees that the things that seem to be a little bit smeared out as well in the film situation.
And Peter, sorry, Anand here, while we're on the subject of films here, this is a polycrystalline film, is that right?
That's right. Yeah. So C-axis is primarily in the plane, but then randomly oriented.
Thanks.
So when you see a resistivity curve like this, just by itself, you don't a priori know what's necessarily leading to the decrease, particularly in a semi-metal, the decrease of the resistance. Are you freezing out charge carriers, Is there something associated with change in symmetry? Is there something changing with the scattering rate? And so what you can see here from these plots is that a quantity that we call the plasma frequency in optics, but it's related to, in this case here, the charge density of the system, undergoes a very notable decrease below about, starts around 250 Kelvin, becomes quite prominent below 200 Kelvin. But the reason why the resistivity decreases so dramatically is that the scattering rate decreases dramatically. And these effects may be associated with partial gapping of the Fermi surface, which comes from the breaking of translational symmetry along the c-axis. And so one sees these effects very similar. It's a very similar phenomena that is seen very often in charge density wave systems, where you get partial gapping of the Fermi surface and you lose charge carriers. And so, for instance, the density goes down, the plasma frequency, but also the scattering rate goes down as you kind of remove phase space for scattering. Now, we're interested in things like the Hall effect. And so here's a plot of, this is the real part of the low frequency Hall conductivity as a function of temperature. And you come in from this inverse triangular state to this helical state into what this low temperature state, which many people have referred to as a spin glass like state. And what you can see is, of course, there's indeed a dramatic change in the optical, the Hall conductivity decreases, and then there's actually a small increase at the lowest temperatures. And so the Hall conductivity itself is a function of frequency, as you can see on the right side here. This is in fact frequency independent over a very, very large frequency range, or approximately frequency independent. And just like the conventional longitudinal conductivity, the Hall conductivity is also a complex quantity. There's a real part and imaginary part. And it's actually the imaginary part of the Hall conductivity, which is the dissipative part of a response. And so you can see that this is the room temperature data here in the inverse triangular state. And you can see, in fact, the dissipative response over a very, very large frequency range is very, very close to zero. And then the real part is the non-dissipative response is essentially flat. And this very much points to in this frequency, or this temperature range, the response being, the Hall response being, the anomalous Hall response being due to the intrinsic Berry phase mechanism of the system. There is this very small increase at the lowest temperature scales, and here the frequency dependence ends up being very interesting. I think this is a subject for future study. What I plot here is the Hall conductivity, the real and imaginary parts, as a function of frequency. And what you can see, the data at the top is the high temperature regime, and the data at the bottom is the low temperature regime. And so you can see the decrease, of course, in the normal sigma XY Hall response as you go down to lower temperatures. But then it starts coming back up again. And when it comes back up, it develops actually a frequency structure. And what precisely to make of this, we don't know for sure. Perhaps related to some funny domain structure, or what people refer to as this kind of spin glass physics at the lowest temperatures. But considering that these structures that one sees in the Hall response are much sharper than what you see in, let's say, the longitudinal conductivity. And so it would be, it's great if somebody, a theorist, might find the data compelling enough to, we can think about this in more detail. Okay, but what it does show for sure is that the mechanism for the anomalous Hall effect at the lowest temperatures is different than it is at the highest temperatures. Highest temperatures seems to be very much consistent with intrinsic Berry phase-like mechanisms, but something else is going on at the lowest temperature scales. Okay, so that's manganese-3 tin, and now let me tell you about a few different other things here. So let me tell you about the Dirac semi-metal cadmium arsenide. So Suzanne Stemmer's group, these are films grown by molecular beam epitaxy from Suzanne's group, and I think these are still the best cadmium arsenide films that I know of. Cadmium arsenide in the bulk crystals actually suffers from having very large, reasonably large, I should say, excess carrier density, but the films have low carrier densities with a Fermi energy, in some cases 30 to 50, 60 millieV above the Dirac point. So this material is a Dirac semimetal, and for the current purposes, I want you to think of this Dirac semimetal as essentially two copies of a vial system with the positive and negative nodes on top of each other. So on the right-hand side here is the optical conductivity as a function of frequency. Red is the high temperatures, blue is the low temperatures. And as you take the system and cool it down, you freeze out charge carriers. And the area underneath these optical conductivity curves is a function of the density of the free charge carriers in the system. And so as you cool the system down, you're freezing out charge carriers, and you can see the area under this curve decreases, and that's consistent again with the carrier density decreasing. You get down to low temperatures and you see a reasonably sharp peak consistent with the high mobility in these systems. This little bump here, that's a phonon. Cadmium arsenide has a very, very complex crystal structure. It's hard to know exactly what phonon this is, but you know, it's a large crystal structure with heavy atoms, and it's presumably something in a, you know, in a kind of a simpler version of the crystal structure would be some acoustic mode, which is then folded back to the zone center by this very, very large unit cell, which comes from vacancy ordering, which is known to be important in these systems. Okay. Now, we've seen a number of different phenomena in the system. And again, I'm not going into these things in detail. I'm just kind of giving you a feeling for the kind of physics that's going on. One of the very first interesting things that, that Bing found was that when you take these films of cadmium arsenide and you put them in magnetic field, you see a very prominent cyclotron resonance. Okay, and cyclotron resonance is, of course, the circular motion of charge due to Lorentz force, that you can drive the charge in a circle due to the Lorentz force by applied magnetic field. The cyclotron frequency is proportional to 1 over a mass. And in a Dirac massless system like this kind of effective mass can be very, very small. That's essentially proportional to the Fermi wave vector in this system. So you can get very, very large masses, which means you get very, very sensitive response of the system to magnetic field. And in fact, that's what you see. So one of the things that we like to do, and is kind of a unique aspect of these time domain terahertz experiments that we're doing in here, is since we measure the complex conductivity, we can measure, let's say, the conductivity in, we measure the transmission through the system in let's say, we can think of it as a transmission matrix, and we can measure the transmission of the X-polarized light when we send X-polarized light into the system. We can measure how much light comes out in the Y direction when we send light in the X direction. That's a Faraday rotation. But ultimately, what we can ultimately do with it is we can take the conductivity, which we would measure, for instance, sigma XX, sigma XY, the real and imaginary parts, and then we can put it into whatever basis is appropriate for looking at the physics we're interested in. And it turns out for this kind of analysis here, the best basis, most interesting and effective basis to put the data into is not in terms of, let's say, sigma XX and sigma XY, but in terms of right and left circularly polarized light. Okay, and then it becomes useful to plot this as right-hand light as a positive frequency and left-hand light as a negative frequency. And this just corresponds to light, if you will, having a frequency dependence that goes like e to the I omega t or e to the minus I omega t. Okay, so then what do you see here? You see this purple curve, that's 0 magnetic field. Okay, it's a Lorentzian peak, peaked at 0 frequency. And these peaks here on the side, that's the phonon. We put a magnetic field on it, and you can see very, very quickly and quite sensitively, the peak moves to the left-hand side in this particular fashion. Okay? So that tells us about the sign of the charge carriers. And quite notably, and it looks subtle on this plot, but in fact, once you kind of do a more detailed analysis, you see the effect is actually quite large. You see that this phonon, as the cyclotron resonance moves towards this phonon and then through it, the phonon actually shifts in frequency. It shifts, and this is plotted here as a plot of the center frequency of this phonon, plotted as a function of magnetic field. And you can see that, in fact, that there's shifts for left and right polarized phonons, but in different directions. And so what happens here essentially is the phonons, which are, let's say, the right and left circularly polarized phonons, which are degenerate at 0 magnetic field, split. And one can show quite generally that for small magnetic fields, they split linearly. You can assign this linear splitting to an effective cyclotron, to an effective Bohr magnetic moment of the phonons. So the phonons pick up a effective magnetic moment. And it's actually an incredibly large number. It's the largest phonon magnetic moment that's ever been measured. It's almost 3 Bohr magnetons. So the splitting really between left and right is quite large. So another phenomena, again, this was after I came back from my sabbatical in Tokyo. Then Bing went and spent a few months there doing work in that group. And again, on cadmium arsenide. And what they showed is that cadmium arsenide driven with ultra intense terahertz actually is a very efficient system to actually generate high harmonic terahertz radiation. And this effect, it was proposed actually for graphene quite a long time ago. In the context of graphene, you can imagine if I have, let's say, a graphene system or any massless parabolic band, and I start driving charge back and forth, and I build up, let's say, more charge on the right and more charge on the left, the current as a function of time has this kind of square wave profile. So it has all these harmonics in it. In contrast, a parabolic band is going to have, if you drive it with sinusoidally varying light, is going to have a sinusoidal current that comes out. And so graphene was proposed to have this very much this kind of response. And in fact, people found in graphene that it actually was very nonlinear. But in the context of graphene, it still, although this was proposed early on, I think, and then was later found, I think it's now believed largely that the mechanism in graphene doesn't come from this. It's essentially a very different mechanism than that originally proposed, that essentially comes from some kind of quasi-equilibrium process with repeated heating and cooling that this heating and cooling vary very rapidly on the terahertz timescales. In contrast, and I'm not going to go into the details of all of this, what Bing and Matsunaga-san and Kanda-san were able to show was that cadmium arsenide is a system where this mechanism, this kind of coherent acceleration of charge, led to high harmonics being generated this material is essentially as a source for high harmonic terahertz generation. And this is just a plot here that shows let's say a semiconductor, the graphene here in blue, and you can see this is plotted on log scale, and this is cadmium arsenide here. So quite a bit more efficient than the situation in graphene, and also by a different mechanism. Okay, let me tell you about another phenomena here in cadmium arsenide, and this is something that people got very excited by in the early days of vial semimetals, and I think, unfortunately, a lot of that early work on what is called the chiral anomaly suffered from various experimental artifacts that I won't go into. But the chiral anomaly is something which was first discussed in the context of particle physics, and the idea is that if you have, let's say, a Dirac C, which massless Dirac fermions is such here, and let's say in a particle physics system, we imagine that it's filled up to zero energy here, and then these energetic states continue on down to minus infinity. If I put a magnetic field on such a system, then I develop Landau levels if the system is charged, but one can show quite generically for a massless chiral fermion like this that you develop, let's say in the third direction, you develop Landau levels, but in the third direction, the direction of the applied field, you'll develop this dispersing charge, which is kind of dispersing energy level, which is going in a single direction. And if you put an electric field on this thing, you would imagine you're pulling in charge from the vacuum. And so that's going to lead to a non-conservation of charge. Now, of course, that doesn't happen in lattice systems. And in a lattice system, we believe if we have a positive chirality node and a negative chirality node, ultimately they're connected below the Fermi energy. And so if you have this chiral anomaly, you kind of pull charge from one node to the other node in just exactly this fashion. You can scatter charge from one node to the other. And it's generally thought that in such a system, in a vial fermion, you might scatter charge within a node much faster than you will scatter between nodes. And then you can build up this chemical potential difference. And this transport anomalies that are related to this then have various signatures. That would be the situation in a vial semimetal. In a Dirac semimetal, you have actually two copies of this system. And again, I want you to think of this very roughly as thinking of two copies of these vial nodes on top of each other here. And then there are other scattering channels that come up that are associated with, let's say, large momentum scattering, and then also what people refer to as scattering, let's say, between the positive node of one of the subspecies and the negative node of the other. And this is typically, this degree of freedom is called the isospin degree of freedom. And then there's an isospin scattering rate. So we did these experiments on these really exceptional films from Suzanne Stemmer's group. And what we saw was really in textbook agreement with the theory of Anton Burkhoff, who I think is part of the EFRC, and I also noticed is on the call here. But this is what Anton had calculated. What is proposed in the DC version of this is that when you put the electric field in the same direction as the magnetic field, you should get negative magnetoresistance. And this has been rather problematic to see with DC experiments. You get all possibilities for all kinds of artifacts. The terahertz spectroscopy is non-contact experiment. So you don't have to worry about these kinds of so-called current jetting effects, which have plagued those experiments. But what Anton predicted is that you kind of have normal Drude transport at zero magnetic field. You put a magnetic field on this system, and you should get this very, very narrow peak, which appears, where the width of this peak is the chiral scattering rate. And that's the scattering rate basically to relax the imbalance in this chiral charge. And that's essentially exactly what we see. This again is the phonon here, which is not directly related to the physics that we're looking at. And we put a magnetic field on this system. This is when the electric field is parallel to the magnetic field. You don't see this physics for the electric field perpendicular there. But when you do that, you see this peak appears at low frequencies. Nothing appears at high frequencies. And the fact that it only appears at low frequencies shows you the new transport channel has formed, right? So the transported zero magnetic field can be described by a single Drude-like Lorentzian, and then you get this other peak which appears on top of that, and there's a kind of a two Drude line shape to this. I won't go into details, but I'm happy to answer more questions about it. But really what it is demonstration of is one, pumping of chiral charge with this E dot B effect, which has been discussed in the context of the chiral anomaly, and two, a direct measure of the chiral scattering rate. Okay, I'll take, if that's okay, I'll take another maybe 5 minutes or so to tell you about the last topic.
Peter,
what's that?
Sorry, can I just ask a quick question?
Sure, sure.
So from that picture, what would you say is the ratio of the, chiral scattering rate and the non-chiral?
Yeah, so this is something that we don't understand, I would say. So you can pull off from yourself on these plots that the scattering rate of the normal is about a terahertz wide. If I look at these blue curves here, this is about half width, about a terahertz wide. The chiral scattering rate is about a quarter of a terahertz. And so we've looked at your papers, Anton, and as well as made some estimates on our own based on the details of this particular electronic structure. This quarter of a terahertz is so say 1/4 of the normal scattering rate. That's a number which is hard to understand. It's much, much larger than one would anticipate based on the band structure parameters in the system. And so we don't know why. The theory that the phenomenology we developed is based on the idea that impurities in this system are large. So the impurities themselves are not breaking inversion. So it may just be that, kind of cadmium, arsenic vacancies in this system are leading to kinds of scattering, which is allowing mixing between isospins at much higher order than we had. Well,
yeah, I think that's possible. That the theory, my theory, kind of assumed that impurities are large in the sense that they don't lead to any scattering within the unit cell, right? Yeah. So, but if that's not the case, then you certainly can have significant scattering between chiralities. And also, is it possible to move the Fermi level even further towards the nodes by gauging in principle? Or
in principle, it's possible. Yeah. So we you're familiar with our paper, and there, what Bing was able to do was to take advantage of the fact that good films have low Fermi energies, and some of the films that were grown had higher Fermi energies, and so in this way tune the chemical potential in this fashion. Although the strength of the effect was very much dependent on the height of the Fermi energy above the nodes, this ratio of 1/4 of chiral scattering to normal scattering within the restricted range we were able to tune it didn't seem to depend very much on that. Right. It may be that we need to be at much lower energies even still. And so then in which case, as you said, gating is probably the best thing to do. Right. These are hard experiments. I don't have any current plans, but it's something to think about.
Oh yeah, I think, well, I'm obviously biased, but I think it's still not, it's all consistent. I think, it's just the impurities may be, not large on the scale of the unit cell. And so.
Which is quite reasonable. The unit cells here are quite large.
Right.
Yeah.
So Peter and Anton as well, I guess, in this case of a Dirac system, this chiral tau represents both the Dirac point relaxation and the isospin from the two overlapping Diracs that make up the vial. Is that correct?
In the context of this phenomenology, yeah, you can make estimates. You would kind of expect that whichever one is faster is the one that you're most sensitive to. And we made some estimates in our paper, and it looks like the inter-isospin scattering is going to be the fastest. Although our prediction for it is 4 orders of magnitude smaller than we actually observe, or 3 orders of magnitude smaller than it actually is. So one would expect the inter-isospin scattering to be larger and that to dominate, but we get the numbers totally wrong. So what's the takeaway message? I'm not sure.
Okay, but in terms of small or large K scatter, there's a difference there. So if you were to compare it to a vial semi-metal where they're not overlapping,
right,
you wouldn't see this dominant mechanism.
There, the only mechanism possible to relax
is delta K to the other node.
Yeah, that's right. Okay. Large momentum scattering, and so here to belabor the point that Dirac semimetals have the positive and negative. I mean, I know you know this, but just for the full audience, positive and negative nodes overlapping. And normally you would expect these, so the bands are twofold degenerate, and normally you would expect that these bands would hybridize, but they don't, and they're protected by crystal symmetries. So it's the fourfold rotation symmetry in cadmium arsenide. So in a sense, the scattering is suppressed between these two species by the same symmetry that doesn't allow them to hybridize, and so that symmetry can be broken in a variety of ways, and it's it mostly holds most at low energies, or this kind of effective symmetry. So in a vial semimetal, you don't have that channel, and life is simpler. But all the materials we know in nature thus far seem to have physics which is more complicated in terms of different bands at the Fermi energy.
Of course, yeah. So just to follow up on that, does that then indicate something about the disorder actually locally breaking that symmetry, so that that's what's responsible for this orders of magnitude difference in the observed scattering rate?
Presumably that's right. Yeah. So so the unit cell here, the calculations that we did were based on kind of a reduced. I think people debate exactly what the real structure is of cadmium arsenide, but it's usually thought to have like 80 or 150 atoms in the unit cell. Of course, you can do a calculation based on a smaller. We kind of neglect some aspects and do a smaller unit cell, but even that unit cell is big. And so if you're imagining that the principal source of disorder is vacancies, as one might expect for things like arsenic, then as Anton mentioned, his calculation and the other calculation that I know out there, they assume that these impurity is large on the scale of a unit cell, bigger than a unit cell. And that's done because that's simple, and you should do the simplest thing first. It doesn't look like it matches the data. That's right.
Yeah.
So impurities are presumably small on the scale of the unit cell, and then you can mix isospin varieties.
If that's breaking the fourfold symmetry, that's naturally
exactly. Yep.
Okay. Sorry. Stop
in theory, the scattering rate would the chiral scattering rate would go to 0 in the limit of 0 Fermi energy, and that's of course not true. I mean, no, it's not going to happen in the real system. There is always going to be some residual scattering rate.
Mm-hmm.
So yeah.
Okay, that's an interesting point. Maybe we come back on that. I have a question myself, but I'll kind of race through the last few things here on this, and then tell you a little bit about precision mirror days. So I'll take, because there was some discussion now, I'll take about another 5 minutes if that's okay.
That's all right.
Okay, so this is a topic, it's not a Weil or Dirac system at all, but I hope it's interesting to you, to the audience. And that's this notion of quadratic band touchings. And so I want to go back in history a little bit here for a moment and pull up this remarkable paper from 1971. And I think even the community of people working on Dirac and Weil systems are not everyone is aware of this paper. And I want to point it out. So Abrikosov and Bodislavsky wrote this in 1971. And we can just read the highlighted text here. The possibility of contact of the conduction and valence band at a single point is investigated within the framework of the one electron problem. It's shown that the symmetry conditions for the crystal admit of such a possibility. So this is in fact the first, as discussed in this paper right here, is actually the first time in the literature that the notion of the Dirac semimetal, it doesn't discuss Weil systems, but the Dirac semimetal, the notion that you could have these special crossings that were protected by symmetry, the first time it enters in the literature. The notion of Weils, of course, is even older than that. It goes back to Conyers-Herring thesis work in the 1930s. And of course, we've had a remarkable resurgence. But this paper is 41 years before the paper of Young and others at Penn State, which, as far as I know, kind of introduced the modern notion of a Dirac semimetal. Okay? But as Abrikosov also says, in the neighborhood of the point of contact, the spectrum may be linear as well as quadratic. And he discusses the symmetry considerations of both these things. Now, at those times, one of the reasons these guys were thinking about these things is that small gap semiconductors were of interest. So you could have a material like cadmium arsenide, which has the same essential crystal structure as, let's say, gallium arsenide. Sorry, cadmium telluride, I said, which has the same crystal structure as gallium arsenide. And you can imagine tuning it to the mercury telluride case, perhaps through a linear crossing as such. This Hamiltonian describing this is referred to as the Luttinger Hamiltonian. And now we generally refer to systems which have this quadratic band touching, protected by inversion symmetry, or at least approximate inversion symmetry, as Luttinger semimetals, where you have this, again, quadratic touching here as such. These quadratic systems have a number of interesting properties, and in the basis of time, I'm not going to talk about this, but one of the things that's particularly interesting about them is their dielectric response. And in any system, when you have this kind of quadratic touching, the presence of these possibility of virtual quantum mechanical transitions gives a contribution to the dielectric constant. And so, of course, the scaling of how the phase space for these virtual transitions goes depends upon their dispersion. And this is a rather small effect in linear crossing systems, 3D linear crossing systems. But it's a very dramatic effect for how energies scale with the density of states in quadratic systems. And it leads to a particular functional form in a quadratic band touching system that goes like 1 over the square root of omega, okay? Which actually, interestingly, has the same part from the real and imaginary parts. And I'm just going to zoom all through this on the basis of time. But the important thing to note is that you can take this functional form here and put it in the functional form of where you use the Bohr, say the Rydberg energy, and rewrite the dielectric constant, let's say, as a ratio of the square root of the Rydberg for a particular system. So this can be a very different number, of course, in a material system than it is in the vacuum of free space, over an energy scale, which could be the Fermi energy, it could be the temperature, or it could be some kind of kinetic energy, let's say 1 over h bar q squared here. And the important thing here in this expression is that this square root of 1 over q, the dielectric constant, converts the real space potential into a 1 over r squared interaction instead of 1 over r, which then corresponds, if you're talking about the interaction energy between charges at the Fermi energy, that goes like kf squared, which is the same as kinetic energy does. And so the important point is that in a quadratic band touching system, both kinetic energy and potential energy scale as the Fermi wave vector squared, which means that interactions are marginal, right? Of course, in a typical parabolic band system, is you make the densities really small. Eventually you get a Wigner crystal. You get a strongly interacting fluid, and then it becomes a Wigner crystal. But in this sense, more interesting possibilities are admitted because screening happens in such a fashion that it essentially can allow you to have very, very strong interactions while still being essentially in a liquid state. And of course, Abrikosov realized this as well. And this is, again, a very remarkable paper because he doesn't use the words non-Fermi liquid. But in 1971, he uses all of the words except for non-Fermi liquid and says things like, you know, here he says the concept of the one particle spectrum. Here, by that he means quasi-particles, i.e. Fermi liquids, turns out to be inapplicable. Okay. So, so this is something we're interested in. Again, I'm just going to rush through this on the basis of time, but 1971, people were thinking about these systems in the context of things like alpha tin. And if you go and you put in the numbers, let's say for the effective mass in alpha tin, very, very small, the effective dielectric constant, reasonably large, the Rydberg energy is about 2 milli-electron volts in alpha tin. In praseodymium iridate, which was suspected to be the case in the context from band structure calculations, but is also shown by angle-resolved photo emission to have a quadratic band touching, it's an oxide. Masses are large, dielectric constant is large or smaller, and so the Rydberg here is about 400 milli-electron volts. So it's much, much bigger energy scales. And I don't want people are interested in it, and I could tell you more about it, but let me just say that it's hard to see the non-Fermi liquid physics that Abrikosov talked about. You need to be at energy scales. We had 400 millieV, but you need to be at many orders of magnitude below that. But what we did see in measuring the optical conductivity and looking at the dielectric constant in the system, and let me just emphasize this part right here. This is a dielectric constant as a function of temperature, which rises up to these very large values, 100, almost 200 here in these system. From the expressions that are given in the context of RPA, you can pull out the Fermi energy. The Fermi energies here are very, very small. These numbers are very, very large. So, you know, typical values in a semiconductor are more like 10. And so what you're seeing here is really the consequence of these virtual interactions, and essentially is showing you how the consequence of the quadratic band touching leads to very increased screening. And again, from this, and I won't talk about the details, but one can show that the effective interactions in this system, which are again on the order of hundreds of milli-electron volts, and the kinetic energies of the system on the orders of tens of milli-electron volts, these are incredibly strongly interacting systems. And so what I think the future here on such systems is trying to take the densities here and bringing them to even lower energies. And what one hopes to come into is a regime at the very lowest temperatures and energy scales where this non-Fermi liquid physics comes out. What we did in our experiments is really just show that the system was strongly interacting, but it's still effectively in the Fermi liquid regime. We want to go to even lower energies, and that's something for the future. So I did tell you I would go over time, and so you've seen my conclusions already, although there were some questions. But what I hope I've convinced you is that there's interesting things to do with these kinds of terahertz experiments on Weil semimetals, Dirac semimetals, and this other system here, Luttinger semimetals. Let me say the final thing I wanted to mention in the context of the praseodymium iridate. This is a quadratic band touching system, and what we know from the band structure of this system is that if we could strain this system, it should become a topological insulator. And so this would be the first oxide topological insulator, which I think would be a tremendously interesting thing, because that should have much, much better transport properties, let's say, than many of these chalcogenide systems that we know have all kinds of problems with defects in the bulk, giving all kinds of large bulk conductances. So that's something that I hope a problem that people will be able to tackle in the future as well. So anyway, thank you for your attention.
Thank you, Peter. We had good discussions during the talk, but if there are any additional questions or comments, you know, why not?
Quick one here from Anand here. Peter, so what kind of strains are we talking about for praseodymium iridate?
That would turn it into a topological insulator? Is that what you're saying?
Yep. Yep.
That's a good question. I actually don't know. I would say that it's essentially the same mechanism, but in a better system as what was done by the Würzburg group on mercury telluride, right? Sure. So the very first system where the quantum spin Hall effect, 2D topological insulator was found was mercury telluride. And mercury telluride, as I showed you a few slides back, is a quadratic band touching system in the 3D bulk. So they took mercury telluride, and by a combination of strain and space confinement, they gapped it in the bulk. They have done experiments on thicker films of mercury telluride, which were claimed to be thick enough that didn't have spatial confinement, making a bulk, where they said it was just strain. And in those systems, the claim was that they were able to make about a 20 milli-electron volt gap. What that was in terms of strain in percentages, I actually don't know. But if but again, mercury telluride's got all kinds of issues as well in terms of bulk conduction problems and defects and those kinds of things. If you could do the same kind of strains on praseodymium iridate, that would be a much better system. Quantum spin Hall, which should also be a much more robust feature in that system.
So,
yeah, go ahead.
I was just going to ask a little bit of a technical question, but for the last system, the praseodymium iridate, with the, so you've got a 10 MeV Fermi level or something, so you've got some plasma response as well as the dielectric response. Just technically, you just use frequency to separate the dielectric constant from the plasma response, or is there something?
I didn't. I can just show you what we did. I didn't talk about it because I
sure.
But so let me do that now. So so this is a plot of the optical conductivity as a function of frequency in the terahertz range. Okay, that's the DC point. This red purple, that's the AC response. And so if we go ahead and just fit the real part to the Drude model, the blue curve here is what you get out. And I should say with all of this, my only contribution to this work, it was almost entirely Bing, was when he was saying that he couldn't fit it.
Just the Drude model, yeah.
Just fit the Drude model. And he said, well, in order to get it to fit, he always had to add a large dielectric constant in the background here. And this is kind of the simplest functional form for that right here. And he was saying the only way he could do it was with just this really, really large value here. And I remember having read this paper of Abrikosov and seeing that these kinds of things. And so that was my contribution to this, was just saying you should take that value seriously. And so if you don't put in that dielectric correction, you get the blue curve here, which just misses the actual imaginary part of the data. And when you get that, then everything kind of fits out. And there's also a very beautiful, and I didn't talk about this, kind of correspondence between, so from the theory with the RPA, random phase approximation theory, you can see what's the size that the dielectric constant should be based on a particular Fermi energy. And so from the values of the dielectric constant, we can pull out the Fermi energy. And that value is depending upon the particular film we looked at, something like 7 to 10 milli-electron volts. If you go then and you look at right here, if you go then and if you look at the scattering rate as a function of temperature, you see T squared with a coefficient which turns out to be exactly the Fermi energy over the Fermi. So there's this kind of very beautiful self-consistency of the data. And so what the takeaway message is for this, the system is strongly interacting. And that manifests itself. The system is still a Fermi liquid, but the coefficient of T squared is essentially the maximum value allowed.
Okay. So presumably if you go up in frequency even further, eventually you lose that oscillator strength. At what point in frequency do you expect that? And what does that correspond to in terms of the quadratic band crossing?
Yeah, so you should see that. Oh, I'm sorry, I don't have the slide here. But essentially when you hit, if we imagine the bands don't have exactly the same mass.
Okay. Yeah.
But let's imagine they did. So let's say if the chemical potential is, so the chemical potential is down here. If they did, it would be an energy which was approximately 2 times the Fermi energy.
Yeah.
So
got it.
If the masses were the same. So the energy is 10 millieV measured from the node. We're talking about 20 millieV is when you would start to see deviations. And unfortunately, these films were grown on a substrate which was very lossy. It's very
opaque in that frequency range.
Yeah, in that frequency range. And so we weren't able to go with this or any other technique up to those frequencies. We've looked for this in single crystals, but single crystals seem to have higher densities, and we weren't able to see. You should see a very interesting cusp in the dielectric constant, but we haven't been able to see that.
Yeah, that's what I was thinking. That measuring through that frequency range where you no longer have that virtual process or that process between the interband would be kind of cool. Especially
so
if
I think our best
gate a film. and tune it around. That would be very
yeah.
cool.
So I think that's what the best bet to do is. So here you can see, in fact, usually when we measure our terahertz, we can measure up to at least 2 terahertz. And in fact, here I'm cutting the data at 1 terahertz, and that's because the data becomes very poor above 1 terahertz, because the film is the substrate starts to be very has all this kind of dielectric loss at those frequencies, and so we get very, very little terahertz through that in that range. So then the thing to do is indeed to make a gate. We've played around a little bit with this in with some of the films we had with dielectric gating, which is a very nice way of doing this experiments with terahertz, because you don't see the dielectric, this kind of gel on top.
Liquid ion gating stuff, yeah?
Yeah, ion gating, that's right. You don't see this ion layer on top. A metallic gate, of course, you see, but this insulator that you put on top, maybe in a gel form, you don't even see, and so you can deplete the films. We don't have very many films, and unfortunately, they're not growing them anymore at ISSP. So that would be a great project for the future. And what you would expect to see is as you change the gate, you'd expect to see some funny threshold move through the spectral range and come down, and then all kinds of crazy things should start to happen with the metallic transport as you come into this non-Fermi liquid regime.
Peter, did you have Peter Orth, you have the last question before we move on?
Some of it was addressed. I was just wondering, so you were saying, Peter, that that there's a strong interaction. Is that based only on the large dielectric screening, or just generally? I was thinking if you strain it and you have a small gap topological insulator, that could be very interesting. Like if interaction effects are comparable to the gap scale.
So that's also, I'm talking about effects which are kind of okay. So there's a number of different things that can happen, and I think people debate about what's the low temperature fade of a quadratic semimetal, low temperature, low energy fade of a quadratic semimetal. So there's been Igor Hrbut, for instance, has a number of papers where they claim that you get basically a mod insulator, that you get some kind of spontaneous generation of a gap. Even in the quadratic band touching, if the non-interacting band structure is quadratic with no gap, you'll spontaneously generate a gap. There's other proposals for various kinds of magnetism, which can be generated spontaneously as a result of all that. That would be very interesting. Of course, we don't know really what the low temperature, low energy fade of a quadratic, band touching system is. It could be that as you take the system to lowest temperatures, indeed interactions are strong, you generate this gap, and that could happen before you ever get anywhere close to Abrikosov's non-Fermi liquid state. We don't know. Yeah, I think precision mirror-date is a very interesting system to look at it. Another possibility for other systems where this physics should be present but hasn't been investigated a lot is in Hafweisler alloys with bismuth. And so those don't have masses as large as these oxides, but they should have masses, which are quadratic masses, which are larger than alpha tin. And so materials that are, the one that's been looked at a lot is gadolinium platinum bismuth, but that has, of course, magnetic ions in it. So what you'd like is, I guess, yttrium platinum bismuth. Maybe that's a nice material to look at. That has all non-magnetic stuff, and would be a very interesting material to look at and see, what happens at the lowest temperatures in the system. The problem here in precision mirror-date is it also has 4F physics, so we don't really know. If something interesting happens at the lowest energy scales, you don't know if it's the 4Fs taking over or not.
Sure. Thanks.
All right, thank you, Peter. Thank you very much. Good discussions too. So if you unshare, and then Anand, if you're ready.
I think so.
Yeah, very good.
That's good.
So the last speaker for the day, Anand, go ahead.
All right. Application window, I want this one. All right, hopefully you guys can see this. Let me know if, can you see everything now?
Yep.
All right, so, well, it's been a really wonderful conference, and on behalf of all the organizers, let me first thank everybody who attended and participated. It was very lively. In fact, we were trying to get Satoru to join us as well. Unfortunately, couldn't make it to have some more thin films represented at the conference at this workshop. So today I'm going to talk about epitaxial thin films, our own efforts in growing epitaxial thin films of Kagome metals. And this is a lot of people involved here. I won't go through the whole list right now, but I'd like to call out the three postdocs who've been kind of really pushing this along. Daeshun has been sort of leading this charge on this effort, Daeshun Hong. And toward the end, the films that I'm going to show you, the sputtered films that I'm going to actually talk about, were grown after a very long and fruitful effort by Sam Zhang. Okay, so we had a lot of introductory discussion today about Kagome semimetals. So I'm not going to talk very much in detail there. I'll go through it reasonably quickly, and then I'll talk about our efforts at thin film growth of Kagome semimetals and some of the challenges that we have in obtaining good samples. Then I'll tell you a little bit about what we did obtain successfully eventually, and we have a paper actually in the archive that I'll talk about that's just been accepted actually on the anomalous Nernst effect and inverse spin Hall effect in manganese-3 germanium films. Okay, so we heard a lot about this today. This is of course this chiral magnetic structure in manganese-3 tin and manganese-3 germanium that gives you this amazing anomalous Hall effect and also other thermogalvanic and spin optical properties. And we also heard about how this arises, symmetry allowed essentially by the existence of this glide mirror plane that lets you have a non-zero Berry curvature in a direction perpendicular to these planes. And that's one way to think about why these systems may have a significant anomalous Hall conductivity. And the fact that that these are also wild semimetals gave us all got people really excited, because they said, well, look, this is the reason why you have this very large Berry curvature. There are these wild points close to the Fermi surface. We saw these pictures today morning from Binghai. And also, he pointed out very rightly that the high Berry curvature could not only come from wild points, but also avoided crossings between different bands. Okay. So, this data was also, I think, shown today, but this is basically, from Nakatsuji's group, where they did show some evidence for wild points, if you will, by measuring transport and showing that there is what looks like a chiral anomaly type effect, where when you apply a current parallel to a magnetic field in a film where your magnetic field, imagine in this Kagome semimetal structure, you have magnetic fields applied in the plane along some direction, you apply current parallel to that direction, you see a large positive magnetoconductance. And when you apply it in a transverse direction, if you will, you get a negative magnetoconductance or a positive magnetoresistance, as you might expect from regular orbital physics. And so they used the systematics of this to prove or to argue that this was consistent with having wild nodes. And they also did some RPEs that shows that there are wild nodes in this material. But this is always a little bit contentious, because these can also arise out of some artifacts, and at this point I think we should still keep an open mind. And it's really interesting to know that, for example, the very large Berry curvature and avoided crossings can also give you interesting effects. Okay. But nonetheless, going back to the beginnings of this EFRC that we are all a part of, the ones, at least our CATS EFRC, we realized early on, of course, and as did several other people, that there was a huge opportunity in growing high-quality single crystalline thin films of these topological semimetals. And part of this is that things like, for example, the chiral anomaly, or if you want to measure the chiral anomaly and do it in a way where you can get away from artifacts, you're probably better off using thin films, because the current jetting effects that Peter just mentioned are actually strongly mitigated if you do measurements carefully in thin films. Secondly, if you have really smooth surfaces, you could do good RPEs, whereas if you could also cleave crystals, but sometimes cleaving crystals can be painful. They don't always give you a good, reliable surface to do RPEs on. And then, of course, there are fundamental predictions that really require you to have high-quality thin films, like, for example, the quantum spin Hall effects, edge states, quantum anomalous Hall effect, that kind of thing. Or if you wanted to, as you just heard, tune properties of, say, of Dirac or a wild semimetal by gating them, again, you're probably better off with a thin film. Or if you want to go look for things like novel spin and charge transport properties. You want to look for the spin Hall effects. Those are typically done in heterostructures, and those are also your great advantage if you have high quality thin films. And then, of course, again, there are these very novel mesoscopic effects that have been predicted going back several years now that could really only be non-local effects, for example, that could only really be explored in high quality single crystalline thin films, or maybe micro machine mesoscopic structures. But those are all those are ways you could do it. Okay, so all right, so there's a lot to be done here, and I think going sort of maybe going a little bit beyond what Peter mentioned about what are these materials and what can you do with them. Well, this is kind of falls in between those two things, but these are the kinds of effects that are also very fundamental to our understanding of these materials. Okay, so in fact, this field is moving really fast. And again, I'm going to point to work by Satoru and collaborators, where they use polycrystalline thin films. You saw a little bit of that today. And what they showed was that you can actually do sort of a spin Hall effect measurement, where you have rather inverse spin Hall effect measurement using non-local spin injection. I won't go into the details of this, but essentially what they showed was that spins are absorbed by manganese-3 tin while they're traversing a copper wire. So there's a little region of manganese-3 tin in between where they get absorbed, and that attenuates the flow of spins. And from that, they were able to say something about the inverse spin Hall effect in manganese-3 tin. Most recently, there's this very beautiful experiment, again, done by Nakatsuji collaborators, where what they did was they used spin orbit torque to, and they took one of their films where this was a polycrystalline film where the planes are now, Kagome planes are actually pointing, some part of the film has Kagome planes pointing out of the plane. And then when they drive a current through a platinum layer that is deposited on top of this polycrystalline manganese-3 tin film, they're able to drive a spin current into the manganese-3 tin. And by doing so, they're able to torque this, what's called a quadrupole moment, if you will, and be able to switch it to some extent. And you can see those switching phenomena on the bottom right. So, so here what they've done is they've measured the anomalous Hall effect in that system as they drive a large current through the overlaying platinum. And when they do that, they can obtain these switching phenomena that they attribute, in essence, to switching this quadrupole, octupole moment. Sorry. Okay. So this is really exciting because they've shown proof of principle, and others have done other experiments where they clearly see very cool phenomena, and we wonder where we could go if we had really high quality thin films. What are the fundamental limits of these effects? How far could we go? What are the origins of these effects? All kinds of very simple, basic questions still remain to be answered. Okay, but these materials have been around for a while. I mean, those papers came out in 2015, and you can bet that a lot of people got interested. But why haven't people been able to make high-quality thin films of these things? And because in principle, you can evaporate manganese and germanium just fine from lots of different kinds of sources. So what prevents you from doing it? In manganese-germanium, for example, it turns out that 3:1 ratio, if you just grew an alloy of the stuff, is just not stable. It'll segregate. Okay, in fact. One of the reasons people think that there is excess manganese is to stabilize the structure. If you don't put the excess manganese in, you don't get that phase that you're looking for. So there may be very basic reasons why these are challenging to grow, and that's not even the full story. But there could be intrinsic reasons why these are not like line compounds like gallium arsenide, for example. Okay, so you're always going to be limited in some sense, or enabled by kinetics or some other thing that you'll do in your growth to enable you to make high quality materials, which immediately limits the phase space of what you can do. Okay, so we actually, or by we I mean the royal we here, Daeshun, labored away at trying many different substrates, conditions. I mean, he really tried a lot of different stuff over the course of a year and a half before COVID hit, and what happened was that we found that, in fact, when we grew manganese germanium on, in this case, an oxide substrate, lanthanum aluminate 111, what we found was that actually the films did not grow as a continuous film. And if you looked at the X-ray in this thing, this X-ray is actually very good, very nice rocking curves, sharp peaks. If you look at the read, which tells you how crystalline the surface is, it's not perfect, but it's not too shabby. I would say this is okay. You're seeing a nice read pattern that tells you the surfaces are smooth, and that checks out when we do AFM. But when we do, when we of course look at the AFM, look at the topography, what you observe is that there are these tiny, islands that are sub-micron in size that are typically of the order of hundreds of nanometers across that form an unconnected, if you will, network of islands. They don't touch each other. There's of course some conduction, but it's not a reliable, you can't do transport on this in any reliable way. Okay, so, and the reason for this is that manganese germanium and manganese tin both have this tendency to de-wet, okay, to not wet a substrate that you're growing it on. They have some surface energy issues. Okay, so in fact we found this also in iron tin, another Kagome metal, where again we get beautiful read, nice X-rays, but when you look at the actual the way the film's growing, you notice that indeed they have atomically smooth surfaces, but these islands are disconnected from each other. Okay, so and that's TEM on the right from Jianmin Zhuo's group from our films, showing us that we have nice crystalline films. So these are high quality films, if you will, crystals, but they have an issue with the morphology. So in fact, Daishun then went ahead and actually did transport on these islands. That turned out in iron tin, we can get them to be a good fraction of a micron, or even several microns big. And he measured several of these samples, and I won't go into the details, but what we saw was consistent with what's been reported in the literature for R versus T, for the resistivity as a function of temperature, and also for things like magnetoresistance, Hall voltages, etc. So anyway, but that story is still not done. We've got a paper on the archive that tells us that spells out these details. This paper is under review right now. And we're not the only people, of course, trying this. Like I said, this is what I'm showing you here is TEM of a film from Claudia Felser's effort, where what they did was they again grew manganese 3 tin on zirconia, and now notice they have a ruthenium underlayer in that film. And it turns out that the reason why they use ruthenium is because ruthenium has a very high free energy, and if you use the ruthenium underlayer, that is known to promote wetting. And but even though they tried the ruthenium underlayer, it turns out they didn't get a connected film. They got these sort of, again, island morphology that I'm showing you here. So we were not the only people suffering essentially from this issue. But nonetheless, when our MBE effort, parallel to our MBE effort, we had also my colleague at Argonne, Sam Jiang, was doing some magnetron sputtering himself, and he followed along somewhat the same route. He went down this road of using sputtering to do manganese 3 germanium, and the way he did that was he sputtered manganese germanium again on alumina ruthenium. Alumina covered with ruthenium buffer layer substrates. So it turns out ruthenium can be grown really, really. I mean, there's the formulae for the recipe for growing really smooth ruthenium on alumina well known. Sam Jiang did that, and he then used his sputtering system to grow a manganese 3 germanium on there. And what you see here is X-ray diffraction and reflectivity, showing you that you indeed do have single phase, single crystal manganese 3 germanium. Though the rocking curves are a little broad, they're like about half a degree, a little more than half a degree for the full width half maximum. And I'll show you why that is in a second. And compare that to our rocking curves from, say, MBE grown films that are a lot smaller, like factor 5 or maybe even 10s narrower. But on the other hand, when you look at the film, you look at the morphology is connected. It's got a nice smooth surface. Definitely something you could, and it's thick enough that the ruthenium underlayer, the conductivity of the ruthenium underlayer does not affect or the properties we're looking for, or you can subtract that away in a meaningful way. They don't overwhelm the film itself. Okay. So all right. So indeed, when Daishun and Sam Jiang went and measured the structure of this guy, they found that indeed ruthenium grows on alumina epitaxially in a manner that we expect. There's a 6-fold symmetry of the ruthenium 101 bar 1 peak here. This is called a phi scan. All this is telling you is that they are that the hexagonal sort of layers of the ruthenium 001 orientation ruthenium and alumina are in registry, but they're off in their orientation by 30 degrees. And the manganese 3 germanium actually has a really good lattice match to ruthenium, and it grows very nicely on top of that. So we checked all of the structural properties of manganese-3 germanium, and they check out that you know that you have a nice single crystalline epitaxial thin film. Okay, but of course you need more eyes than that, and we did TEM on these films, and while large areas of this thin film will look really like it's crystalline and in registry, but if you look closely, you'll actually see some moire patterns in this TEM, and those moire patterns actually arise as a result of having some crystallites that are misoriented, and we believe that from our data that this is consistent with the sort of rocking curves that we are seeing. Okay, so I won't go into the details of this. And the AFM of our films now show continuous smooth films. The scale bar here is plus and minus 2 nanometers, and the reason why it was kind of blurry is not because the resolution of our AFM is low or anything like that. It's because they're just really smooth features. So there are these finger-like features on the surface on this length scale of a couple of hundred nanometers that permeate the whole surface. It's uniform. It's very smooth, and as you saw in the X-ray reflectivity, it's just that it's got these modulations, long wavelength modulations on the surface. Okay, but those modulations are not high. They're a couple of nanometers up and down. Okay, right, and the film is about 100 nanometers thick in this case. Okay. All right, so as we also learned, manganese-3 germanium has got remarkably low magnetic moment, and I should tell you that our manganese-3 germanium is not really manganese-3. It's more like manganese 3.2. Our films. And our films still don't have appreciable moment. They have a moment, you can measure it, but it's only about 100th of a Bohr magneton per manganese. We also know that they're antiferromagnetic because we can measure an exchange bias. We can cool it down from above the Newell temperature in a Tesla or so field, and then do a sweep of the magnetization of the film. And here we're measuring a permalloy layer that is ferromagnetic deposited on top of the manganese-3 germanium, and on the right. And what you observe is that indeed there's an exchange bias, and this exchange bias is a couple of hundred Oersted. So that tells you that there is antiferromagnetic correlations at the surface of the manganese-3 germanium, and that this is ordering at some temperature above above, let's say, 380 degrees Kelvin. All right, so we then okay, so we should mention that recently Stuart Parkin's group actually showed that they can grow manganese-3 tin following a very similar recipe. They also used ruthenium underlayer for their film growth. They used an STO111 substrate to get their 0001 oriented manganese-3 tin. And in our case, so we used, remind you that we didn't use STO, we used alumina. And in their case, they also used a different substrate, MgO 001, where again, using a ruthenium layer on top, they were able to actually get a textured film, which was actually oriented along 404 bar 3. And again, this is a fairly high quality thin film, and this is really exciting because you can actually get these planes that are not flat, but they're pointing at some angle to the surface. Okay, so you can now start doing things like doing transport that's along those planes vertically, or perpendicular to the planes horizontally. Okay. So anyway, so there have been some exciting developments now in this field, and we have gone ahead and measured, looking for similar properties that other people have seen in manganese-3 germanium and manganese-3 tin in our films. And in fact, I think we have the first measurements on thin films of manganese germanium, if I'm not wrong. And we measured this anomalous Nernst effect. And just a reminder, and you heard today earlier from Bing Hai and from others that the anomalous Hall conductivity and the anomalous Nernst conductivity, they are actually different in the sense that the weighting functions, or the pondering function, like Kamran pointed out, are different. So for anomalous Hall conductivity, you have to integrate overall occupied states. So your pondering or weighting function is a Fermi function. Whereas when you look at the anomalous Nernst effect, you have to sort of take a derivative of this. And what ends up happening is that the way these things weight near the Fermi level is different. So, and as it turns out, right at the Fermi level, if you're right at the wild point, the anomalous Nernst effect is vanishingly small. But as you just go a little bit above and below, you get a very large change. So the anomalous Nernst effect essentially changes very sharply through this region. And so it's got sort of a complementary probe. So the anomalous Nernst conductivity is on the right here. The Hall conductivity, okay, the rightmost is anomalous Nernst, A and C. AHC is the second from right. And you can see that those things are sort of different. And if you're near the Fermi level, you should measure both, essentially, to know that you've got an effect coming from these wild points. And if you could tune the Fermi level, that'd be even better. Right? So anyway, so all of this was pointed out, actually, back in the day by, not in the context of, actually, it was pointed out by Di Zhao and company in the context of Berry curvature and its effects on anomalous Nernst effect. Okay. So, so we went ahead and measured the anomalous Nernst effect in our films. And the way we do that, remember, our films are c-axis oriented, so that all the c-axis is pointing out of the plane. So we actually can't measure the anomalous Hall effect in the usual way people do, because we cannot drive current in that direction. What we can do is the anomalous Nernst effect. The way we do that is we apply a heat gradient across our film, across the thickness of our film in the vertical direction. And the way we do that is we have a gold wire that is deposited on top of our film, but of course it is isolated from it by a silicon nitride insulator. So you have a heater wire on top of our film. You run a current through the heater wire at some frequency, omega, and then heat goes through the vertical direction, if you will, some flux of heat at frequency 2 omega. You lock into that, and you then do a measurement of the Nernst voltage by applying a magnetic field now in the plane of the sample. And you know, let me remind you that the Berry curvature is in the plane of the sample. So when you do that, you can also rotate the magnetic field. You can do all kinds of interesting things. But here, what I'm showing you is on the right is just a measurement of the anomalous Nernst conductivity, anomalous Nernst coefficient, while sweeping the magnetic field back and forth in a direction transverse to the voltage measurement direction. Okay, so these are three mutually perpendicular directions, and you're just sweeping the magnetic field. And to compare, we actually measured also an iron film using our same technique. And you can see that our anomalous Nernst conductivity that we obtained for manganese-3 germanium is comparable to that of iron, even though our magnetic moment in our films is, you know, very small, like 10 to the -2 Bohr magneton for manganese. Okay, so it is consistent with the literature on these systems. Again, ours is the first measurement of thin film, I suppose, so that's good. And we've got a, you know, that pentagon that I have, the red pentagon there on the left is our film. On the x-axis is the magnetization. On the y-axis is, okay, the x-axis is magnetization, y-axis is the Nernst coefficient. All right, so indeed we have very, you know, very substantial Nernst effect measurement, Nernst effect in our films, consistent with this whole idea of having a large Berry curvature. Okay, so we also went ahead and measured the inverse spin Hall effect in our films, and the way we did that is via spin pumping. So I'll just go through this very quickly. So the idea here is that you put a ferromagnet, in this case permalloy, in contact with our film, which is the detector, right? And what we do is we excite a ferromagnetic resonance in the ferromagnetic permalloy film. And the sense of, so the magnetic moment here is pointing, let's say, in the vertical direction. You excite a resonance, it starts precessing about that direction. And then what happens is that drives a spin current into this, what's usually called the inverse spin Hall detector layer. That's usually a metal like either platinum or tungsten. And what happens is that this current of angular momentum traverses this interface and goes into the adjacent layer. And when it does so, essentially what it does is it broadens out the FMR resonant frequency line. Okay, it's sort of a loss of angular momentum, if you will. And the broadening depends upon this one factor, the interface factor, if you will. It's called the spin mixing conductance. That tells you how transparent the interface is to this flow of angular momentum across it. Now, the way the angular momentum gets taken up by the metal to the right here, shown in blue, is through a spin flip scattering process. So what happens is an electron that's spin up is incident on the interface. It flips its spin and goes to the right. Okay, that's a spin flip scattering process that absorbs that angular momentum. Now, you notice that I've drawn this electron trajectory as a curve. I mean, it's really specular, so it should just be straight in and straight out, but actually it curves. And the reason why it curves is because of a spin-dependent scattering process. And this can happen due to skew scattering and other things, side jump scattering. But essentially, something that gives you a spin-dependent scattering like this will give you what will turn out to be a voltage in a direction transverse to the flow of the spin current. So an electric field is developed. This is called the inverse spin Hall effect electric field. EISHE, and that electric field is what we end up measuring. We end up measuring a voltage essentially. Okay, and the way that that is quantified is through something called the spin Hall angle. The spin Hall angle turns out to be the ratio of the spin Hall conductivity to the longitudinal normal conductivity, and that depends on something called the spin-Berry curvature, which also is something we saw today in Big High's talk, I think, and that essentially is like the Berry curvature, but instead of the velocity operator, we use, instead of Vx, use Jx, which is the spin current operator. Okay, so it's the analog of the Berry curvature for spin currents. And due to this, when you have a spin-Berry curvature, you indeed get exactly this. You get an inverse spin Hall effect, just like you would for a heavy metal like platinum or tungsten. And you can compare, well, how does your material do? And platinum and tungsten are sort of the standards, if you will. And so I'll show you what happens when we do the experiment. Okay, so we do this using a coplanar waveguide to excite a ferromagnetic resonance. And this is a very standard technique. The schematic of this is shown on the left here. You have the alumina layer, the substrate, ruthenium, then manganese-3 germanium on top, permalloy layer on top. That's your of the manganese germanium. That's your inverse. That's your ferromagnetic pump. Then there are two voltage tabs that are on the left and right in yellow, and also shown on the right. So that's where we're going to measure the inverse spin Hall effect electric field, if you will. And then there is a coplanar waveguide that is isolated from the manganese-3 germanium using an insulator. It's just deposited using liftoff, a silicon nitride insulator layer, followed by titanium and gold for our waveguide. And so we excite an RF excitation in that waveguide that drives a ferromagnetic resonance in the underlying platinum permalloy layer. And then that drives the spin current down. I should have some arrows and such pointing here. The spin current's driven down into the manganese germanium, and then a transverse voltage develops in the system where you can now measure that from left to right, if you will, on the right picture. You can see also the magnetic field is pointing along the center conductor direction, so that's the geometry, and that's the correct geometry for getting a spin Hall effect voltage. So it turns out that as in all spin Hall effect FMR spin pumping measurements, we essentially are measuring a resonance. So we sweep the magnetic field in this case while keeping the excitation at a fixed frequency. And when we do so, there's usually a symmetric and an anti-symmetric component. So it turns out that the symmetric component, the one that's shown on top here on the left, it arises out of the spin Hall effect, and its width depends essentially on that how efficiently the spins are being pumped, or how transparent that interface is to spins moving through it. And then the amplitude of the symmetric component depends upon how good your system is at converting that spin current into a charge current. Okay, so that depends upon the inverse spin Hall effect. Now, there's an antisymmetric component as well. That's somewhat an artifact that comes about as a result of the anomalous Hall effect in this particular geometry in the overlayer of platinum of permalloy that we have on our manganese germanium. Okay, all right. So when we deconvolve the stuff into symmetric and antisymmetric components, and we look at the symmetric components, then we can actually extract various things by using the formula that was shown you earlier. By looking at the width of this resonance, we can figure out what this what the spin mixing conductance is, the transparency of the interface to spin currents, and that turns out to be what I've written on the left. For platinum permalloy, it's like 25 per nanometer square, and for manganese-3 germanium permalloy, it's about 3 times higher, more than 3 times higher. Okay, so it turns out that permalloy forms a pretty transparent interface with manganese-3 germanium. So that's encouraging, which means that you can get a lot of spin current into manganese-3 germanium from permalloy, okay, through this resonance process. Then we can also look at the amplitude of this thing, and we can determine how good it is at developing an inverse spin Hall effect. Now I should mention that these curves you're seeing on the right were taken using exactly similar geometry, so nothing has been changed. So these different material systems that we're using, we've used exactly the same excitation currents, the same frequency of excitation, the same geometry for the devices. So it's as close to apples as we can make it in the lab. And so what you see right away is that indeed, the permalloy manganese germanium has a higher amplitude. It's got a wider, the full width half maxima looks like it might be wider. So when you go through all of this, and what we did was we couldn't actually extract numbers straight up because there were too many parameters we didn't know. But because we had exactly the same geometry for both manganese, germanium, and permalloy, and platinum permalloy, we could compare those two quite well and efficiently. And what we see is that our spin Hall angle ratio between those two, between manganese, germanium, and permalloy, platinum, sorry, is something like 8. Okay, and there's an assumption going in here that we actually extracted the spin diffusion length for platinum from literature. That's a well-known number. And for manganese germanium, we were lucky that Otani and Akatsuji recently published that from their work. So there's some free parameters here that could, not free parameters, fitting parameters that could probably evolve over time. But nonetheless, you can see just from the data that we get a pretty big signal from manganese germanium, and looks like it's a lot bigger than we get from platinum. Okay, so so I'm going to pretty much summarize and end here. But what we've shown you are what we believe to be the first large area thin films, continuous films of manganese germanium. Looks like the kinetics of sputtering are very favorable to making continuous films. I should just mention here that for sputtering, I believe our rate for deposition was more than 100 times higher than in MBE. So that may be an important thing. You may be it's equivalent of quenching essentially. That level of speed of growth is important in this particular process. The films were found to have substantial anomalous Nernst coefficients comparable to the best ferromagnets. We measure the spin mixing conductance and spin Hall angle, and they seem to line up with, well, okay, so the spin mixing conductance is very high, and the spin Hall angle is larger, substantially larger than platinum, maybe as high as 8 times larger than platinum. And I think the main point that I would like to make here is that, you know, we just at the beginning, I think, of this synthesis has taken us a while, and we're just getting started. And MBE is actually also moving along. We made some progress in our MBE films. And the thing about this is that if you can grow high-quality thin films, smooth epitaxial films, there's no doubt that there'll be key questions, the answers to which will be provided in somewhat more reliable way. Because I think one of the sort of issues here in this field is just that we are still learning how to make these materials. Okay, and hopefully as we make progress, these will serve as model systems for exploring mesoscopic spin and charge transport in these materials. And today we saw so much evidence for the amazing properties these materials have. So there's a good reason to go and try to make them well. So with that, I'd like to end my talk and also acknowledge the people who've done the work here, particularly the postdocs that I mentioned. They're shown on top left. Naveen Anand has been doing the spin pumping measurements. Chang Jiang has been helping in both aspects of transport and spin pumping the project. And then I'd also like to point out the great work that Sam Jiang did in actually growing the sputtered films and making that a possibility. So with that, thank you very much, and I'm happy to take your questions.
All right, thank you, Anand. Let's have questions and comments on Anand's talk. Right.
Oh, I didn't have my video on. All right.
Now it's on. That's fine. So, do you have any questions for Anand? You made everything perfectly crystal clear.
That's right.
This is Rob. I had one question.
Sure.
Is the hysteresis loop that you're measuring with the Nernst effect seems to have a much larger field scale than the magnetization from single crystal. So can you explain
Yes,
why
it does. Thank you. Thank you for bringing that up. Actually, I forgot to mention this, right? So actually the curve is right here. Yeah, there you go. So okay, let me get a bigger picture. So indeed, so in our Nernst effect measurements, our hysteresis loop is much broader. But notice something here. It's starting off, the reversal process starts off at a very low field, at a relatively low field, right? Well below Tesla. Let's say, actually well below even probably 0.1 Tesla. So it starts off right away, but it takes a while to reverse, right? So that's why I actually asked this question and we think that we don't know why that is, right? But it does not follow the magnetization. Our magnetization, if you look at our magnetization curves, I think that's over here, those are actually quite narrow. they're broader than what they have in the literature at 10 Kelvin, but they're still much narrower. I mean, the full scale here is like, probably, I should know the number here, but it's probably a couple of, something like 0.1 Tesla or something like that for the width of that curve. Indeed, it seems to take up to about, you can see that, right? Even at 6 Tesla, it's not done. At about a little over 6 Tesla low temperatures, at room temperature, this is at room temperature, you get to see the full, sort of reversible, so that's where this Rhesus loop kind of ends, if you will. So what we think is going on is that indeed there's an intrinsic field at which it begins to reverse. That's fairly low, but perhaps the reason why it's not reversing fully is that these, if we believe these to be sort of, having these octopole moments, if you will, reverse, that's the order parameter you want to reverse. If that's what's going on, then what you need is, maybe they're being pinned. Those antiferromagnetic domains are being pinned by defects in our film, and as a result, they take a long time to reverse. They take a very high field to reverse. That's probably the reason why. So the width of this thing indeed is quite high, as you can tell, but also, like I said earlier, it starts early. It doesn't, it doesn't persist out to 3 Tesla and then switch. It's not very square. You can see the shape of it. And this shape is actually not that different from what I saw earlier today from in some of the data in what's his name? And in Kamran's talk.
I'd like to add that. So as one of the
so guys, this is Changjiang, by the way. This is Changjiang.
Yeah,
go ahead.
So as one of our speakers talked about today, the difference in the line shape between the magnetization and the anomalous effect could be an indication of the topological Hall or the Bay curvature. So or arising from the skyrmion type of contribution.
Yeah, so the thing is, there might be domain walls, and if there are domain walls, then there could be other interesting things going on that give rise to this.
Well, do you remember what Kamran said there was a sort of intrinsic field scale for domain wall reversal. I mean, I don't remember offhand what that was exactly.
Yeah, I'm trying to remember. It was like 50 or 500 or something with 5 in it. I'm trying to remember what. I don't have that data. I don't have that.
I took notes, but unfortunately, I didn't write that field value.
Yeah. So I think for Cameron's data, it was only 20. So the kink shoulder was only 20, and then it was of the order of 100 Ørsted by the time the loop was closing up.
Is that right? Okay. Good.
But the shoulder in the M of H.
Yeah.
The sharp feature was only about 20.
That's right.
Ørsted.
Could well be, yes.
Right. Other comments, questions on this talk or Mn3X in general? There's a lot of interesting stuff that was brought up today, and it's clear that we certainly don't know everything about these systems.
Well, I'm wondering if Colin is here. Is Colin around, or is he? Well, we already asked him so many questions.
I'm still here.
Hi, Colin.
Hey.
So in your when you did the critical exponent analysis, when you're measuring near the transition,
yes,
or even beyond that, did you think you had a single domain sample? I mean, what was going on there? Do you ever see any evidence for what you might call our domains in your sample, domain formation?
For the critical properties, that was in zero field, and so there we would have had a multi-domain sample. And we have, well, I mean, we have actually tried to do some small angle scattering to look for domain wall effects, and we're still interested in this, but it's not has not concluded yet. I mean, when I look at these data and then connecting to Benion's talk, it would seem to indicate that there could be a very extended skyrmion regime in the thin film.
Yes,
It doesn't seem
indeed.
like a crazy thing. I mean,
no. I mean, that actually was. I got pretty excited when I heard Kamran talk about that, and I had not read his paper. And
maybe this is a way to really enhance the skyrmion character of the domain walls, and then But we need some sort of real space tool to actually look at this.
Indeed. You know, but I'll tell you something, that the field scales are high enough that that I think, you know, I'm always thinking about the real material, like it has defects, it has other things going on. So who knows what's really going on, what's spinning those domain walls, and what the actual character of those things is. But I do believe this is pretty promising as a place to look. The problem is, of course, there's not any moment that I know that would be associated with this, right? So I don't know if the moment would be detectable or how you'd look for it and what the length scales are at which you're looking at. So I'm not sure. So maybe you have some ideas, but when Kamran was talking about that, that's what's spinning in my head as I knew about our data, and it's just like, okay, what's the how would you actually look for it? And it's not very clear to me.
It will be surprising to have these fermions persist up to several Tesla.
Yeah.
Yeah, I agree. The thing is just that the curve itself looks so much like what you see in the bulk samples. It's just everything is stretched out.
Yeah. Yeah, I mean, the thing I would think about is, Sam, to your point, is that the exchange interactions are quite substantial, right? So I don't know what would, I have to actually visualize what I didn't quite catch that, what the visualization of the fermion really was. What was it actually meant by a fermion? I don't still have it in my head yet. So
well, I mean, it was a magnetic texture that does give rise to a fictitious field, right?
That's right. So my question there, Ula in particular, did you have any there were no out of plane components as far as I know, right? Everything was in plane. Is that correct?
Well, if you don't have an out of plane component, I think you get no sort of fictitious magnetic field at all.
Yeah, I think the whole point was that he was saying there wasn't out of plane.
Well, yeah, so
okay.
So that's what I think, right? But this does talks that with a spin orbit interaction, you can have in plane magnetization, and you may still get space barriers, right?
Yeah, I didn't quite remember if Kamran talked about that or not, but yeah, okay.
No, it did not so much, I think. I mean, he was just talking about if you have a magnetic texture, what's the sort of real space field that you would get from that.
Okay.
So do you think that this, maybe it's false to differentiate this, but is this a dimensionality effect, or is it a impurity pinning effect that's stretching this out in field?
Oh, geez, I would say the following. I would say we need to grow better films and keep going in this direction and see what happens. And I can tell you offline. We do have some different films of narrower rocking curves now that I didn't show. But they have lower coercivities, but not as low as the single crystal bulk samples. And also, I'm really curious to also know something. I would like to learn more about the defect states in these bulk samples. A little bit of that was discussed today, right? What is the nature of the defects? And what does that do to the magnetic pinning, if you will? If there's some idea, if there's some, these are frustrated systems. Who knows what happens, right? When you have something that's not quite balanced out, and then I just can't, without maybe having something to stare at, I don't know what to think right now. Yeah, because I can tell you this, I mean, given the way the exchange interactions behave in the system, and Ula's been trying to model this, right, using his atomistic modeling, and clearly there's a lot of room, I think, for frustration and pinning and stuff like that.
Yeah,
Ula, would you agree with that?
No, I do. I mean, yes, I've done a boatload of different sort of finite temperature modelings of these systems, and I think the one thing I can say for sure that I understand is that they're very complicated, and another thing is that what's surprising, as Colin pointed out, the sort of anisotropy, sort of single ion anisotropy energy as derived from their neutron measurements is say 0.01 or smaller milli-electron volts, right? And one thing I've learned for sure is that scale sets in, that scale of the anisotropy energy. I mean, you'd imagine that doesn't matter at all at temperatures until you're down to sub-Kelvin, but it actually comes in at that anisotropy energy comes in when you're at temperatures going up towards 100 Kelvin, which is sort of a bit of a mystery for me. That anisotropy actually makes it different at those large temperatures. So that also means that the actual ordering that you get at lower temperatures is very sensitive to exactly what the anisotropy is.
Yeah, that was the message also,
Even,
right?
Even at those very, very small values, which is really sort of baffling to me, because it's certainly nothing I've seen before.
Yeah, that was my question actually with Colin, is that if there was some way he could figure, if there was, that if those things are only separated by a few millielectron volts in energy, let's say, then at 300 Kelvin, there should be some degeneracy, right? And so is there some way to probe that, or to know if it's there? Which would be, I mean, either way would be interesting to know. That's good.
I mean, 300 is getting rather close to the critical temperature in the germanium case. For tin, it's the temperature is higher. But overall, I would expect, that these this beta mode in the case of the germanium should begin to become populated as we heat up. And then those lie over the gap energy is around 3 millielectron volts, but the peak is quite broad. So in the course of heating up to 50 or 100 Kelvin, we're really going to be populating these out of plane modes, and that may be where this kind of 100 Kelvin scale comes from, essentially, in some of the transferred measurements.
Yeah, that's what we were also staring at and saying, okay.
Yeah, we haven't actually. I mean, we could certainly, one can do inelastic scattering at the elevated temperatures, but it's more or less. Right now, it doesn't seem like something that will be very surprising. I'm expecting that this gap will fill up as you thermally populate the beta mode. Yeah,
because those data you were showing, right, where you did the very fine refinement between, that was a low temperature measurement, right, on manganese germanium.
Yes.
Okay. And is there corresponding measurement at, I don't know, at 100 Kelvin on manganese 3 tin? Does that exist, or?
What I showed was manganese germanium. And manganese tin, we're working on it, and it's in process.
Right. Okay.
Well, and I think also, I mean, the order at different temperatures of the magnetic structure, different temperatures, and then connecting them to the Kamran stock, that I thought was really interesting too, right? Where he was talking about the relation to mobility.
Yeah, that was very cool.
Whole other chapter that there's a lot to explore.
Yeah. So one other question, if both maybe the neutron scatterers are all here. I don't know if they're both here, or okay. So was there any decision about the transfers thing you're seeing, Colin? Is that just basically averaging out to 0, or is that what you're saying? That there was some volume within which they're pointing one way and then they're screening each other out, essentially.
Yeah, by symmetry, we would not expect an imbalance in those transfers.
That's what I'm thinking. Yeah, so there's no reason to. Okay.
No,
okay.
But in diffraction, we're just seeing the projection onto the normal plane of the wave vector, and we just see that there is this. And I mean, I think it's pretty. It's very difficult to get around this fact that there is some sort of ferromagnetic component. Sure. But it has this curious aspect to it that any direction that I apply the field, the part that I pick up in my susceptometer, I'll never see this because it's always.
Sure. That was kind of, that was interesting. Yeah. So the other question I have for you is, do you understand why Professor Boothroyd mentioned that the anisotropy difference could then allow or give rise to this perpendicular moment, the ferromagnetic moment?
Yeah.
Did that have a handedness to it, or was it always going to also be canceling out? I mean, he mentioned that the ferromagnetism would be allowed. Now, so is there, given that the overall structure is chiral, would then prefer one direction over the other?
No, it wouldn't. So as you change the sign of the difference of these K parameters, then you will either enhance the spin, which is the bisecting spin,
right,
and kind of tilt inwards the other.
Okay.
Or
that's all.
The opposite. Okay. So it'll always.
Yeah. All right,
So,
excellent.
I think it looks like people are starting to peel off, and given the spread in time zones, that's maybe
Yeah, no,
not so surprising either. So before more people peel off, I'd just like to say that, you know, I've recorded this workshop, and if I can figure out what to do with that, how to extract it from somewhere on my disk drive, would like to make this accessible, of course, to the participants in the workshop too. So we'll figure out a way how to share that, and we'll send out information about that.
Yeah.
And again, I would like to thank all the speakers, those who are still with us, for taking time and being part of this workshop. I think it was very nice. A lot of really good talks. So thank you so much.
Yeah, wonderful. Yeah.
Yeah, thank you. It's been great.
Thanks for having us. Thank you for organizing.
It was really fun.
Excellent.
So with that, unless there are any other parting words, I think we can.
Yeah, Rob's sending everybody beer, but I think.
You say Rob or Ross? I think you meant Ross.
No, Rob. That was you.
Definitely Rob. Yeah.
Done.
You can both send it.